success. If you love what you are doing, you will be successful. A very good morning to all of you present here. I take this privilege to warmly welcome all our delegates on the first day of the HBNI interaction meeting on condensed matter physics. As said by our famous Einstein, people like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion. Now it's the moment of extreme pleasure to welcome our guests to the stage. On behalf of our institute, I take this honor to welcome our honorable chief guest, Professor J.B. Yakmi, to join here on the stage. The next dignitary to honor us with his presence is Professor P.R. Basudeva Rao, the VC of HBNI. Moving forward, I would like to request the respected, well-known director of Saha Institute of Nuclear Physics, Professor Gautam Bhattacharya. It will now be the turn of honorable guest, Professor B.K. Nayak, Associate Dean of HBNI, to grace the stage with his presence. Now, I would like to request Professor Satyajit Hajra, the coordinator of the organizing committee, who made this meeting possible, to join us on the stage. So let's have a huge round of applause for the esteemed dignitaries seated here on the dais. And now I would request the research fellows to distribute the bouquet. इधर ही। Thank you all for your presence. Hope to have a successful meeting. With this, I will conclude here and I request Professor Satyajit Hazra to deliver the welcome address. Thank you.
Yeah, thank you, Smriti. Eminent chief guest, Professor Yakmi, Honorable Vice Chancellor of HBNI, Professor Bhakti Rao, our renowned director, Professor Gautam Bhattacharya, Associate Dean of HBNI, Professor Nayak, distinguished guests, nominated speakers, colleagues, students present over here and on the online. A very good morning to you all. I, on behalf of the organizing committee and also on behalf of Science of Nuclear Physics and Variable Energy Cyclotron Center, welcome you all to the 2 days HBNI interaction meeting on condensed matter physics at SINP. It is indeed our privilege to organize the interaction meeting at SINP, which will not only help us to gain information about research activities going on in other HBNI institutes, but also help us to showcase our research activities in front of you. I am happy to inform you that within a very short notice, all the institutes have agreed to participate in the meeting. So we have representative work from each institute. This also makes a program very tight. So I sincerely request you all, the speaker, to strictly maintain the time of their talk. However, it is nice that the majority of the speaker, about 16 out of 19, have agreed to present their talk physically in this meeting. Regarding the program, today from 5 p.m. onwards, we will have a student presentation session, which is divided into two. In the first half, there will be a poster presentations, and in the second half, there will be online presentations. We have reserved the online presentation to the outside participant, while the poster presentation for the in-station participants. Tomorrow, from 5 to 6 p.m., we'll have a lab visit session, which will cover both SINP and VCC. We have arranged the conference lunch and dinner at VCC SINP canteens, where from the food we'll have a good chance to interact and discuss, which will be beneficial, particularly for the students. With these few words, I again welcome you all in this today's meeting. Thank you all. So may I now request our Vice Chancellor to deliver his speech.
Professor Yakmi, the chief guest of this program, Dr. Gautam Bhattacharya, directors of other constituent institutions, Professor Nayak, Professor Hazra, other faculty members of SINP, VCC, and other constituent institutions who are present here and online, and my dear students. At the outset, I want to convey my sincere thanks to Director SINP for coming forward to host this meeting. And my thanks also to Professor Hazra and Professor Nayak for putting in a lot of efforts to organize this program at somewhat short notice. But I'm glad that it has evoked a very good response from all the CIs. I'm not really a specialist in condensed matter physics, so I will restrict myself to some general comments. Of course, I know that condensed matter physics is a subject of vast scope, and the diversity of topics covered by this is makes it the most active field of contemporary physics. And I read somewhere that 1/3 of all the American physicists identify themselves as condensed matter physics. So that is the range of condensed matter physics, and research that we will classify today as condensed matter physics encompasses so many subjects, so many topics which we have heard sometime or the other, whether it's solid state physics or low temperature physics or statistical physics, all of this. And breakthroughs in the field of condensed matter physics have led to the discovery of many things which have really shaken science and led to the use of liquid crystals, modern plastic, composite materials, and so on. And I know one topic of high relevance to nuclear energy is also a topic of condensed matter physics. It's very, very important to run a nuclear reactor with a nuclear fuel when it's structural materials. We know the way defects form, distribute, and influence the properties of materials, whether it's a structural material or a control rod material or even the fuel material. So that way this topic is of great relevance to the department. I went through the technical program devised by our colleagues, and I found that it has put together a fascinating list of topics, and it shows the faculty of HBNI are highly productive in different domains of condensed matter physics. And this meeting will provide a good platform for them to have a broader perspective on the research problems pursued in different institutions. And I believe this will enhance mutual appreciation and later lead to collaborations. I'm highly thankful to Dr. Yakmi for readily accepting our invitation to join us today and share his perspectives. Dr. Yakmi is a champion of multidisciplinary research, and like him, I too strongly believe that there is enormous scope for multidisciplinary research in HBNI because we have eminent experts in a wide variety of disciplines available across the institutions. In the context of our being a university, I want to particularly highlight a few issues that I've been discussing with my colleagues, which have been bugging me also. Not only in the context of implementation of the national education policy, but also in the context that we want ultimately HBNI to be a desired destination for the best young minds in the country. If people, young students who finish their MSc or even a BSc, if they finally say HBNI is a place where I want to go, I think that should be the final goal. And for that, we need to do certain things in addition to what we are doing today. In other eminent institutions, and particularly those abroad, every student who enters the university gets a bouquet or choice of research problems which he can study, and he can choose what interests him, and that is what gives the best results. Sometimes even the choice of a supervisor is possible. It is there in many Indian institutions as well. HBNI has a world-class research infrastructure and excellent set of faculty in every CI. But the situation today is a young student who joins one of the institutions ends up doing a research that is pertinent only to that institution and with the infrastructure available only in that institution as far as possible. There are, of course, collaborations. It's not that it's not there. It's not zero. But there is a long way to go. And I would imagine the greater interaction between faculty and sharing of academic calendars is one topic I would like to suggest. For example, when a new course is offered in SANP, is it possible that this course is announced across the CIs and students from other CIs are also able to attend it online? So this is one of the possibilities that I've been always discussing with my colleague, which should happen as a result of such meetings. Another topic is why we cannot create courses that can be offered across the institutions. A given topic, let us say it can be statistical physics or it can be semiconductor physics, whatever. If we choose a course, I'm sure that we can find faculty from different institutions to give the lectures. And it's not necessary that all the lectures have to be given by a faculty from one institute. So this kind of approach will even make multidisciplinary courses possible by combining the expertise and diverse areas of interest in various CIs. And the last point I want to make is that we should also expect to see in the years to come the possibility of a student being guided by two experts across the CIs, a guide from the parent institution and a co-guide from another institution, This is also possible. So all these are things that we have to do if we have to become a really eminent university. And I'm sure it's just possible through such interactions. It is my desire that such faculty meetings should have the mandate to explore such possibilities and come up with specific recommendations. I am glad that Professor Yusuf has come forward to lead a discussion on such matters in the concluding session. And I hope that Director BRC will also find time to chair that session, and that will help us to arrive at a way forward. Now, this is about this meeting. I will now turn to a favorite subject of mine, and I spent a few minutes with your permission to talk about science history, which is a favorite topic of mine. That's because 2022 is a very, very special year for physics. We commemorate the 125 years of the discovery of electron this year by J.J. Thomson. We also commemorate 100 years of the Nobel Prize given to Niels Bohr. I wish some of the faculty here will come forward to deliver popular lectures on these subjects across the CI so that students can really get excited by listening to the developments which led to finally discovery of the electron and discovery of the Bohr model of the atom and so on. But my reason for talking about this is also a little different. If you study the work of Thomson and even that of the great Ernest Rutherford, this will demonstrate the power of synergy between experimental and theoretical physics. Today, we emphasize so much. You can see all newspapers, education policies, government statements, all of them emphasizing skill development. I would venture to say that behind many epoch-making discoveries, there was a skilled associate. And I will take the example of discovery of electron itself. In the case of Thomson, the discovery of electron was made possible by the use of specially created vacuum tubes. And each tube used by him was custom made for the work by his talented assistant, who was called Ebenezer Everett, who was a self-taught glassblower. And Everett made all the tubes used by Thomson in his experiments. And in fact, in a lighter vein, he was also responsible for operating them. He knew that Thomson was somewhat clumsy when it came to handling apparatus. And he told him, you don't touch the apparatus. You tell me what is to be done. I will carry out the experiment. In fact, here there's if you read the papers describing this discovery, it says he forbade Thomson from touching anything delicate on the ground that he was exceptionally helpless with his hands. And it was the help of such skilled people that we make us go towards the very big discoveries. The quality of this glass blowing was absolutely crucial for the experimental work. Similar was the case of Rutherford. When Rutherford carried out the experiment which demonstrated that alpha particles are nothing but the nuclei of helium, he had to use a very special vacuum tube apparatus in which the wall thickness was, if I remember correctly, it was 0.02 millimeters, allowing just the alpha particle to pass through and get collected. And later on, he analyzed and showed that it's helium. So this required extremely skillful person to make those vacuum tubes. And he depended on a German glassblower, Bombosch. And this man has made such experimental apparatus that I have seen many papers in which he has acknowledged that because of him, this experiment was carried out. Even Rutherford has written about that. It is not that before Thomson, nobody studied this cathode rays or carried out similar experiments. In fact, the great Michael Faraday, who later coined several terms containing the word electron or electrode, including electrodes, electrolyte, electrolysis, cathode, all these were coined by him. But he did not succeed in his experiments when he tried to make a vacuum tube and pass electricity through that to see what happens. He did not have appropriate vacuum systems to reach the high vacuum. Walter Kaufmann, another person, had in fact better data than Thomson, and he had also observed similar phenomena much before Thomson. But he did not have the courage. This is second quality. He did not have the courage to say that this is a fundamental part of matter. Even though he had what is called philosophy of what is called as positivism. He believed that unless you see something with eyes, you cannot believe it. It is very difficult to think that people can have that kind of notion. But this is what he had. So he did not bring himself to announce a corpuscle hypothesis, which finally Thomson announced. So that's how on April 30, 1897, J.J. Thomson announced that cathode rays were negatively charged particle, and he said that it's a building block of the atom. It was a risky thing at the time. Many people, in fact, made fun of Thomson for arriving at such statements, but ultimately was proved right, and he also won the Nobel Prize. Now one can see that Thomson's success was due to not only his own visionary approach in his knowledge in this work, it was also due to the excellence in design and fabrication of the apparatus and the courage and conviction he had in arriving at new theories. Let us come to the second topic, Niels Bohr. It is interesting to see that Niels Bohr was like many other scientists. I keep telling my colleagues that Marie Curie, who is well known for discovering radioactivity, her first paper was nothing to do with radioactivity. It was on magnetism in steel. Similarly, Bohr's first paper, which was published when he was 24 years old, was on the determination of the surface tension of water by the method of jet vibration. He had a fascination for liquid drops and he studied the vibration. And this paper and the next paper marked the early stages of his lifelong interest in liquid drops. But 30 years later, this was the knowledge and this was the background which helped him to arrive at the liquid drop model for fission. Why I'm saying that is very often people think that attending lectures or attending courses not directly connected with their present work is not of interest. It's not relevant. I don't think anything in science can be really termed as irrelevant. You never come to know when knowledge will come to be of great use to you. Before ending, I want to mention also that Niels Bohr had a very interesting Indian connection. Many people from here may know or may not know. He was visiting India as the guest of the Prime Minister Jawaharlal Nehru in 1960, and he was so impressed with the seminars being organized at Chennai at a place called Ekamra Nivas by Alladi Ramakrishnan that he expressed his admiration for the seminar at a press conference. And this attracted the attention of Prime Minister Jawaharlal Nehru, and when he was urged by the Minister of Education of Tamil Nadu, at the time it was called Madras, Mr. C. Subramaniam, he agreed to meet Professor Ramakrishnan and his students on December 8, 1961 at Raj Bhavan in Madras. So that's how Prime Minister met Alladi Ramakrishnan and he asked him, what do you want? I was told by Bohr that work being done is very excellent. He said, I desire that an institute modeled along the lines of the Institute of Advanced Studies at Princeton to be created in Chennai. And Subramaniam, the minister, was able to persuade Prime Minister to agree to the creation of Madras of a new institute, and within a matter of few weeks, Mat Science was born. That is how the Institute of Mathematical Sciences was born, starting from a visit of Niels Bohr to India. This year, I have to mention it because this year Institute of Mathematical Sciences completes 60 years, which is an important milestone. And HBNI is very proud to have in its fold such an eminent institute. I am very glad that some members from IFSC are also participating in this program. Before I end, I want to emphasize that I am a strong believer that a strong foundation in basic sciences is an important requirement for developing complex technologies. This I have realized all through my career and I have been emphasizing all through. And to support my statement, I only want to give a quotation from a person none other than Bohr himself. After his visit to Chennai, after meeting Alladi Ramakrishnan, he wrote back to Alladi Ramakrishnan thanking him for the hospitality. And I quote from that letter verbatim. It was dated 19 February 1960. And Bohr says, I deeply admire the effort you are making in building up such an enthusiastic and competent group of theoretical physicists. And then he says, and even if the primary aim for this is purely scientific, I feel that the effort will essentially contribute to the background for the endeavors to promote prosperity of your country by help of modern technology. So these are the words of Bohr, and one can see how we need a synergy between theoretical and experimental programs in every domain, finally to arrive at complex technologies which are required for the country and particularly the Department of Atomic Energy. So with these few words, I thank SINP once again for hosting this meeting, and the organizers and all the faculty who have traveled and or joined online to participate in the meeting. Thank you very much.
Thank you, Professor Vasudeva Rao, for his nice information about the history of science and mentioning about the HBNI in general. So may I now request our director, Professor Bhattacharya, to present his presidential address.
It's a great honor and privilege for me to welcome you all, especially the people in the dais, Dr. Yakshmi, Dr. Vasudeva Rao, Dr. Naik, and our colleague Satyajit, my colleagues from VECC and SINP, the students. I don't know whether all of you are from SINP and VECC or from outside, and all those who are connected online. I repeat, it's a great honor, privilege for me. I mean, to welcome you here at SINP. The genesis of this meeting was a formal meeting in HBNI a couple of months back, where it was strongly felt that we should, get together, we should act together to maximize our output. I don't want to repeat what Professor Basudev Rao has already said, but let me tell you very frankly, I did not prepare any formal talk. I was taking cues from whatever he was saying, so I'll comment on the complementary aspects that he did not touch upon. So regarding the utility of this kind of meeting, the most important is that in the present time, let us face it honestly and quite frankly, it is not possible for all the institutes to buy all the machines that we need. Okay, so we have to budget accordingly, and the rationing has to be judiciously done. So it is important that we start sharing not only with our colleagues, but also with our colleagues in other institutes. This is number one. The second is the students that Professor Rao has already mentioned. Sometimes, when the supervisors superannuate, well, it happens, it's a normal thing. Many students are kind of clueless as to how to finish their PhD, okay? They may have some co-guide from the local institute, but as a kind of a formal co-guide who may not be so keen as to, help that guy through, because just for the sake of formality, this person has signed as a co-guide. It is important that from the beginning, we may have, co-guides from other CIs, so that the students have a chance to visit other laboratories as well. First, if we buy an expensive instrument, it is okay if we optimally use it, but some of us, let me admit it, it is not also natural that we know how to maximize its output. The same instrument can be used in a different way with some different ideas by some other colleagues from other places. The same can happen with the instruments in those places, that our colleagues can go and use those machines with the idea that we have. So sharing has a lot of benefit that we have to, rely upon, and this kind of meeting, I mean, on a particular topic like this theme meeting in Condensed Matter, I believe is the first of its kind. A similar meeting can happen in a few months down the line in some other institute, where we'll be able to see the apparatus, the instruments in those places. So when you complete a cycle, then the students can also, visit those places, because you can tell your students that, okay, you go there, some of the instruments are there which you don't have. You can, make use of those instruments for this kind of physics. So this is about, the need of the theme, because it has also some bearing in hiring of the faculty members as well. It is not necessary these days to hire people of the same type in all institutes. I mean, this is a thinking that, we need to discuss and debate, with other institutes as well. I mean, this is my thought, that it is not necessary that, all institutes should hire people in a 360-degree angle. I mean, it's not possible, because we may not have the instruments, we may not have the apparatus to carry out experiments in all angles. But altogether, the DAE fraternity is very powerful. So the complementary sides should be looked into. I mean, some people, some institutes may have a long expertise, a long history of doing something for a long time. Other institutes may have a long history for doing something for a long time. Together, we make one single HBNI umbrella under which the faculties and the students can work together. Now, coming back to the aspects of history, I mean, it is also a privilege for me to tell you something about the history of this institute, that, it didn't start just like that. I mean, about 100 years ago, in 1915, when the physics department of the Calcutta University was founded, C.V. Raman was hired as the Palit professor. I mean, he was working in Bowbajar Street, not far from here, in a laboratory owned by Cultivation of Science. And when he was offered this Palit professorship, which is an endowment chair by the name of, from the donation of Sir Taraknath Palit, a very well-known barrister in Calcutta at that time, who donated, I forget now, nearly 25 or 30 lakh of rupees in those days. I mean, more than 100 years ago. Raman's first reaction was that, do I have to teach? So Ashutosh Mukherjee went back to the Senate of the university, and very quickly they came to a decision. See, that they're starting a physics department for the first time. They're going to give the MSc degree. I mean, what will happen today? Today, the vice chancellor will say, of course, you'll have to teach. That is the reason we are recruiting you. But knowing Raman's worth, the Senate, not just Ashutosh Mukherjee alone, decided that, and was, I mean, when Ashutosh Mukherjee, went back to him, he said, no, you don't have to teach. But the moment Raman joined, he started teaching. That's a different thing. But he was given the, flexibility of not teaching and doing pure research. He was giving a glass blower, exactly what you mentioned. And even today, if you become a Palit professor, you will be given a glass blower. That's the tradition. I mean, we didn't change it. So that is number one. Within 15 years of founding the physics department, 1915 it was founded. 1919, Saha came out with the ionization equation, which S.N. Bose told his students, friends, and colleagues. S.N. Bose is a lot of friends outside physics. because he used to play musical instruments, he used to mix with the poets. He had an intellectual, fraternity. So he said, look, Meghnad has measured the temperature of the star sitting at home. That is how people got to know. It was a very good advertisement. Students got interested. I mean, you see, in those days, the bright students used to be lawyer, barrister to earn more money. The reason that in Bengal, students, over the last several decades, students are getting interested to do basic science is because of the inspiration they got at that time. So, the outreach program, what we call today, was S.N. Bose's single line statement that Meghnad measured temperature of the star sitting at home. So that was 1919. In 1923, S.N. Bose wrote that famous letter to Einstein, probably the most famous letter that one scientist wrote to another scientist, which had an impact, such an impact that even today, we have only even tomorrow, the same story will remain that only two types of particles, the bosons and the other is the fermions, right? Half of the world's particles are now named after him. Subsequently, probably at that time, Bose didn't have, people say, much idea about the consequences, but that is a natural thing. Some of the geniuses do not understand immediately what are the consequences of their work. Like Dirac equation, the beauty of the Dirac equation was not conceived the same day that Dirac wrote that equation. He didn't understand it. So that was 1923. In 1928 to 29, Raman did that famous experiment. Of course, his associate was K.S. Krishnan, who helped him with the instrumentation and in many other things in Kolkata, which of course got Nobel Prize, So within 15 years of founding a department, except Bose was in Dhaka at that time, but he had a close connection with Saha in Kolkata. There are three epoch-making discoveries. If you look at the comparison with the Western world, only in Western Europe, you might find an example at that time, not even in US, forget about in Asia. So when they started doing their research, Saha was more interested in the use of nuclear energy for the betterment of life of common people, because he felt how the people in British India were suffering from various things, the poverty and many other things like superstition, like his commitment to the River Valley Project case, DVC. He gave all his time at that time to the, the formulation of the DVC project in the model of the Tennessee River Valley Project. In 1938, when Hahn and Strassman, found that, with slow neutron, if you bombard uranium, nucleus, dismantles, fragments, this nuclear fission. Saha realized it. Saha realized it immediately because he was visiting Europe in that summer. And coming back to Kolkata, I was told by a student of Saha, well, I'm quite old. And when I was young, I was in my master's, I met an old person who happened to be a student of Saha. We met in a reunion of the Calcutta University. He said that Saha came from the dockyard, and in those days used to travel by ship, straight to the physics department and shared his excitement about the discovery of nuclear fission. So, and in that year, 1938 or 39, in the MSc final exam, he said questions on nuclear physics. He started teaching and he did that. So the way things evolved is very hard to imagine, today. How contemporary, they were working on the state of the art thing, and they're trying to disseminate with the students the state of the art subject that was coming up. Parallelly, when Homi Bhabha was stranded in India because of the war, well, he thought of expanding the domain of nuclear physics in India from a different direction, that to make India self-reliant on nuclear power, nuclear energy, and the peaceful use of, whatever nuclear physics can give. Saha was working on the complementary aspects of training students in Allahabad and then even in Kolkata. Then after the independence, well, by that time it was quite known that independence was about to come. I mean, Bhabha started BARC and TIFR more or less at the same time. That what Dr. Kakotkar mentioned very emphatically, why he did not start a big BRC or a big TIFR with limited resources, because he felt that the two different types of institutes would fit the whole agenda. That basic science will happen in one type of place, and the application from mission-oriented laboratory-based science will happen in some other kind of place. Okay, so we are of the former type, that a basic science institutes with a specific need, laboratory-based science, that is different from the university mode of science. Okay. Now, subsequently, these two, world-renowned scientists, together with their colleagues who are also world-renowned, like, Bhatnagar and other people, they invited many stalwarts like Professor Niels Bohr that he mentioned, he visited in 1960. I was told by another professor who taught me in my BSc that Niels Bohr attended a Saraswati Puja in near Bose Institute. Okay, at that time. So he visited Calcutta at that time, and because both Bose and Saha was already dead. Saha died in 1956, but SN Bose was there at that time. And that was Bose Institute by the name of so J.C. Bose, and D.M. Bose, his nephew, who was a very well-known cosmic ray physicist, was the director of Bose Institute at that time. So we have a rich history. Before Saha expired, he wanted to have a cyclotron in Calcutta, and with the generous fund from Sir Dorabji Tata Trust, he could get the parts from different places, and eventually the ship arrived late because of the war, but finally he could get it done. I mean, that was assembled in Kolkata, and that is still lying somewhere in the Calcutta University. We should somehow, Amit, if you are listening, we should somehow try to, get it in our archive here. I mean, archive means, where we keep our stuff. I mean, here, the old antique. Saha handpicked N.N. Dasgupta, who was trained in UK, and he built the first electron microscope, the first in Asia, in the Institute of Physics, which was an offshoot of Calcutta University at that time. And that electron microscope is just, you can see it just outside this room here. I mean, that was the first electron. So we have several examples of, for the first time quotation, and we have a rich history. And now, it is our responsibility to continue this, but today's world is very different, very difficult to go alone. We have to join hands, join our forces, and only then we can make an impact in the international domain. Our competition is not with, it's not that a scientist should compete with other aided institutes and vice versa. Together we should compete with the best in the world, and that is how we should prosper. Our students should get the best possible postdocs, and eventually they should come. I hope that they would come back to India and serve the nation. So that's all I can say at this point. I mean, I assure you that you will be well taken care of by us, by our colleagues. And if you have any problem, you contact Satyajit. He has raised his hand. I was waiting for him to raise his hand. And let us look forward to the next day, till tomorrow. So the 2 days of excitement that we share on each other. Thank you very much. Thank you.
So thank you, Director, for your nice speech and encouragement. So now it's time to give the lecture of our chief guest. And before that, so by this to dismantle this. Sorry. So we can go down and we have to reorganize the stage, and during that time, may I request Professor Naik to introduce our speaker. Please. Okay. So you are after that we.
Okay, in the meantime, it is my pleasure to project on the screen. Yeah. Good morning, everybody. It is my pleasure now to give a brief biodata of our chief guest of the day, Professor Jitender Bir Yakmi, better known to us as Professor Yakmi, has spent a research career of 45 years at Bhabha Atomic Research Center before his retirement in 2010. Before his retirement, he was Associate Director Physics Group and Head Technical Physics and Prototype Engineering Division. 2012 to 2016, he served as DIE Rajaramanna Fellow at Homi National Institute and also worked as Chairman, Atomic Energy Education Society, Mumbai during 2012 to 2015. Some of his notable contributions to physics include a USA and European patent on artificial heart. He is credited with establishing a program on the use of molecular materials for fabrication of molecular magnets, sensors, and organic electronic devices. He has more than 450 publications with 65 review articles to his credit, with a H index of 52. He has edited or written some 10 books. More recently, he has published a book on superconducting materials and their applications on interdisciplinary approach by IOP Publishing UK. He is a fellow of National Academy of Science and elected member of Asia Pacific Academy of Materials. He is a winner of triennial MRS ICSC Superconducting and Material Science Award by MRSI and a Distinguished Alumni Award by Kurukshetra University and the IIS gold medal by University of Tokyo. I just got all these information from internet. I hope I have been able to do it properly. Thank you, sir. Now you can present it.
Good morning, all the participants and senior colleagues, including Director Science, Vice Chancellor HBNI. Hello. No, I'll do that. Okay. Oh, otherwise the camera will not record what you want. Okay. Here, thank you. Now camera is seeing me? Okay. These cameras are quite crooked things, no? See, I was planning to speak something which I had written down, but during the previous two talks, Dr. Vasudeva Rao and Gautam, they triggered me to say some things because that is the spirit of such meetings, that ideas come from other ideas and you expand. Both of them talked of glass blowing, both of them. I remember as a skill in BRC, we learned many things. Actually, you learn more things when you have a low period in your career. Because when it is high period, you go on doing what you are doing. Why should you learn? Why should you learn, some lowly things, as you say? So I learned glass blowing. So once I was in Orsay, Laboratoire de Physique des Solides in Paris. So I said, I want to seal some sample. Where is your glass blowing? They said, you can't touch that because it's a specialized thing. I said, don't tell me. So show me where it is. The glass blowing equipment is same whether it is India or Paris or whatever. You have an oxygen cylinder, you have a gas of like we call Barshane or whatever, and you have a torch. And I was quite free. I can do Pyrex. And those who know glass blowing, I think Vasudeva Rao will know, sealing quartz is a big deal because quartz is high melting. I can seal 1-inch dia quartz tube into 0 and seal up your sample, which is a very, very tough thing. But these things actually help you in your career. I'll tell you how. A time came when we were collaborating with TFR on uranium-based heavy fermion materials. This was before high TC superconductivity came. Now, TFR cannot arc melt uranium, not allowed. Uranium can be handled only in BRC. So they will contact us. They either used to go to Atomic Fuels Division where they have arc melting heat. But Atomic Fuels Division is used to handling 0.5 kilogram or 200 gram or those kinds of things. Whereas here you want 0.5 gram or something. So we had made our own arc melting apparatus in what you call modular lab. In chemistry division where I was working, we had everything. So I have melted many compounds in either arc melting, including some dangerous ones, which I realized only later I could have died doing, not taking precautions. I give you the example. Physicists know uranium cadmium 11 is a famous compound. Cadmium is very low melting. You show it in flame and it goes into fumes and is very dangerous. But success of glass blowing was, I took uranium, I took gallium. Gallium is liquid at room temperature. So I ran my glass blowing torch, vacuum is running. I just showed a flame, compound is made. you need skills. That's what was said. If you have additional skills, you score over others. That is the idea. Second thing which triggered me was, as Professor Vasudeva Rao was saying, sometimes you are doing some other things. Like he said, Niels Bohr having an assistant who was a master technician but won't let him do things and all. See, Camerling Onis, who discovered superconductivity, got a Nobel Prize and all. Those days, there are no institutional funding or something like that. He was a rich man having his own lab. He had an idea how to compress gases. So he had a very faithful technician who would work all the time. This man is like a lord. You have seen his pictures and all, Camerling Onis. So in his lab, different gases, inert gases are being liquefied. So helium happened to be go into liquid form at 4.2 degree K, and that is where superconductivity was observed. So superconductivity observation was on the side. I mean, he didn't plan for that really. So, but imagine if he was not interested in liquefaction of gases, he wouldn't have got that thing. Then even learning to speak in another language, like when I come to Calcutta, I often say, Kibolchi, all those things. See, you become comfortable if you learn another language which is useful. My friend, Professor Osawa, who discovered, he was a computational chemist, so the theoreticians here know, he discovered the structure of fullerene in 1970. He didn't get the Nobel Prize because he published in a local Japanese journal, which nobody reads outside Japan. All the people, Crotto and his colleagues, Smalley, those who got the Nobel Prize, they recognized that this man had done earlier. In the meantime, they discovered after their Nobel Prize was announced. So imagine Osawa should have learned to publish his results in English journals. That is also a skill, no? To publish your journals where it is read mostly by others. Somebody mentioned, my friend mentioned that I have published a book last year. I'm writing another book. Again, this concerns the total event scenario here. The book is about, again, Institute of Physics Publishing, Bristol, UK, that they are my publishers. A PhD student, what he or she undergoes those 4 or 5 years, only God knows. Because the professors who are sitting in their high-flown rooms, they don't know what goes wrong and right with their student and his groups and how they talk. So how to succeed and sail through that period in a most constructive manner. That is the book. And how to plan for your career. People do PhD, then they are postdoc fellows even in Europe for 5 years, 6 years, 7, 8 years, not getting a real job which they want. So I think such books have relevance if we want to steer the careers of students who come to us. He was saying we must, attract good students multi-institutionally. HBNI is a back of it, of course. But then we have to also sort of standardize the training, treatment, as well as acceptance of junior colleagues who are your students. Coming to the main theme of the talk, under HBNI, it's a very nice combination of a name which has been given, IMCMP. Oh, very good. We discussed condensed matter physics activity from 10 DA units. 11th, you can count HBNI also, except, of course, Tata Memorial Center is not there. I would say it's like a festival. We are celebrating condensed matter physics here today. Maybe for the first time in a big coherent manner, it is being celebrated what we do in all 11 units and even outside 11 units in DA. So it is a time to rejoice. We are not going to give, sort of lecturing each other and all. We want to learn and benefit from each other. If I were to mention just one topmost activity of each of these 10 institutions, it will become, it was mentioned in an indirect manner, it will become a compendium of very high value condensed matter physics research. I'll give you examples. Because different people are sitting in their own institutions, not either bothered about what others are doing, or maybe not getting a chance to know and interact with them. I give just one activity each, BRC, neutron scattering, high pressure physics. I won't even mention other things like superconductivity. This itself is so powerful and all pervading as far as as condensed matter physics is concerned. RRCAT, synchrotron radiation lasers, IGCAR, MEG and squid sensors. I won't choose others. I am talking about condensed matter physics, which is #1 in India. If you want to mention that, I go everywhere and sell their MEG idea to different people, not only within India, also abroad, that here we can make ourselves. VCC, accelerators, Vikas Dada, he writes articles, City of Cyclotrons, Calcutta. So, it is known for that. Already he mentioned how the first ever accelerator was to have been assembled earlier, but it took time. Saha Institute, it is called nuclear physics, but how many things it does? Biophysics. It is the backbone of, that particular topic. If you remove Saha Institute from the scene, the country will lose a lot of biophysics. I want to say that. Molecular biology. I'm intentionally not mentioning high energy physics, string theory, this, that. Those things are there. IPR, nicer, turning the education around. New courses, combined courses, BSc plus MSc. It is being recognized, including our Bombay University Center with BRC and all. Then go to IOP. IOP Bhubaneswar is experimental as well as theoretical. Mathematics, theoretical physics, but also, somebody mentioned electron microscope. My friend Bhupinder used to be there for years together. I have seen these things. Then, of course, math science. He mentioned a lot about how math science was started. Dr. Ramana used to bring the first director of math science to BRC for giving lecture. That fellow is a very powerful speaker. He will speak on causality. We were very young. We were wondering what is causality. These are see, if you are a good speaker, you really teach well and people pick up. And of course, my friend Bhaskaran, for the last 30 years, I have been going and meeting him in Math Science Chennai. And everybody knows his career, working with Anderson and so many. HRI, last. I would say I'll give them just one thing. They nurtured our Ashok Singh. That itself is enough for me. Because he got Yuri Milner Prize, which is 3 times the value of Nobel Prize. He got it working in HRI in Allahabad. The new name, whatever it is. So talking of these things, now we are going to take stock here. Facilities developed in DAE sometimes have been multidisciplinary in nature automatically. Not that you planned it that way. For example, neutron scattering. A physicist like Dr. Chidambaram, he does it for his own interest. But the protein crystallographer comes, he's a biologist. He also uses the same equipment, but for him things are different. So this is multidisciplinary. Again, MEG, health sector, medical doctors, but then physicists want to know how the magnetic field is, lines of force are, traversing and going into your mind, going into your body and all that. To tell you, till 1970s, even end of 70s, condensed matter physics in BRC, the people who worked with solid state physics those days, they never made any samples on their own. They would either buy a crystal or walk into somebody's room, like my predecessor, senior, Dr. A.J. Singh, Amarjit Singh. Can you make this sample for me? He was broad-minded. He'll make and give it to them without any credit. But then came high TC superconductivity. Now this was a free for all. Everybody has to make his own samples. Physicists learned how to make samples. chemists learned how to handle cryo equipment. They were not doing that earlier. Imagine if Professor C.N. Rao was handling cryo in his earlier life, he would have discovered ITC superconductivity 15 years before it was actually done. But he never went below 70K also. That is the problem. So, when I came to technical physics division, I was already maybe 55 or so. Dr. Kakodkar said, you should come that side. I came. So we transformed technical physics and prototype engineering division because they were making sensors. Even now they were making a lot of equipment, mass spectrometers. We are known to be making instrument making division. But then it was all handling only elemental materials or oxide materials. I brought in organics because I came from chemistry side. It took some time, but today if you listen to anybody from TPD or BRC, he will be talking very freely about phthalocyanine, porphyrins, and things, such molecules, which physicists, they get scared. So it is this kind of scare which we have to remove from the minds of the people if we have to. Can I operate this myself? Or somebody will do? It's full presentation. Yeah, presentation. Share. आएगा आ गया no first last
Share it. Share it. Can you show me? IT%.
share तो हो गया ना मेरी last slide
But you search from online.
Some people cannot see.
yeah. That is the difference. Doesn't take.
Yeah, now it is. Now you click on this top one. No, this one. This one.
Make it full.
Slide one. Give it to me. Give it to me.
Phone come. No?
Yeah, you can do this.
I can start. So you've seen the title. I have been speaking about it. Yeah, okay. See, let me give you an example. Just chatting with you, nothing complicated. The 2009 Nobel Prize winner, Indian, Venkatraman Ramakrishnan, Venki, he's called. He was educated in Baroda. He's an Indian product, BSc Physics from Baroda. Then he went and did his PhD in physics, Ohio State University. Then biology, he was interested. He was a theoretician initially. Then biology from San Diego. Worked 12 years in BNL, Brookhaven National Lab. Currently, he is working in molecular biology lab at Cambridge, where he got the Nobel Prize. So look, biology, physics, chemistry, everything is combined in his career. That is multidisciplinarity. And what is the citation of his Nobel Prize? It is said the protein producing ribosomes which transform DNA into living matter. What is this living matter? Living matter is also called active matter or self-propelled matter. Sometimes I give lectures on that. Living matter is soft matter. We are actually talking about nature, the way nature does it. The nature only made our skin and tissues and all that. That's what he got his Nobel Prize on. So, if soft living matter lies at the multidisciplinary interface, a confluence of physics, chemistry, biology, engineering, and maybe some other disciplines together. And nature likes to work with polymers, colloids, surfactants. Also, all ambient condition, ambient pH, ambient pressure, ambient temperature. Nature is not like our steel making, we humans make steel in the most extravagant manner, the way we waste our energy in making that. Nature works at room temperature. So what is this soft matter I talk? Soft matter is not a gas, not a simple liquid, not a hard solid. Think of chocolate. But you touch it, it touches your fingers because it becomes liquid there. Now this, I already told about colloids, surfactants, polymers. There are a lot of examples. Colloids are a little alien to physicists more. So their colloid examples of colloids are ink, milk, paint, blood, ice cream. Soft matter, I said, is synthesized in repetition under ambient condition using non-covalent interactions. If you go to a chemistry lab and see them synthesize new compounds, most of the times they are working with covalent forces. Covalent forces are one order of magnitude larger than non-covalent. Non-covalent means van der Waals forces, hydrogen bonding, and amphiphilicity. These are the kind of bonding. So, another example of a Nobel laureate, Dijon. He got the Nobel Prize on soft matter, but it was not written soft matter. It was written complex matter in his Nobel citation. He didn't like it. He was also a true example of a multidisciplinary scientist. How? Like us, most of us physicists, he was working on magnetism, neutron scattering, superconductors at Saclay, that is the Atomic Energy Department of France, or Orsay in France, both of them. But before that, we have all read Solid State Physics by Charles Kittle book. He was a PDF postdoc fellow with Kittle. Eventually got attracted to liquid crystals, polymers, and these soft matter business. So he felt the young kids in schools must be brought into the realm of multidisciplinary fields. Mind it, he must have gone to nearly each and every school of France before he died. For so many years, he will go and give lectures, and a senior French professor will accompany him, take notes what he is speaking. There is no standard figures or so. Everything on blackboard, something is drawn, so he will take that. Finally, a book came out, Soft Matter, which has the same hand-drawn figures, the way they were copied. I once gave that book to Dr. Srikumar Banerjee because he appreciated that. So, Condensed, we also thought we should catch them young, like Dijon in France was trying to catch them young at school level. I thought in India we had to catch them young, the solid state physics people, condensed matter physics, young people, that they are conversant with chemistry and biology. So we ran a 2-week workshop in 2008. It was called Condensed Matter Interface with Chemistry and Biology. We said everything free. We will choose young people. Either you just finished your PhD or are about to submit. That about 27, 28 age group or so. About 40 people were selected from all over India. They were brought to Homi Bhabha Center for Science Education at the periphery of Anushakti Nagar. So what did we choose to do? I brought 5 foreign speakers and 5 Indian speakers. Who are those speakers? And I told them, please choose your own theme and you must give 4 lectures each. You can't say, I'm a very busy man, I'll give 1 lecture and go. Sorry, no. The names are given here. It is not important who gave, but look at organic electronics, molecular metals, and so on. This is being taught to fresh PhDs of solid state physics. They're young. So this has to be done. And who are the Indians? Ram Gopal Rao, who is now the IIT director Delhi. Earlier he was in IIT Bombay at that time. K. Ganesh, director of IISER Pune, the first IISER. He came and gave lectures, 4 lectures on DNA. He must give also 4. Don't run away to your Pune saying I'm busy. No. So they did all that. And including our Yusuf, he will meet him tomorrow. He was also giving it. I thought I have still not done enough. He was retiring in September 2010 from BRC, as it was mentioned. I thought physicists, engineers, and chemists generally shirk from biology. They really are scared of biology. Vice versa, biology and physics, physics and biology, engineers definitely very, very scared. So I must give like a course of lectures. I gave under the title Biology for the Chemists, Physicists and Engineers. I gave 4 lectures, and the last 4th lecture was on the day I retired, 30th September. So I maintained what I promised to myself. And I think these things do have an effect. You make them familiar with the terminology and what is the concepts. So somebody will ask me, you are talking about multidisciplinarity, why should we go for it? And what are the future interests or lucrative topics in this? The wheel-free motion. Wheel-free motion. You know, we normally travel by car. I think humans are obsessed with the wheel. We even say you are reinventing the wheel. You know, this is commonly told in arguments. Look at nature. Do you find wheel anywhere? No. Nature does not waste energy. It does not pollute the environment. When I travel when I'm driving my own car, only not more than 2% petrol or diesel carries me. The rest of it goes in pushing that 800 steel thing around me, which is the car, or braking, friction, and then internal combustion engines inefficiency, and so on, and changing the gears. I mean, what a wasteful way of living. Look at that. So we have to find methodologies so that we also curb pollution. Whoever does this will be a king in science. You know, materiomics. Anything omics means biology. Your genome to gene to genomics, protein to proteomics, and so on. So material to materiomics. Computers mean you say connectochrome. Okay. So materials which are needed for biology and interface between materials and biology is a big thing. It is already going on, but I think we have to work more. Living matter, I said that already. It was in the citation of Venkataraman Ramakrishnan. Homeostasis. What is homeostasis? You know, we are able to live. We emit anything living, not necessarily humans, because our pH and body temperature and blood pressure and glucose, they are maintained back and forth by our bodies or nature. They go plus minus, but they are brought around that. Why? How? Because it is called mechano to chemo to mechanical conversion of energies, and nature can do it back and forth. So it has a feedback mechanism. It will say your pH is going up, bring it down. Like we have a proportional temperature control or something like that on that concept. Humans cannot do it. I'll come back to it later. Why, how it can be done and why people should benefit from it. Flying like birds, drones. You know, your prime minister these days talking of drones, because drones can be used in defense. We have so much of interaction with Israel, which is maybe the topmost country working on drones these days. And drones for agriculture, and drones for so many things, including for traffic congestion. Drone can manage so many things. But drones have to learn from birds, even the best of the planes, which are being designed even today, whether it's for defense or for passengers. They learn from birds how birds are flying. And lastly, gut microbe. See, when I'm sitting here, I have maybe 1 trillion microbes in my gut, which are good microbes and bad microbes. And recently we heard, this pandemic, viruses, they are also there. And then you have bacteria, then you have archaea, all those are there. But then they influence your health. This virus came and it started just at the tip of your gut. Even before it goes down, it started influencing your health. So bacteria, archaea, fungi, and virus in our gut can lead to diseases, and also they keep your health good. So more and more research is going in this direction. Now one has to learn where one is placed and what one should do in a given institute. As we say, physicists are more, astrophysicists and others, they are more worried about looking at a, asteroid or things like that. You have 100 billion galaxies in the universe, so they have a lot of work to do, these astro guys. But there are also 100 billion neurons in my brain. So there is a lot of work to do. Already I mentioned MEG technique, handling, the intricacies of the brain, what is going on in the neurons. Similarly, I have 1 trillion microbes in my body. I already mentioned about microbiome. Actually, I have 100 trillion cells, all kinds of cells in my body. Is it not complex enough to start? We have only started it yet. As वो हिंदी का गाना है ना, अभी तो पार्टी शुरू हुई है. So we have to go like that. But the young ones are asking, where are the jobs? These days they do the same computer science, same IT. Earlier they were being welcomed by open arms. Now many colleges themselves are closing these. There's a glut of them, okay. Also because you have now emerging exponential technology, artificial intelligence and so many of those things. They are wiping away the jobs. I mean, they are just taking over. So those kind of single subject cocoon, I call, that will no longer will be needed after some time. If you have done just IT, then sit at home. If you have done IT and biology, please come. That will be kind of. So we need to exit this single subject cocoon. Now you will say you are asking me to do 2 different degrees in 2 different subjects. Yes, why not? Because we people have been doing all these things earlier. Now do it in a formal manner. So I know my friend, a Bengali, his son has just done from Philadelphia 2 weeks ago a degree in cognitive science and physics combined. So he'll get a job because you can't easily replace this combination. If it is non-overlapping 2 topics, jobs will be guaranteed. 2, 3, 4, whatever. Your richest guy who has all the money in the world, Elon Musk, he did his graduation in physics and a graduation in economics. Physics and economics don't mix so well, but he did it. And I'll just give you one example. Why we have to do multidisciplinary. There are job sectors. Like environment is a sector of jobs. Medicine is a job sector. You combine the two. There may be a requirement for environmental epidemiologist. Who will get the job? Who has also done 2 things, biology and as well as computer science and engineering. He will get the job. Not just a biology fellow or just a computer science fellow. This is, I already talked of it enough, Kalpakam, MEG. I think I give great credit to my friend, Professor T.S. Radhakrishnan, who spent a lifetime building it. So people, those who have not done, at least DA people, they must go and see. Ideas will come to you, what I can do. This is the one, I think I was here, yes. So what was mentioned, our, patent business. So am I delaying a lot? I should cut it. Okay, this is that international patent with I and Yusuf and a medical doctor, a cardiothoracic surgeon. He in Chennai we took, but the details you can ask Yusuf. I don't want to spend too much time on that. It is a patent for so-called artificial heart. That nature does not use wheels, I already told you. See, an ant can carry hundreds of times of its own weight comfortably. Nature's marvel. So, can you make artificial limbs? Can you make artificial, joints? We tried. This is from polypyrrole. We made an artificial muscle. It can be done, but there are a lot of studies all over the world. These are, I mentioned the subjects which are common to 2 or 3 different subjects. Nature does not use pigments. You see all those beautiful colors. Nature has not used the Asian paints and things like that. No, it is the way at a nano level, the platelets are organized. You get green color, you get blue color, you can, even those beauty companies, they are lipstick making people and all. They are trying to worry about how to use nanotechnology, copy nature. So nature has been making its own materials, non-polluting, for 3.8 billion years ago. Imagine this E. coli molecule, E. coli cell, single cell. It has factories inside. It is a few microns, but you have sensors, memory, actuators, flagellus. Nature makes single crystals. When we grow single crystal, we want monodisperse, same size. We also want single domain. Nature does it. In a bacteria, it does like a compass. They are arranged in like a dipole. And so now this bacteria knows, like a compass, it can either go on swimming to the north or to the south. And we do it in lab. We try to that using a Langmuir-Blazet technique, which is a air-water interface. It is a water trough on which we grew crystals, and then we grew many layers. And can we use those layers or samples, crystals? Yes, we use it for potassium ion sensors in BRC. Why you want to use for potassium ion? Our body cells, basic unit of life is the cell. A cell was discovered by a mechanical engineer, Robert Hooks. You call him physicist if you want. So, basic unit of life is cell. Each cell is enclosed by a wall. We call it plasma membrane. But traffic is controlled going in and going out. Anything cannot go the way you may prefer. Particularly the polar ions, potassium and sodium, they cannot do the way they want. They are sort of blocked. So if your potassium ion concentration inside or outside is changing, your health may suffer. So we made a sensor for that, making 19 layers of these single crystals, which were grown in a Langmuir-Blazet trough, which is a water trough on the surface of the water, and harvested, and then you do what is called cyclic voltammetry and show it that it is a linear relationship between the concentration of potassium. Brownian motion, all of it. This deals with colloids. Colloids lie between suspension and solution. And I gave you examples. A red blood cell, if you put it under a phase contrast microscope, it is flickering all the time on its own. Why it is doing so? One has to study. It shows the colloidal size possibly offers motility, means movement, self-propulsion. Then possibly the smallest life form which utilizes nucleic acid may be colloidal. So when you are bringing so many disciplines, you want to also study, does it emerge? And can we do something about it in a positive manner in the lab, not for negative ideas? Of sensors, I was talking in technical physics division BRC. We have been making sensors for so many gases. So these are called chemi-resistive sensors. We use, say, for hydrogen sulfide gas, for ammonia, for chlorine, and so many gases. So I brought organic materials to this field, and for example, we have made a sensor. This is the equivalent circuit in the middle. you must have high sensitivity, small response time, small recovery time, selectivity. It's only that gas it should sense, nothing else. So those are the constraints. Now I'll tell you multidisciplinarity, what we did. We had an MBE machine, which is basically a physics-based equipment, very expensive. It is generally used for silicon, germanium, very pure ones, make layers, molecular beam. We had a machine which had lived its life for 15 years. So we converted it into organic materials. Once you put organics, your MB is finished. You can't go back to do silicon germanium because you can't degas it anymore. Organics are clumsy. But then we learned to make very high quality organic films, in this case for cobalt thiocyanins. When we make those films, they are very high quality, and we show we can make sensors which can sense 5 parts per billion of chlorine because the film quality is good. Now we have brought physics and chemistry and organic chemistry and sensors together in one platform, and we learned how to make very good films. We learned how to make very good new magnetic materials. It was mentioned molecular magnets. I am not telling you all that. You know, if you read about magnetism, you have single molecule magnets, which is a field in itself. You also have single chain magnets. Single chain means ferrimagnetic chains, large spin, small spin, things like that. So we made this. I have a colleague, his name is here, Sandeep Naik, Bengali. He was he was associate director of biology group before he retired recently. So he went to Technical University Darmstadt in Germany twice for 6 months each, just to grow this crystal, because they had the facilities. So this is a single chain magnet, single crystal. You want to learn more physics out of it about magnetism, because you have a handle on new molecular materials which are single chain magnet. Then we had switching, again molecular magnet. Part of this work belongs to Yusuf, part to others. I won't go into details, but we made switches out of that. Switches are the basis of electronics. If you have a switch, you can do so many things. Purely Yusuf's lab. We made magnetocaloric effect in low magnetic fields. You know, the beauty of these molecular magnets here is copper, manganese, iron, hexacyanate. These are the clones of what is called Prussian blue. Prussian blue is a blue color pigment known for 200 years. In Hindi, we call it Neela Thotha. You know, India we call that. So these are all compounds related to that, but there is a lot of physics waiting there. These are molecular, inorganic molecular magnets. And look here, Yusuf could do normal MCE means magnetocaloric effect. Above 13K it is positive, below 13K is negative. So you can make even a constant temperature bath with it, but the temperature is too low. But look at all the ideas which are available. Can we regenerate human limb? You know, there are vertebrates which are going to sea and the land together. They can do. Salamander is like a fish animal. You cut its limb or it gets cut, in 40 days flat, it can regrow its own limb. Can we do that? It's not so easy. When I'm sitting here, my bones are being replaced all the time, but at a very slow rate, 40 microns per day, which is not useful. So you want to try and do new things. I said drones, birds, whether it's Boeing or, you know, Airbus or military planes, they all study how birds are designed by nature. And see, flying is the only thing which we humans can't do. We can do various other things. We have a great desire to fly, but when I was talking about homeostatic abilities, I told you temperature, blood pressure, pH, sugar levels. What we make is unidirectional. Either I can convert chemical to mechanical energy or mechanical to chemical. But more recently, we are getting into these things. It is learning how to do, you know, homeostatic materials. That's a matter of detail. Again, it connects to living matter. Then I tell you some of my transparencies are a little matter. I give you two examples where human health related materials have been studied either at a BRC or an IIT in collaboration, which are problems crying for, to be tackled for human health. Number one, how do arteries, blockages formed in our arteries? Your blood pressure goes up, you get heart attack, you may die. This must be studied. So with Sri Chitra Tirunal Institute for Medical Science Technology, Trivandrum, we did this in BRC because we had the facilities. We had AFM, we had Langmuir-Blodgett technique, and they have all the wherewithal. We took the same mixture of glycolipid, phospholipid, and cholesterol, which is there in the real system, and tried to deposit films on polycarbonate. Polycarbonate is the surface which comes closest to the inner surface of the arteries. And we studied by contact angle measurements, can you chip off? So does it stick or not stick? How much does it stick? So these are, and then there is a medical doctor in IIT Bombay, a lady, Rinti Banerjee. She did her MD for the last 15, 20 years. She's at senior professor now. She has been working on what is called respiratory distress syndrome in infants more, very rarely in adults. So, our lungs are not bags. If you look at that, oxygen is exchanged. Each lung is having 1.5 billion alveoli. Alveoli means small bubbles. The surface of the bubble, you exchange gas, means oxygen is given to blood across that thin film. If that thin film gets punctured, the child can die. So that's what happens. We need a replacement of that film. Lung surfactant. Lung surfactant is surfactant as well as proteins. So this is an important topic to be studied, but there is physics involved, chemistry involved, biomedical technology involved. So I'm coming to the end of my talk. Sector calls for multidisciplinarity. We are living older and older. 76, thinking that I am young. But age brings you a lot of new diseases, particularly central nervous system. Related to your central nervous, CNS means brain and spine together, your neurons. How do they act? Why do they make us, we became slaves to that we cannot do what we were earlier doing. But problem is there are so many diseases, Parkinson's, epilepsy and all, which are related to that. There are a number of pharmaceutical institutes in India, including like in Punjab University, Chandigarh, there is an institute of pharmaceuticals, almost best in India, who are trying to see why drugs cannot be given to the brain. Brain is enclosed in what is called a blood-brain barrier. Neurons are going across, but you can't push any drug you like. So how to do that? You may make a drug, but it doesn't reach brain. What to do? BRC innovation, you must have read about it. BRC made an ECG very cheap. This is all again technologies, engineers, physicists, chemists, medical doctors coming together. In a single charge, 3G technology will do. Go to a rural area, you can record 300 ECGs. With your mobile phone, you can transfer the ECG data to the best cardiologist so that at least you can get the health of the patient. My last thing, that doesn't matter. That was about the book, which I say, can I somehow show my last slide, not for the book? Because it has an idea, which, people do high energy physics. Then people also do condensed matter physics. There is a recent paper 2 weeks ago in Nature. Don't worry about my book, which was published last year. Matter. You had a Higgs boson, so we say we are happy with standard model, okay. But Higgs boson doesn't explain dark matter. It needs further symmetry breaking and an axial Higgs mode, which has been recently observed for this compound, rare earth tellurium-3, either lanthanum or gadolinium. Why they are interesting? They are charge density wave compounds. You know, Pearl's distortion, you read about it in physics literature. And the temperatures are very high, 380 Kelvin, 600 Kelvin. So now condensed matter physics people have to study like the way we used to study superconductivity. Superconductivity, spin density wave, charge density wave, they are all ground states of matter. And they compete sometimes for the same area at the Fermi surface. So in order to study competition between these ground states, you have to study all this. I think this is a gold mine waiting here, RTE3 for condensed matter physics. Thank you.
Okay, now, it is my honor and privilege to give a vote of seat. So now it is my honor and privilege to give a vote of thanks on behalf of HBNI to all those who helped making this meeting a reality. First and foremost, we would like to thank Director SNP, Professor Gautam Bhattacharya, to readily propose to host the first subject-wise interaction meeting on condensed matter physics here. Thank you, sir. We would thank Professor J.V. Yakhni, chief guest of the day, taking time out to be present with us and delivering an inspiring talk on how to work on interface of biology, chemistry, and physics for the societal benefit. Thank you, sir. We would like to thank all the faculty of various CI, OCC, who are present physically and others connected online with us to present their institute activities on condensed matter physics. We thank all the PhD students who will be presenting their work, some orally and some through poster form. Our special thanks are due to Professor P.R. Basudeva Rao, Vice Chancellor SBNI, for proposing the concept of holding interaction meeting among faculty of various CI to enhance interaction and scientific collaboration among them. Thank you, sir. Last but not the least, we would like all the people at SNP and HBNI Mumbai for providing technical support to stream live the proceeding of the meeting. Thank you all. So it was for half an hour, but okay. We'll have a 15 minutes break now for tea. After that, session one will start. So those who are in online, please note it.
Sir, please stop sharing.
Yeah, no, you see, we have already stopped here, no? Make it video like this.
টাকা আরেকটা টাকা থেকে 10,000 দিয়ে দে তুই ঝপরে গিয়ে উঠে দেখো আমার তুমি তার আসো তাও তাও তো নাকি কি ঠিক তো ওই ইলেকশনের সামনে হ্যাঁ ওইটা থাকে থাকে কোনটা ওটা তারপরে আপনি গঙ্গা কাজে আছে ভাই সকালের মধ্যে 5 চেয়ার টেবিল ছড়ানো যায়
ये लैपटॉप यहाँ पे शिफ्ट करेंगे या वहीं रखेंगे? लैपटॉप यहाँ पे शिफ्ट करेंगे या यहाँ वहीं रखेंगे? अच्छा, शेयर वेबएक्स नहीं शेयर किया मैंने। Oh, just you. क्या कर रहा है क्या? हाँ, नहीं कर रहा है। आपने तो बोल रहा लैपटॉप करो ना। हाँ, ये लैपटॉप ऊपर ले जाके बेटर एक्चुअली। तो शेयर कर दो। वो पहले वो बेक्स चाहिए। Yes. Yes. बोला ना रोल मत हो गया हो गया हो गया हो गया ना। पॉइंटर कहाँ है? पॉइंटर तो ये मैं बोला था बैठे में जरूरत नहीं, यहीं खड़ा रहना पड़ेगा ना। ठीक ठीक। माइक चाहिए क्या? नहीं जरूरत क्यों, मेरे को यहीं खड़ा रहना पड़ेगा ना। आई डोंट हैव टू रोम इट। अच्छा अच्छा, हाँ दैट इज वो ठीक बोल रहे हैं। सुविधा रहेगा ना। हाँ
There's no need for any introduction, anything.
Should I start? Yeah. Okay, good afternoon, everybody. So in this short presentation,
I'll give you a reminder after 25 minutes.
it's a half an hour, 20 minutes.
Actually, after 15.
Yeah. So good afternoon, everybody. So in this short talk, I will discuss how we can use neutron scattering for the condensed matter research. So this is a typical which we do in a neutron scattering experiment. You have an incident beam of neutrons which falls on the sample. And suppose if there is no change in this energy of the neutron, then what you probe in this scattering experiment is a change in this wave vector. So you detect the neutron as a function of angle. So in the scattering experiment, what is involved with the wave vector transfer? And this wave vector transfer, which we call momentum transfer also, it is inversely proportional to this real space which you see. So Q and R are inverse to each other. And this is the cartoon of the thing which we see in the neutron scattering experiment. So here we see this elastic peaks, which gives the information about like long range kind of ordering, structural information. You can have in inelastic peaks, which gives the information about collective excitation in the system, like phonons and vibrations. And depending on this Q value, I have defined this presentation in the 4 part. So this first 3 part covers this elastic scattering, where there is no change in this energy of the neutron. And the last part covers about the dynamics. So first I will start from this crystal structure. So neutron in general with the material interacts with the neutron nucleus interaction. And other part by which the neutron can interact is this dipole-dipole interaction. As neutron do not interact with this charge clouds, so it can penetrate in the bulk of material and can give the information about from the bulk of this material. Now, this is the example from the single crystal study on this superprotonic conductors. So they are the material where there is a huge proton conductivity at high temperature, and this high protonic conductivity arises because of the fact that they have large number of symmetry allowed hydrogen positions than the number of hydrogen atom present, and due to which at high temperature there is a hydrogen band formation and deletion. To understand this phenomena, we have carried out single crystal neutron diffraction study. And please remember that neutron diffraction is the only technique by which one can get the information about the location of hydrogen and hence for hydrogen bonding. And in this study, what we have found is this single crystal, which is superprotonic conductor, it deteriorates with time due to the presence of moisture in the air. And this, due to deterioration, there is a asymmetric hydrogen bond changing between PO4 and SO4 ion. And after the deterioration, the crystal becomes stronger, and which results in the further deterioration of this material, and which also results in the unit cell shrinkage. So by carrying out the single crystal neutron diffraction experiment, where one tries to record this reflection in the 3-dimensional reciprocal space, we have received this information about the crystal structure of this material before and after the deterioration. Now moving ahead from this single crystal to the powder neutron diffraction, where one tried to project this 3-dimensional reciprocal space in the 1 dimension. So one record this intensity as a function of momentum transfer. Here is the example from this graphite, which is used as a reflector, and this graphite plug was removed from this Sidus reactor. And here what we found is that, as you know, when you put this radiation in the graphite, there is knocking out of these carbon atoms. And once you heat this graphite, there is an annihilation of the effects, and there is a release of huge amount of Wigner energy. And here we have carried out neutron diffraction experiment in the wide Q range to get this structural information, how these defects evolve. And here what I show is that neutron diffraction patterns for the sample with increasing the neutron fluence. So what we see here is that as the neutron fluence increases, this peak, which is 002 peaks, it moves towards the low Q value. It means there is a increase in the lattice parameter C, which has been shown here. Further, by carrying out this high Q experiment where you are only sensitive to the localized environment, we have found that there is an additional peak at 2.14 angstrom, and it arises due to this pentagon structure in this graphite blocks. And by carrying out this neutron diffraction and AB initio simulation, we have found out how this cooperative movement of this 2, 3, 4 coordinated structure happens in the graphite. Now moving to the magnetic material, as neutron has a magnetic moment, so it acts as a very small magnetometer and it can probe microscopically spin-spin correlation in the material. So I have divided this work in the 3 categories. First, I will discuss about this low dimensional and geometrically frustrated magnets. Then I will come to the magnets, which shows the negative magnetization. And at the end, I will discuss this energy material. To understand the magnetic phenomena, we use a couple of analytical tools like full proof refinement, RMC, mean field calculation, spin wave calculation. So here's the example from this frustrated magnets, which are like on this triangular lattice. So if you put these 3 spins on a triangle and consider this action interaction between the 2 spins is antiferromagnetic, then you know one cannot satisfy all the interactions simultaneously. And this results in the huge ground state degeneracy, and which results in the 0 point entropy. And once you have a degenerate ground state, as you know, if you apply any sort of small perturbation, then one has to do this degenerate state theory, and one can tune this ground state quite effectively. So here theory says if you have a spin 1/2 Kagome system on the Kagome lattice, then it should show a quantum spin liquid behavior, which we have investigated. Even we have tried to drop this Kagome lattice by anchoring them close to a graphene, and by which we have made this insulating sample to the semiconducting type, and we have seen a change in this Curie temperature also. So here I show this result from this spin 1/2 Kagome system. So there are Kagome layers which are separated well along the C-axis. So system effectively becomes a 2-dimension. Here the neutron diffraction study at 25K and 1.5K do not show any enhancement in this peak, as well as no additional peak, which rules out the possibility of long range order and suggests a ground state, which is something like spin liquid kind. We have also investigated this compound by carrying out specific heat measurement up to 80 millikelvin, which also do not show any signature of long range ordering, despite having this Curie-wise temperature of something like 10K. So as you know, in this idea and the theory of this spin 1/2 Kagome system is that you should have ideal Kagome system, and if there is distortion, then there is a possibility of magnetic ordering, and this part has been explored here by using pressure as a tuning parameter. So this is a canonical example of this Kagome sample. This is Herbert-Smythe material, and here there is a Kagome lattice of copper. And what we have found is that when we apply pressure more than something like 8 GPa, then there is a change in the crystal structure, and this Kagome lattice become distorted Kagome lattice, and due to which there is a signature of magnetic ordering, which has been shown here as some kink in this magnetic susceptibility. We also investigated magnetism of this layered material, where there's a lot of interest now. So these are basically honeycomb kind of a structure. Here, by studying their excitation as well as ground state, we have investigated this exchange parameters. We have found out model Hamiltonian form, and we have positioned this compound depending on this exchange interaction in the J1, J2 phase diagram available for this honeycomb kind of materials. We have also worked on other kind of low dimension and geometrically frustrated magnets like 1-dimension triangular chain, 2D Kagome lattice as I was discussing, and some sort of chain compounds also, where sometime magnetic ordering comes, sometime it do not come, depending on the frustration index. But due to lack of time, I will not go into detail of these problems. Now moving ahead to this slightly alternating system where we have the Kagome system, Kagome layers and triangular layers. Here what has been observed is that parent compound of the Ca, BaCO4O7, it shows non-collinear magnetic order. But if you put little bit nickel in this compound, it shows collinear magnetic order, as well as it shows the ferroelectricity. However, the parent compound shows pyroelectricity. So this kind of information, this kind of microscopic magnetic structure, we have obtained by carrying out the neutron diffraction experiments. Now moving to another sub-area of the magnetic materials, where we have been working from this decades. Here, these are the material which shows this negative magnetization. So here, the magnetization as a function of temperature under the field cooled condition changes from the positive to negative. And the idea here is that there are two sublattices which has two different temperature dependencies, and there is some sort of anisotropy present in the sample, due to which at compensation temperature, magnetization becomes 0, and after that it becomes negative. This kind of material has application in tunnel magnetic junctions, where one can replace this insulating layer by this compound which shows this negative magnetization at the T compensation temperature. So to look for the material which can be used for this tunnel magnetic junction, we were in the search of the material where this compensation temperature can be around room temperature, so that we can effectively utilize them. And in this material, what I show here is that this compensation temperature is something like 265 or so. And we have also received the microscopic understanding of this negative magnetization by carrying this neutron diffraction experiment, which are under zero field. So here what I show is that there are two sublattices and they have the temperature dependence, and at some temperature, one of the sublattice takes care of the other, and the effective magnetization becomes negative. Here, instead of, in addition to the exchange bias, in addition to the negative magnetization, we have also ordered this observed exchange bias phenomena. Here, what happens is that what we found from the neutron diffraction study is that there is a chromium lattice which orders in the canted antiferromagnetic structure. Canted antiferromagnetic structure means there is a ferromagnetic component, and this ferromagnetic component of the chromium ordering align antiferromagnetic to the rare earth ordering, and hence give rise to the negative magnetization as well as exchange bias in this material, and which we have confirmed by carrying out this neutron diffraction experiments. Now I move to the another class of magnetic materials. Here there's a magnetic ordering, but there are some ions which can be responsible for like ionic conductivity. So this is an example. In the crystal structure, there is a layer of magnetic ions, but there is a layer of sodium which is responsible for sodium ion conduction, and this kind of material can be used for battery application. Here we have carried out this neutron diffraction experiment and used this advanced soft bond valency sum analysis to find out how this sodium ion diffuses in this crystal structure. Even we have found out that the sticking disorder controls this ionic conduction as well as magnetic properties of these materials. All this in here I show this diffusion path of the sodium, which we have received by carrying out this neutron diffraction experiment. So all this information we have got it by carrying out this neutron diffraction experiment. Here what I show is that how this ionic disorder can play the role in getting this electronic conduction. So in this compound, there is ionic conductivity as well as there is electronic conductivity. So there is a mixed cation distribution over this both octahedra and tetrahedra side. And here we have measured this, we have determined this electronic and ionic contribution in the conductivity by carrying out impedance spectroscopy measurements. And we show that this chromium strongly affects this contribution of ionic and electronic conductivity. And this chromium contribution at x equal to 1.5, both this contribution become equal. Now moving ahead from this scattering phenomena where we were discussing the result in the wide Q range, I focus now on the results where the scattering is in the low Q range. Here I show the example from the protein, and this protein, if you put this multivalent salt, something like ZrClO4 or AlCl3, then there is a two-phase separation. If I increase the concentration of charge, what we found from this neutron diffraction, small angle neutron scattering experiment is that this system again becomes single phase. And this phenomena has been ascribed due to the charge inversion of the protein. And what is shown here is that this is zeta potential, which at the low concentration is more than 10. And if I increase the protein concentration again, it becomes more than 10, resulting in the single phase of this protein. We have also investigated the stability of this protein against unfolding by putting them in this multivalent salt. So what happens is that if you heat any protein, there is a gelation process, and which has been shown in this small angle neutron scattering data. So this is a protein which, if I heat it, you see there is some intensity by increasing the temperature at low Q value. It means there is a digestion process which is happening in the protein. Now if I mix in this protein some tetravalent salt, then there is no change in this scattering signal at low Q value, which says that there is no gelation process. So it means this multivalent salts are able to restrict this protein unfolding in this kind of proteins. So this kind of information we have received by carrying out the small angle neutron scattering experiment. Moving ahead to the other small angle phenomena here, what we have found is that there is a silica nanoparticles, and on the silica nanoparticles we have put non-ionic micelles. And this conventional wisdom is that these micelles, which non-ionic micelles which are absorbed on this nanoparticle, should grow as the surface area grows. So here we have used this technique in the neutron diffraction called contrast matching. So there are three kinds of interaction which is present in the system: interaction of silica-silica, interaction of silica with the micelles, and the interaction between the micelles and micelles. By contrast matching, we have cut this interaction of silica-silica and silica micelles. So there is an effective interaction remain is the interaction between these micelles and micelles. And what we found is the interesting result is that fraction of absorbed micelles decrease with nanoparticle size. So it do not go as like surface area of this nanoparticle. Now this is the another important information which we have received by the small angle neutron scattering is that these are the eccentric fibrous material. So they have the nanopores, and this internal structure of this fibrous material was not known. They are very important for the catalytic as well as biomedical application. Now here we have combined this electron as SEM with the X-ray and neutron small angle scattering, and we have recorded the data with this 3 decades of wavelength transfer. And by carrying out this experiment, we have modeled that, and we have found this internal structure of this fibrous material. Now I move to this phenomena of neutron reflectivity. Here what I show is the layers which has been grown under different conditions, means like under different argon pressure. And here I show this result of neutron reflectivity. So this is the result for plus means up spin neutron reflectivity and minus neutron spin reflectivity. And what we found by this study is that depending on this argon atmosphere, there is change in the surface roughness. And if we anneal this sample, there is a formation of GDCO2 multilayer at the interface. And in this phenomena, by understanding this surface roughness, we have understood how this magnetic properties of this multilayer changes. There is another system where we have tried to grow the ferromagnetic phase of Fe3 germanium by this multilayer route at low temperature. So here we have made these samples at low temperature and try to anneal them, or vice versa by keeping the temperature higher. In both cases, we could make this alloy phase at the temperature much lower than this what you will make by conventional alloy method, which is something like 1000 degrees centigrade or so. And we have made this compound, this alloy at 520 degree by using this multilayer route. Neutron can effectively use to see this hydrogen distribution in the material which are used for the nuclear industry. So this is the example from the zircaloy, which is very important to the nuclear research because it has low neutron absorption cross section, but hydrogen ingression changes its properties. And here, by carrying out neutron radiograph of this zircaloy 2.5 samples, we have found how this hydrogen is distributed in this zircaloy 2.5 alloy by carrying out neutron radiography. So here I show this pattern. So this color scale shows this how the hydrogen is distributed as a function of different temperatures. Now I move to the dynamics of this material. So in the dynamics, we can describe two kinds of dynamics. One is this stochastic motion, which is like diffusion or reorientation, and other is the like periodic motion, which gives rise to the coherent excitation in the material like phonons and magnons. So this periodic motion in the excitation comes at the finite energy. However, this stochastic motion results only broadening of the elastic line. This we can study by carrying out the neutron scattering experiment. And here is the example from the metallosomes. So what happens is that if we carried out elastic scattering on this sample where metallosomes is attached with the cholesterol. So here is this signal from the quasi-elastic neutron scattering. So this is elastic line and this is quasi-elastic signal. By finding out this quasi-elastic signal at couple of few values, what we have found is that once we bind this cholesterol with this metallosome, it restricts the dynamics of this metallosomes. So this information we have received from the quasi-elastic neutron scattering. Now coming to this dynamics, inelastic neutron scattering gives the information about the electric excitation like phonon. In this study, we have used this neutron scattering to find it out how this material NiX, which is chalcogenides, they have different thermal behavior. So here we have measured their phonons and we found that difference in the phonon spectrum results in the different thermal expansion behavior along the A and C axis. So this information we have get it by measuring the phonon density of this material and modeling it by carrying out these simulations. Now, so far I was showing the science which we can do with the neutron. I will quickly describe the facilities which we are having at Dhruva to do this neutron scattering experiment. So these are the systems which are used for the investigation of crystal and magnetic structure. So we have single crystal diffractometer, powder diffractometer, as well as polarized neutron spectrometer. These are the instruments which are responsible for the small angle neutron scattering as well as reflectivity. We have also quasi-elastic neutron spectrometer, which is shown here. Recently built a facility to carry out the neutron scattering experiment under electric field. This is very important for the material which shows the multiferroic behavior. So here we can do the neutron diffraction experiment under electric field and can see how this coupling can vary. Now, this is the example from the neutron imaging beam line. We also work in the couple of developmental projects. So we are making cold source, we are making type of flight spectrometers and other facilities. We are also making some beam lines at the Apsara reactor. We have also facility to make our own samples. So this is the facility to grow the single crystal using optical float zone machine and characterize them by this X-ray Lave. We have also facility for making different kind of sample. Most important, this is for making powders. And this is spray dryer facility where one can make these nanostructural granules, which is very important for carrying out the research in the small angle neutron scattering. We have this facility sputtering for making the thin films. We have the characterization facilities like PPMS, FESEM, impedance laboratory, differential, DTA, Raman scattering, dynamic light scattering. And we have the experimental facility to carry out the measurement under extreme conditions like high pressure. So with this, I think summarize, I have told that how neutron can be effectively used to investigate the condensed matter phenomena. And I have shown a couple of examples from the various fields like functional material, magnetic materials, battery materials, quantum materials, and told how neutron can be used to investigate this material. Thank you. And I acknowledge my contribution from the colleague from the SSPD, TPD, Director Bhatt, Director encouragement. Thank you.
Thank you for an excellent presentation with very nicely prepared slides. Unfortunately, because we are running a little bit out of time, so we have to compress. My suggestion to the organizers will be that we will have to put all these and make them available on the website subsequently so that other faculty can study it at leisure and contact you. And if there are a few questions, we will take it. But I want to say that I was particularly happy to see your work on the irradiated graphite and also the diffusion of hydrogen with zirconium, which are of great value for the department program.
Yes.
Maybe you can also investigate the possibility of studying helium diffusion in stainless steel, which is very important for the hospital reactors.
Yes, I think we should. Yes.
If there are any questions from the audience, there are a few. Yes, please. I think you please take the mic.
I'm Gayatri. I'm from on the radiation damage studies that we carry out at an accelerator. My simple question is, what is the sample thickness or the cross section you can see for the hydrogen diffusion? Because our usual thickness of the sample is around 200 to 300 micron.
Well, I think 200 to 300 getting neutron signal will be extremely difficult because neutron phenomena, you really need a lot of sample because the flux of the neutron is not that high. So something like imaging also, something like if you can combine couple of the sample and increase the volume, that is acceptable. But if you want the all result on the micron size sample, not possible. Like if you can combine couple of micron size sample and stack them, that is possible. Yeah.
Yeah, that's the purpose of meeting, and that should not be lost. Yes, please. Can you, because the people online may like to listen to you also. Mic is coming to you. Going around the entrance, coming down to the other end.
I think liquid cell can be done, yes. It is routinely done, liquid. Water is effectively sometimes it is beneficial. You can contrast matching this water. So it depends on the problem, but liquid sample can be done. So there is cells actually by which you can fill your sample. That's not a problem. Something like at the order of 10 to the power 5 at the sample position. Yes, that's okay, Paul. Because this is like experiment where you are just only seeing how this neutron beam get diffused from direct direction. So it's all right. It's a neutron beam, like collimated neutron beam, and you see how it is diverged. Yes.
Are there any questions online? There are no questions online. Let us thank the speaker for an excellent presentation. The next presentation. Welcome Dr. Devasis from VRC.
Good afternoon. And what I will speak is the some glimpse of the synchrotron-based condensed matter research at BARC. I would like to thank the organizer for giving me this opportunity. And basically this X-ray, and particularly when it is synchrotron-based X-ray, it is not only important, but I will say it is indispensable for condensed matter research.
Take it full screen. Yeah.
Thank you. Yeah. So what I will do, after the introduction, I will give some information about the synchrotron beam lines made by the physics group BSc for condensed matter research at, and then some scientific research results, and then summary. So as I told that X-rays from synchrotron is really important. And why it is important? There's several reasons. Like this, it has almost 1,000 times more flux than lab X-ray sources. So you can do the in situ experiments, and the collimation is much better. You can use also very tiny samples, and there is every material, there is some kind of absorption edge what you can use there, and as well as the polarization for the synchrotron beam. So these are the beam lines which are built by physics group of BARC at Indus 2. And you can see that there are 1, 2, 3, 4, 5 beam lines at the Indus 1 synchrotron, and there are 7 plus 2 facility beam lines at Indus 2 synchrotrons. And the 2 beam lines are under commissioning, and the 7 beam lines are already operating. And these are used for the condensed matter research. So basically, what are the fields where these are used? This, of course, this crystallography, protein crystallography, then local environment and chemical structure, electronic state, imaging, and the mesoscopic structure of materials. So this is the brilliance versus energy for the two. And of course, there is some now for 2 beam lines, there will be this undulators, which has much larger flux. So this increased flux can be taken is a very advantage for this kind of experiments what are shown here, like this imaging. There are 7 plus 2 beam lines, as I mentioned here, like imaging beam line. Then there are 2 exapse beam line, which is one is dispersive exapse and also scanning exapse. There are beam lines for diffraction at high extreme conditions, like high pressure and high temperature, then photoelectron spectroscopy beamline, small angle scattering beamline, then protein crystallography, and these two beamlines here, these are under commissioning. First, I will concentrate on the local structure and chemical environment in materials. So for this, normally X-ray absorption spectroscopy is very important, and this is the facility, as I told, and it is working since 2009. So there are recent upgrades in this beamline, which also includes this XMCD setup, and then in situ X-ray absorption studies, and of course there are several facilities which are mentioned here, like this for the charging and discharging of the battery materials. This kind of in situ experiments one can do here, and also very dilute samples for biological exams. So this is one example for the charging discharging study of the electrode material, which is based on iron oxide and for lithium-ion battery. And particularly this kind of in situ experiments can tell what are the intermediate stages in a particular chemical reactions which is taking place during the in the lithium-ion battery in this charging discharging. Here it is shown that this intercalation reactions and then their conversion from Fe3O4 to this Li to Fe3O4, then FeO, and then metallic Fe. So this can be seen from the X-ray extended X-ray absorption fine structure, which is shown here. So one interesting thing is that when this X-ray absorption is used, if we use it at grazing angle, then this it can give a depth selective information. Like this is a nickel titanium multilayer, and whether this alloying takes place at the interface or not, that can be certainly measured through this grazing incidence exapts. And because that what happens, there is a formation of these standing waves here at the surface, and by changing the angle, one can get this information. And where it is in this example, where it is shown this nickel titanium multilayer is very important, as Dr. Jain also told that this is used also for the neutron guides. And then the reflectivity of this kind of material is very important. And it is shown that when this multilayer is grown in the mixed atmosphere of argon and dry air, it gives a better reflectivity for the neutrons. So now this is the X-ray photoelectron spectroscopy beamline, and that is also gives the chemical environment and of the materials. Like as Dr. Yakmi was also telling, that this kind of organic semiconductor like magnesium thiocyanate. So this kind of organic semiconductor, when they are just it's made a layer on a substrate, and depending on whether this layer is first it is aluminum and then magnesium thiocyanate or other way, then they have shown that the interface is diffuse or not. That depends on this particular purpose. And this photoelectron spectroscopy experiments, by changing this angle, one can, it shows the spectra here for different angles, where it can be differentiated whether this alloying is formed or the interface, this interface is diffused or not in this kind of organic semiconductor. Another example is that non-evaporable getter materials, which are very important for this achieving this high vacuum, which are particularly for all these beamlines. The beamlines are very high vacuum, like 10 power minus 10 to 10 power minus even sometimes 11 or 12 mebar. And then this kind of material is very important. So understanding the chemical structure of this kind of material is very important. And this by this photoelectron spectroscopy, one can use whether this hydrogen is adsorbed by these materials or not. Now, protein crystallography. It is a very important technique, and there is this beamline is already working for several years, and it is heavily used by the users. And this is one of the examples. This is on the peptidase. And there is a peptidase are basically these enzymes, and they cut the peptides in smaller forms. Basically, proteins, when we eat something, then these proteins are broken down in peptides, and then by this then smaller peptides, and then finally in these amino acids. So this understanding the structure is very important. So protein crystallography can give this kind of detailed structure, very high resolution structure. Otherwise, without synchrotron beam, this kind of structure, getting this kind of structure is very difficult. So these are the examples on this kind of enzymes. And there was also another example where this screening of the crystals for the SARS-CoV, which was also done at this beamline. Because when you prepare the protein crystals, all crystals cannot diffract because there are some internal defects and things of that sort. So this beamline can be used also for screening this kind of crystals. Sometimes this making these crystals are difficult, and molecular dynamics can be used to simulate what are the properties and all. So here there is a cholera bacteria proteins, and there is some row dependent transcription. There are different process of transcriptions, which is a row dependent, row independent. So in this case, there is a row protein which is important, and how they behave for this transcription termination of this cholera bacteria, that has been simulated using the molecular dynamics. So these are the complementary thing for the information one gets from the protein crystallography beamline. Now coming to the mesoscopic structure in materials. So for this, there is a small angle X-ray scattering beamline, which is just recently installed in 2019. And this beamline is also used by the academia as well as industries. And I will show a few examples from this beamline. Like we see this coffee ring effect. If there is a spill of coffee in a cup, then if it gets dried, there is a ring which forms, which is called the coffee ring effect. Now, if there is a drop of colloids in the paper in form of some porous membrane, then whether this coffee ring effect forms or not, that can be differentiated by doing the scanning small angle X-ray scattering. And one can also do this kind of modeling based on this differential equations, putting the two types of source terms like absorption and the flow. So this has been done recently in this beamline. Another important thing, as Professor Yagni was also telling, that colloids are really interesting. So when we can prepare this kind of tiny droplets because of the high surface area, one can take use of this high surface area to getting these droplets dried very soon within a fraction of a second. But the physics is that during this drying process, the capillary force makes these nanoparticles to be interlocked, and one can get this kind of grains. Of course, this process is very interesting and useful in the industry, which is called spray drying. And with this spray drying process, can we pack the not only spherical particles but anisotropic particles like ellipsoids here, and how one can get the local packing fraction of these particles here, that we have done some experiments, and we have shown that the standard analysis will not help unless and until one takes care about the effective structure factor, which is governed by some distance distribution function, which is negatively skewed. So this is some recent result in this direction. Of course, this kind of granules have several applications that right now I will not go into that. Just this applications of this kind of granule is that to understand the cementation process, like when the silica granules is just put in for some pozzolanic reactions, just put some calcium hydroxide and then put some water, there is some pozzolanic reaction which starts, and with time how this pozzolanic reaction goes, so one can start with this time dependent studies with this. And of course, one can do different models based on the formation of these fractals clusters with time, whether the scaling phenomena occurs or not. So one can. Other time-dependent studies one can do is this kind of lamellar structure, which is very much important as in the like the FMCG and other industries. And this kind of studies has in fact initiated some collaboration also with some industries like Jyoti laboratories and all. So there is also the drying of the polymeric films, nanoparticle loaded polymeric films. So we have shown that this is some kind of reversible process. You can do hydration as well as dehydration of this process in the PVA silica nanofilm. So these were the examples of the mesoscopic structures. So this is the imaging beamline, which is at Indus 2. This beamline effectively gives the absorption contrast as well as the phase contrast, and one can get the details about the many interesting problems. Like here, it is the kidney stones, and here it is the arsenic inside the rice seed, which is maybe a very important problem in West Bengal. So this one can study how this arsenic part is inside the rice. It goes from the soil, and by doing this 3D elemental mapping using the KH subtraction imaging, basically at the KH below and above the KH, one do the experiments, and then after subtraction, one get the effective form of this, how the arsenic grows inside this seed. One can do it. And of course, the structure of the bone by the tomography. So this kind of interesting things can be done with the X-ray imaging. Materials at very extreme conditions is it is a novel way also to synthesize some of the unconventional structures. This is a beamline, which is a now it is there is a in this beamline, which is now one has got this microfocusing, which is of the order of 8 microns beam one can get by using these lenses. So this beamline can also be used for getting this kind of unconventional structure under pressure, like something like this GPA, 2 GPA, or 214 GPA, that kind of structure. We know that KBR exists, but whether KBR3 or KBR5 exists or not, that kind of experiments can be done with this beamline. Same time, whether this torsional motion can give some transition which is otherwise not possible in hydrostatic with the hydrostatic pressure. Here is an example that three times reduction in the phase transition pressure in this zirconium niobium material. There is in hydrostatic pressure, it needs 7.5 GPa, but here it occurs at 2.3 GPa. So unless and until we say about infrared and Raman, this condensed matter part is not complete. So there is a infrared beamline at Indus 1, which is also used for many condensed matter studies. So this beamline, there is an example here that this is molecular crystals and this acrylamide, and how the peak varies with a different pressure. There is a phase transition of this glassy to a glassy-like nature, and then the wave vector, wave number from 600 to something like 4,000 centimeter inverse, this beamline can access. So this Raman spectroscopy, we have one homemade Raman spectrometer as well as this micro Raman spectrometer, and these are the sample environment, and like 77 to almost 1200 degree Kelvin, then different pressure, then confocal 3D Raman mapping. And one example from this kind of system is that normally this gadolinium silicate, which is a polymorphic material, in nature it can exist in almost in 3 forms in ambient conditions. When you give some pressure, which is something like 25 GPa, then it goes to a glassy nature, and after releasing the pressure also it remains at that glassy state. So this may be one kind of process that one can recover the glass phase at the ambient condition by putting this kind of pressure. Another interesting example is the surface enhanced Raman scattering, that we know that because of the surface enhanced plasmon effect, one can in fact detect the vibrational spectroscopy of these biological molecules. So this is one of the example for the plasmon induced dimerization of thiazolidine, this molecule in presence of silver nanoparticle. So this can be accessed by this kind of Raman experiment. Thin film, the surface physics is a very important thing, and in our physics group of BRC, we have this kind of facilities where one can make a long, means almost like 1 to 1.5 meter mirror or multilayer, which can be deposited in a very short time. And then there are other facilities which are sputtering facilities which are available in this system. This is a very long, 9-meter long, this inline DC magnetron sputtering system. And these have been used, in fact, for making these neutron mirrors for the neutron guides, what Dr. Jain has told. So this shows some kind of reflectivity profile from this kind of mirror which has been made. And here it is, this is m equal to 2 for this, just this kind of mirror. One can verify whether how the quality of the mirror. And then, of course, we have in physics group expertise on the crystal growth, single crystal growth facilities. Then I'm not going into detail, but there are different kinds of single crystals which can be prepared. And recently also they have made some fabricated some kind of very small detector, which is based on some high purity germanium. Also, we have some kind of expertise in this thermoelectric devices materials. So for the shortage of time, I'm not going into this, but this figure of merit and this efficiency of this kind of material, now it is, I think it is almost reaching like 7 to 8%, the efficiency of this kind of. There is also a facility for the gas phase cluster formation. And recently there is a work on how the generation and the stability of the lanthanum clusters for different values of the same. It has been verified, which was otherwise it was not earlier reported. So basically, I would want to conclude now. And so the summary is that the synchrotron-based condensed matter research is indispensable. And the basically fundamental aspects of condensed matter, which is structure or the local structure material, mesoscopic structure of the materials, all needs this high flux synchrotrons. And this kind of materials like functional materials, magnetic materials, battery materials, ceramics, colloids, soft matter, and these techniques, which are very important. And BRC, we have this kind of beamlines, as I have mentioned, and also these associated some development for these beamlines. So now future directions, we are hopeful that the 4th generation synchrotron, if industry comes, then of course this ability of this kind of in situ experiments and the polarization dependent experiments will be enhanced many folds. And so at this, I would like to acknowledge various divisions in the physics group, like this BRC, BDAS, SSPD, high pressure physics, MPD, TPD, and ILSS. And of course, I would like to thank Director Physics Group, Director BRC for their
presentation, giving a broad overview of the beamlines and their very important applications. I'm sure there will be a lot of topics which we discuss maybe in a complementary manner, even from the RRCAT presentations. If there are just one or two questions we can take, or we go to the next presentation because we are running out of time. Yes. That's something we like. I want to distinguish to go to that's something we like.
No, that is
at room temperature. Planning to go and load the pressure. There are a lot of interest to be and
what I showed, that the EXAPS beamline right now they have this XMCD option. This VRC beamline, I'm talking about the VRC beamlines. Yeah. I think so. It is at this moment. Yeah.
Thank you, Dr. Seth, for a nice presentation.
Yeah.
We now go to
Please. Good afternoon. I am going to present an overview of the theoretical condensed matter activities in BRC. So let me first acknowledge the contributions, because in different divisions people are working depending on their divisional mandate. So these are, first thing is, aim is to study the pressure-induced high pressure, pressure-induced phenomena, particularly equation of state, phase transition, and also pressure-induced superconductivity. And then there is this glass and advanced material division. Their main interest is to design and development of high entropy alloy and functional materials. Then in chemistry division, they are more interested in calculating the thermophysical properties of metallic nuclear fuel, which will be advanced fuel material for fourth generation reactors. And in SSPD, there are a lot of activities on functional materials and soft condensed matter. Now, we all know that when we talk about condensed matter, there are large degrees of interacting degrees of freedom. Now, for example, that condensed matter consists of a large number of electrons, atoms, molecules. And as a theoretician, our aim is to understand their macroscopic properties from the comparatively simple law of interaction in the microscopic level. So to do that, how to approach? There are generally two types of approach. One is semi-empirical approach, where you can devise a potential for that macroscopic system, and which has a short range repulsive interaction and a long range attractive interactions. And you can generate the potential parameters from experimental data and also from sometimes from first principle theoretical data. And another approach is quantum mechanical. All we know, we cannot solve the Schrodinger equation, but there are under some approximations we can solve the problems in this area using quantum mechanics. So the most successful quantum mechanical theory in this field is density functional theory. So since our majority of the work is based on density functional theory, I want to just give a flavor of it. So it is basically given by Weinberg and Kohn by two theorems. First theorem tells that for an interacting electron system, the total energy of the system is unique functional of electron density. And second theorem states that for the correct electron density, ground state energy will be correct density can minimize the ground state energy. But with this theory, you cannot just apply for solving the condensed matter problems. So then Kohn devised a way to apply this theory for condensed matter problems. So basic idea is that you can map this interacting electron system to the non-interacting reference system and look for a potential which gives you the same electron density as the interacting electron system. So using that, you can solve this Kohn-Sum equation, which is a Schrodinger equation like things, and he gave the way how to calculate this effective potential. This is the self-consistent cycle, which in every DFT calculation we perform. This is first is that assumes or guess density. Then you can construct the effective potential, and accordingly you can solve the Kohn-Sum equation. And again, you construct from the Kohn-Sum wave functions, you can again construct the density, and you can continue the self-consistent until you reach the convergence. And when you get the convergence, you can get the total energy of the system, and from total energy, you can calculate the force, pressure, and other things like phonon frequency, etc. So when you calculate the force, according to force, you can study the dynamics also, which is called ab initio MD simulations. Now this is the computing facility available in the BRC. There are two supercomputers, and Aganna. We are heavily used in these two supercomputers. Also, there are a few small clusters in other divisions. And for DFT calculation, we are mainly using these softwares like VASP, Quantum Expresso, Win2K. They are the main software for DFT calculations. And Phonopi, Phon, they are mainly used for calculating the phonon properties. EPW is from using from superconductivity calculations. And USPEC we are using for high pressure crystal structure search. Similarly, for classical MD simulation, there are software like LAMS, MPS, DL Poly, DSPER, etc. So now I will present some of our work on equation of state, phase transitions, etc. This is, we have done the equation of state for americium. And you know that americium is sitting just after plutonium in the periodic table. And it is the first element in the actinide series where F electrons are localized. And when F electron is localized, you cannot do the DFT calculation with local density approximation or generalized gradient approximation. You have to go beyond DFT. So beyond DFT is to handle these localized electrons, one should apply the on-site Coulomb correlations effect. That we have done using GGA plus U type of calculations. And we have calculated the correct ground state properties. And by when you apply pressure, this localized electron will get delocalized and your amount of Coulomb interactions will reduce. So your you have to get the high pressure equation of state, you have to fine tune these U parameters. Next we have studies another thorium dialuminide. In this system, we have used the evolutionary crystal structure search to study the phase transition under pressure because there are controversy regarding its high pressure structures. And we found that near 2.5 GPa, there is a LB2 to simple hexagonal structural transition. And this new structure is completely different from whatever known in the literature. And also we have calculated the PT phase diagram for this compound by calculating the vibrational free energy by calculating phonons. And also to understand the origin of these phase transitions, we have calculated the electronic properties. First, we have the electron localization functions. You can see that when there is a phase transition, then there is a electron localization between two aluminum atoms, which signifies that the metallic bond with aluminum metallic bond is changing to some kind of getting some covalent character, which is the region of this transition. Similarly, we have also carried out phase structural transition in PTL2 using evolutionary crystal structure search. We predicted two transitions. One is around 6 GPa and another is around 28 GPa. In 6 GPa, it is a metal-metal transition, but in 28 GPa, it is metal to insulator transition. To understand the origin of this metal to insulator transition, we first see the Fermi surface. We found that there is a large parallel sheet of Fermi sheet, which can lead to the charge density wave instability in the system. To calculate that whether there is really a charge density instability or not, we have calculated the electronic susceptibility. As we know that if there is a charge density wave instability or Fermi surface nesting, then electronic susceptibility in one direction shows a singularity. But in 2 or 3 dimensions, it is not a singular, but it shows some kind of signature. And then we have calculated the phonon frequencies phonon dispersions, and we also saw that in the same wave vector there is a phonon softening. So we tell that it is due to charge density wave instability. There are a lot of activities to study the equation of state of nuclear fuel materials. There are we have studied many systems like thorium nitride, uranium nitride, thorium carbide, then thorium dinitride. Here in thorium carbide, we shows that our calculated equation of state matching quite well with the available experimental data. And also this in case of THN2, in earlier literature, it is found that its ground state is FM3/M, NaCl structure. But we found that it is not NaCl, it is a monoclinic C2/M structure. So similarly, we have calculated the high pressure phase transitions in other high nitrides. Next is this thorium and uranium sesquicarbide carbide. Here also we have carried out the evolutionary crystal structure search, and we have calculated the equation of state. And also, since uranium is involved, uranium may in the compound may show the electron localization. So study that, we have used the on-site Coulomb correlations for uranium carbide. And we have showed that if you use the on-site Coulomb correlation, this phase transition pressure goes high. From 50 GPa to it reached to 75 GPa. And these are also nuclear fuel materials, but they are metallic fuel, and they will be used for advanced fourth generation nuclear reactors. They have significant higher melting point, high thermal conductivity, and high stability. Because of that, we have studied the thermophysical properties of these two systems, and we found that their precipitate will match the experimental result only when we include the electronic contributions. Also, we have calculated the thermal and electronic conductivity for these two systems. Now some dynamic high pressure. Dynamic high pressure occurs when there is a high density, it is actually high energy density systems when at a short time you deposit a large amount of energy at a short time. So then the shock will create and it will propagate and it will change the matters. Here interest is to study the Hougonio parameters. This is the Hougonio equation, and here interest is to calculate the Hougonio parameters for the functionally graded materials. Functionally graded materials are used in RAM impactor. In RAM compression, our aim is to get the peak pressure by reducing the loss due to increase of temperature or entropy. So they have used that a semi-empirical method like Debye-Gunderson model to calculate these Hougonio parameters for linearly graded and quadrically graded materials. And they found that paraffin-based materials will be best for this RAM impactor. Next, we have studied the shock propagation through metals. Here we have used the embedded atom potential and classical MD simulations. So this is the shock front. Here this 2 peak corresponds to elastic and plastic waves. And we have showed that for different regions for plastic or elastic peak, this Hougonio elastic limit will be different. And we have also studied the dependence of on Hougonio elastic limit on sample length, initial temperature, peak stress, and strain rates. Some of our works on superconductivity. To study superconductivity using ab initio methods, we have used the Migdal-Eliasberg theory, and according to that, we have solved these two coupled equations. Here, Z is the electron mass renormalization factor, and delta is the superconducting gap. So we self-consistently we solve these two equations, and search for the minimum temperature for which superconducting gap will be 0. And this method we have used for LIVC, which is at only 2 minutes. So we have studied this monolayer, and we have showed that this monolayer will be a 2-gap superconductor and with TC 70K. Similarly, we have also studied superconductivity in metallic hydrogen. This is typical phase diagram for hydrogen, and in this region around 400 to 600 GPa pressure range, it will be metal. And we have calculated its superconductivity, and we found that around 400 GPa TC will be around 321 K. So similarly, in recent, there is a huge interest in superhydrides, which form at high pressure, and its transition temperature is around 250 K. So, but because of hydrogen is involved, there is structure is not clear. So we have used the evolutionary crystal structure search and predicted a structure and calculated the superconducting properties. Next, there is alloy design using the DFT-based calculations. We have first designed the ternary and quaternary equiatomic high entropy alloy, and based on that, we found that there are 8 ternary alloy which can form at single phase, and from this single phase, there are we found 3 quaternary alloy can be constructed, and using based on this screening, they have designed the alloy and they measured the things, and they found that these 3 will be single phase alloy and these 2 will form the mixed phase alloy. Another is we have studied the formation mechanism of ordering in delta ZR2 alloy. At high temperature, it is a BCC disorder alloy, and at low temperature, it goes to the ordered UZR2. So we have studied that how these forming, and we found that chemical energy ordering is the driving force for this ordering of UZR2. And we have also studied the piezoelectric response in this hybrid organic inorganic perovskites. There is a lot of activities in recent that it gives very high piezoelectric response. So what is the origin of this piezoelectric response? We found that there is a metastable phase which is, and the stable to metastable phase switching is actually give this high piezoelectric response in this material. Then there are some MD simulation, ab initio MD simulation, which studies the sodium diffusion in sodium deficient and sodium excess sodium materials, and they found that in case of excess sodium material, there is a sodium-sodium repulsion, which deform the AlO4 and SiO4 tetrahedra and make a path for sodium diffusion. Just another 2-3 slides. So also in LiAl2, here we have studied using ab initio simulation the lithium diffusion, and we find that in the amorphous, since the distortion and reorientation of the AlO4 tetrahedra, this gives the higher diffusion for lithium, and we have also predicted a pedal wheel mechanism in this work. We have also studied the superionic material, the diffusion of copper in this material, and we found that at low temperature it is a solid like just nearest neighbor hopping, and at high temperature it becomes liquid like diffusion. So this is also some subcondensed matter. Here in days, it is the acetamide plus lithium perchlorate and pure molten actinidia. We found that diffusion is restricted due to the formation of hydrogen bond with acetamide molecule. And there are two types of diffusion. One is structural diffusion, where hydrogen bond is breaking and creating, and ion is diffused through structure. And another is the vehicular diffusion, where whole cage is diffused through the medium. And this is the, just another two. This is the water, is a water that if you add water, that diffusion of lithium increases, and that we give the reason why it is so. And this is some classical molecular dynamic calculation for Cu2Z and SnA4. It is a thermoelectric material and it is the rare earth free. So we have shown that using our MD simulations, we can predict the thermoelectric figure of merit and also the lattice thermal conductivity quite accurately. And we have also studied the Barrow transition, where in this NaMn7O12, and we gave the mechanism. This is the Jahn-Taylor distortions, which occur at the Barrow transition. So using classical MD simulations, we have give the reason why it is so. Thank you.
So you had a lot of interesting results. Yeah, materials. And we have
Yes.
joined online. If there are any questions, one or two will get taken up, otherwise, yes.
How is this uranium silicide is synthesized in bulk?
No, this is, we have done just calculation, thermophysical.
Transition from metal to
Insulated, yes. Yeah. So, still, it is not, nobody has done this experiment.
So this is Shuri from HRA. So I have a question about the MNCM project for
Okay.
So did it relativistic?
Yes, so we have just used spin orbit, not spin orbit interaction. Yes.
Thank you very much for the presentation. There are many questions, so you can continue during the lunchtime perhaps. I think we will have to request Dr. Bhushan to join us. Before that, I think there should be unsharing of done. For that talk and the lunch. Absolutely. Okay, so we conclude this discussion. Yeah, we can. Fine. So then we thank all the speakers and I wish Dr. Bhushan in advance. And thank you for also making the presentation. And I think you can make arrangement about the lunch. Yes, we can proceed. Thank you very much, both people present here and both online, also online, for your patience and waiting till 1:30. But we will have to join little earlier so that we're able to conclude the other lectures also in the afternoon.
Yes.
Thank you very much.
So thank you, Professor Basudeva Rao. And we are concluding these sessions, and still as we are running really late, now we'll break for the lunch. And our bus is waiting at the gate, and we have some car also. So we'll join again here at 2:30 and start with Dr. Bhushan, and then as usual, we'll go on. Okay, so we will again join at 2:30. Yeah.
You can put a message on the chat board also from those online.
Yeah, we have already sent a message to Dr. Bhushan. I agree.
পরের সেশনটা তো অনলাইনে আছে আর এটা থেকে
আচ্ছা
এখান থেকে কানেকশনটা যেমন আছে অনই থাকবে অফ অফ। আর আপনি মোটামুটি কি বলে এটা শেয়ারিংটা এখান থেকে করে দিচ্ছেন তাই তো?
আপনি কি ওদিকে আছেন?
হ্যাঁ
আপনি ওদিকটা আছেন?
হ্যাঁ 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 আচ্ছা।
এর পরেরটা অনলাইনে আছে।
বলে গেলাম আমাকে। হ্যাঁ नहीं जानते सुन रहा सुनते आप तो बैठ नहीं सकते।
Thank you. Yeah.
Hello, sir. Can you hear me?
Yeah. I'm able to hear you.
Should I share the screen or the window?
Yeah. You can do all those things.
Okay.
So because just people they finish their lunch, they are on the way. I came early. Just maybe you will be waiting, so I thought, well, let me go.
Right. For sharing, I think you have to enable me to share.
Yeah. We'll do that.
I think that person will come and probably. Yeah.
Just call the person.
So I have to be made presenter.
Yeah. Let this person come.
Yeah.
परमिशन आइए, आप थोड़ा आइए इधर. वो बोल रहे हैं कुछ उनको परमिशन चाहिए प्रेजेंटेशन के लिए.
सही परमिशन देना, वो जो होस्ट वो पे है ऑलरेडी. आई हैव गिवन हिम द परमिशन एक्चुअली.
हाँ. आप अभी स्क्रीन शेयर कीजिए.
It says you can't share unless the host or a co-host or presenter makes you the presenter. तो हमें आपको प्रेजेंटर बनाना है.
हाँ, जाइए. I will do it. Hello, sir. Govindaraj ji.
Hello, sir.
You can unmute. Hi. You can unmute yourself.
Yeah, okay. I think now you are saying it. Yeah. Can I just share?
Yeah.
Share.
Now it is done.
Yeah. Correct. Yeah, it is coming. Yeah.
Yeah. It is coming.
Is it coming?
Yes.
Okay. Can I just make it full screen and?
Yes. You can make it full screen.
Is it coming now?
Full screen has not come.
Oh, okay.
No, it's okay. Make it full screen.
I have to share the screen, I think.
Screen is coming. I'm able to see your presentation.
Okay.
Maybe you just maybe below that copy you hit bottom line. Yeah, that's what I'm telling.
Is it coming now?
No, not yet.
Okay, I think I have to share the screen only, I think.
Okay, you can do it once more.
Now go for the full screen.
Full screen,
Is it coming now?
Yes. Very nice.
Okay. Yeah. Thank you, sir. My voice is audible?
Yes, it is pretty clear.
Okay. Yeah. Thank you, sir. I'm ready now.
Just wait for maybe 5 minutes.
Yeah.
So let the people come. We had a delayed lunch because
yeah, right. Yeah. Morning was very interesting. Yeah. And very good talks. Yes, very nice. Yeah. I have heard Yakmiji many times, and today he was at his best, I can say. Yeah.
So we'll just wait maybe another 5 minutes.
Yeah, sure. Yeah. Okay, sir. Yeah.
Okay. All the best.
Yeah. Thank you, sir.
We have created a this is a session 1. Okay. You can make it session 2. Session 2, no? Yes, you can put that thing here. Can just see. See, it is connected here. I think there. No. Take that, yeah. Okay. So this one.
Yes, sir.
Just hold on. You are coming? Okay.
Can I start?
Just boss is on the way.
Okay. Yeah.
Just hold on, hold on. This one, right? Night, Anna. Thank you. It's a superconductivity. Session 1 ही कॉपी कर दीजिए तो मीन माय PTX इसलिए दी तो हाँ এটা করে দাও X
मैं बाद में फोन करता हूँ मीटिंग में.
So many slides.
Yeah.
Very good.
आ गया बस आ गया क्या बस
Can I start, sir?
Just hold on.
Okay.
Maybe 2-3 minutes. We'll tell you. Huh?
Okay. Okay.
So the bus is on the way.
Okay.
Sir, ये वाला? Sir, रहने दे.
Better now. Better, yeah.
Just wait for another maybe 2 minutes.
Sure, sure. Yeah, okay.
वो बंद करो वीडियो बंद है
Hi, Bhushan.
Yeah.
Yeah, you can now start.
Okay. Yeah. Thank you.
So you have 20 minutes.
Yeah. Yes, sir.
After 15 minutes, you will be giving an indication. So
Yeah.
you can leave some time for question and answer.
Sure, sure. Yeah. Okay. Sir. Yeah. So, is it visible completely?
Yes, yes.
Hello? Am I audible?
Well, audible.
Yeah, okay. Thank you. Thank you. Firstly, I thank the organizers for giving me this opportunity to present some of the analytical instrumentation that we have been doing in EMAID, which is the new division from TPD, Technical Physics Division previously. So, because this is a HBNI presentation, I thought I should first introduce the audience to the basic features of analytical instrumentation. So as you know, any analytical instrumentation consists of three different things: a probe, an analyzer, and a detector. So the probe, analyzer, and these are the three important things of any analytical instrumentation. Now the probe basically consists of either particles with mass, massive particles such as electrons, positive ions, or neutrons, or photons, which can be lasers, X-rays, UV, IR, and gamma. So these constitute basic probes, and in the analyzer part you have electrostatic, magnetic, or optical part. So in the electrostatic and magnetic you have either hemispherical energy analysis or magnetic mass analyzers. These basically analyze the charged particles that are either coming out of the sample because the probe has interacted with the sample. And then you can also have optical analyzers such as interferometers and spectrophotometers. You can also have analyzers for neutral particles such as time of flight analyzers and Mott polarimeters for even analyzing the spin state of a charged particle. Similarly, when you have the detector and after analyzing, the particles have to be detected. So for detectors, you have charge particle detector and a photon detector. Charge particle detectors are usually Faraday cups, channeltrons, channel electron multipliers, or microchannel plates. And in the photon detectors, you have photomultipliers, crystal scintillators, and HPG detectors. Now, this basically constitutes any analytical instrumentation setup. So you need to understand three things: probe, analyzer, and detector. So these are the three important aspects of any analytical instrument. So we have developed different types of analytical instruments in TPD, EMID, BRC. I will just give you a hint of all this. I'm not going to dwell in detail. Most of it is available, and some of the things which have done new instrumentation, I'll just take it up a little bit in an extensive manner. OJ electron spectrometer, X-ray photoelectron, thermal ionization mass spectrometers, inductively coupled plasma mass spectrometers, quadrupole mass spectrometers, time of flight mass spectrometers, helium leak detectors, superconducting magnets, and various types of gas sensors and ultra-high vacuum pumps. So this is one of our earliest instrument developed in TPD, BRC. This is basically the scanning OJ electron spectrometer. OJ is basically a two-step process. The probe, which is 5 kV electrons, basically hit the sample and remove one of the electron from the core shell, and an electron from outer shell falls into the core shell, and one more electron, the difference in energy, gets knocked out. So this means the final state of the OJ process is basically a doubly charged state, and the analyzer here detects the OJ electron that is coming from the sample, and this is basically a cylindrical mirror electron energy analyzer. And each electron that is coming out of the OJ process is very specific in terms of energy, and that is specific to the material that is being analyzed. So by looking at the spectrum and specific peaks on the spectrum, one can identify various chemical compositions of the sample. And this is basically there's a very close to the surface only one you can analyze. You can also probe the sample and produce a chemical image by scanning the primary electron beam, which is the probe, across the surface of the sample. So you can also get a chemical image of the surface of the sample. So these peaks here represent the, for example, this is a silicon matrix with a copper thin film coating on the surface. So one can see the silicon peaks here and other peaks, iron, oxygen, carbon, etc. And the amplitude of these peaks is directly proportional to the composition of the sample or the elemental concentration of that particular sample in that particular matrix. So this is one of the earliest scanning OJ electron spectrometer which we have developed. This is a very recent development, X-ray photoelectron spectrometer. This is called ESCA, or electron spectroscopy for chemical analysis. Here the probe is either aluminum K alpha, Mg K alpha, or in this case we also have a silver L alpha line. So these are basically X-ray sources. So the probe is here X-ray, which is a photon, and that hits the sample, and electrons are generated from the photoelectric effect by this equation, and those electrons are detected with the help of a hemispherical electron energy analyzer to very high energy resolution. And eventually, after detecting these electrons, the channeltron multiplier basically gives a signal for each of the electron that is being detected, and eventually you get a binding energy spectrum like this. So you can see various peaks depending on the position of that particular peak. One can say what is the sample. In this case, it is a gold sample, pure gold sample. So you can see all the peaks that are coming out of the gold sample due to the photoelectric effect. This is very straightforward and very useful for identification of atomic species, and it's very good for identifying chemical composition, especially at the surface of materials. I mean, most of the XPS and ESCA systems are being routinely used in all condensed matter physics experiments. One can find out the binding energy and as well as the shift in the binding energy due to the presence of oxygen or other compound nearby. So basically the element gets shifted, and the amount of shift is directly proportional to the valence number. So one can also here do the chemical imaging of the sample by moving the sample with the help of a 3-axis motorized manipulator. So one can get a three-dimensional image of the surface of the samples by having some sort of a depth analysis also. And then we go to the mass spectrometer. Mass spectrometers are being designed and developed in TPD for a very, very long time. This is one of our earliest mass spectrometers, about 25, 30 years back. And this is our latest mass spectrometer, maybe about a year back. So one can see the development in instrumentation, and of course, the spectrometer has become much, much more compact. So this is basically the workhorse of nuclear industry. All units in DAE require this kind of a mass spectrometer. And here the probe is basically thermal ionization, which means that you make the sample in the form of a liquid, and the small droplets of the liquid is placed on a tungsten or a rhenium ribbon, and that ribbon is heated by passing a current through it. And in that process, the sample gets thermally agitated, and an electron filament, which is very close to the tungsten ribbon, finally ionizes the sample that is coming out of the heated tungsten ribbon. So you produce positive ions of the sample, and then these ions are accelerated and pushed into a magnetic sector. Now, magnetic sector, BQV is equal to mv squared by r. Using that formula, you can find out the radius of that particular mass. So once you select the magnetic field, you can detect that particular mass at the end with the help of a detector. Now, this is an extremely accurate method of finding out various masses, especially isotopic abundances. And it requires extremely small samples, maybe a few milligram or a microgram. And mass resolutions are very high. And this has got enormous sensitivity. For every 500 atoms, you can produce one ion. So that is a very good sensitivity. And for nuclear industry, what is most important is this isotopic ratio concentrations. So U235 to 230, for example. So we can detect this with the precision of 0.05%. So this is the workhorse of the nuclear industry. All DAE units require this, and we have been developing this, and it has been getting better and better every day. Another type of mass spectrometer is the inductively coupled plasma, where the probe is now plasma ionization instead of thermal ionization. So in the case of a plasma, you generate a plasma with the help of a argon gas in a RF or a microwave environment. And basically RF ionizes the argon gas, and in the it produces plasma. And that plasma is now, the sample is introduced into this plasma zone. By dissolving the sample, and basically you require liquid samples for this. The process is called leaching, and the sample is introduced into this plasma zone. Here you can see the light on this. This is the plasma zone. The plasma basically ionizes almost all the sample materials, and eventually you produce positive ions of the sample, along with positive ions of, for example, argon, which is the plasma making gas here. And this positive ions are pushed into the magnetic sector, or you can also use a quadrupole mass analyzer. And then at the end of the magnetic sector, you can detect these ions for particular mass with the help of a Faraday cup or a Chalentron multiplier. Now, the advantage of this method is that it has extremely high, low-level trace element analysis can be done to something like ppb level concentrations. Here we are showing us very, very small amount of natural uranium peak here, which is given in a sample to us. So these are the various types of elements that can be analyzed. Eventually, one can also find out the concentration of this particular element in the matrix of sample. Another type of mass spectrometer is secondary ion mass spectrometer. I'll just explain to you in a little bit more detail in this. There are two types of SIMS, it's called. Two types of SIMS machines are there. One is the static SIMS and the other is the dynamic SIMS. In the case of static SIMS, is mainly used for surface characterization. That means you basically study what are the elemental compositions of the surface, what is the molecular species that are available on the surface, what is the isotopic concentration of these species available on the surface. And surface means it is surface to, let's say, about 100 nanometers deep max. So this requires very little samples, and it gives us molecular and isotopic information. And this type of SIMS is done with what is called as a time of flight secondary ion mass spectrometer. Dynamic SIMS, on the other hand, is used to study bulk by continuously sputtering out the sample material So you are basically using a probe which is continuously, sputtering out material from the surface. So one can do the depth profile from the surface onwards to, let's say, a few microns or so. So it goes right into the bulk of the material. So it requires more sample, but it gives us concentration of elements from surface to bulk. So one can do depth profile analysis from surface onwards to, let's say, even up to 10 microns or so. And this is done with the help of magnetic sector. In the magnetic sector, the magnetic sector is tuned for one particular element in that matrix. And the probe basically goes on sputtering out materials. And in the process, it produces ions of that particular mass, which goes through the magnetic sector. And eventually, with time, you make a plot of time versus that element. So you can find out the depth at which these elements occur, or this particular element in the matrix occurs. So these are two different but complementary technologies. We have developed time of flight sims in our lab. So this is our time of flight sims machine. You can see that this basically is the primary probe, which is the 25 keV gallium ion gun here. And then this is the analysis chamber, and this is the time of flight analyzer. And on the other side of the time of flight analyzer, inside this vacuum chamber, is the reflectron. So ions are pushed from the secondary ions are pushed from the sample surface. They go all the way here and they reflect back with the reflectron, and the detector is located somewhere below this at this location. So a travel path of about 3 meters for the secondary ions is considered here. And this is the sample introduction mechanism. You have a load lock mechanism. So the analysis chamber is all the time kept in ultra high vacuum conditions, something like 10 to the minus 9, minus 10 millibar all the time. And this is pumped by 4 ion pumps. And then you have a load lock chamber to introduce the sample. And this is how the analysis is done basically. So in this case, the 25 keV gallium gun is pulsed. So once it is pulsed, so this is the primary ion beam, which is the probe here. This is pulsed. The 25 keV is made into a very, very small 1 microsecond pulse. So 1 microsecond pulse will consist of roughly 10 to the 6 ions. That is the probe size. And that impacts on the sample and produces secondary ions. And once the secondary ions are produced, the analyzer is now pulsed again to push those secondary ions into the time of flight reflectron, which has a path length of about 3 meters. So if all the ions are pushed with the same energy, then they will arrive at the detector directly proportional to the mass of the various masses of the ions. So so the detector is a very fast, high-speed microchannel plate detector, which has a pulse pair coincidence resolution of the order of 300 picoseconds. So that means you can resolve 2 pulses, 2 ions arriving at the detector within a period of 300 picoseconds. There are other features in this secondary ion mass spectrometer, which is the charge compensation. So you can study insulating surfaces. Sample stage is precise, so you can put several samples. In our case, we can put around 6 samples in the sample stage at a time. Sample holder, 4 to 6 samples. And we can also view the surface with a microscope. We can also introduce oxygen leaks, and there are several pumps in the vacuum pumps in the system, giving a base pressure of the order of 10 to the minus 9 millibar. So this base pressure is very important, because otherwise you will damage the surface, and this is a very surface sensitive technique. So even if you touch the surface with your bare hands, the surface is already damaged, and you are only studying whatever has been transferred from your hand to the
Excuse
sample.
me, Dr. Bhushan.
Yes, sir.
Okay. Can you please conclude? I think.
Yes. Yeah. So this is the mass resolution from this time of flight secondary ion mass spectrometer. You can see we can distinguish between aluminum and C2H3, which is a mass resolution of 3200. Similarly, we have mass resolution accuracy calibrated with the help of this sample crystal violet, and this is very accurate. And we also study different types of samples for the nuclear industry, such as natural uranium, enriched uranium, etc. We can also do secondary electron images of the sample. We can also do chemical imaging of the sample. These are secondary ion images. Somebody was telling arsenic in rice sample today morning. So we can do that. You can see this is the arsenic in rice present. So this is very heavily present on the eastern coast of India. And we can also do depth profiling. This is the polymer solar cell. And this is the indium tin oxide coated polymer solar cell. So it's actually very bending type of solar cell. So we can see what are the different types of elements coated. So basically, time of flight SIMS is basically used for molecular information. Sample material is limited. Localized information is required. Also, one can study many species of parallel interest, and it has got low trace elemental detection of 10 to the 12 to 10 to the 16 atoms. We have extended this to make a linear electrostatic ion trap mass spectrometer. So basically it works like one can continuously trap the ions here, and one can do. So because of time, I'm just rushing it through. So there is no mass limitation, no electric field, magnetic field. So it's a fantastic detector in its own. And then other developments are, we have made helium leak detectors, which is a single mass magnetic sector mass spectrometer. We also developed gas sensors for various processes, especially for the nuclear industry. Works by the process of selective diffusion of gases through a heated nickel membrane. And this is the case of a hydrogen sensor, which was utilized in Bhavini, PFBR, FBTR. And then we have also developed a hydrogen sulfide sensor. Basically, it works on the principle of thin film coating.
Bhushan, I'm afraid
yes,
we are running
I'm
out
just
of
finishing.
time.
Yeah. And this is the last slide, and developed some new type of hybrid ion pumps for ultra high vacuum. It basically consists of diode pump as well as a NEG pump. This NEG we have synthesized to powders. It's a very novel method of synthesizing this NEG pump. This doesn't require electric power supply or magnetic field, nothing. So it will work, once it is activated, it will work on its own without any power. And we also developed this is the earliest superconducting magnet. This is the latest superconducting magnets. And in conclusion, I will say that analytical instrumentation is like extension of our sensory perception. It requires the combination of all the three, probe, analyzer, and detector, to be fine-tuned to result in very high sensitivity and precision. It also gives in-depth understanding of materials and other samples, which helps us in taking informed decision about choice of materials to be used in the nuclear industry. Also, it reduces the failure rate because you have taken very good samples and you have understood the samples, and the choice of materials is very good. So it provides smooth operation of reactor systems and other instrumentation. So I thank Dr. Yusuf, Director of Physics Group, and Professor S. Hazra for giving me this opportunity to present some of our analytical instrumentation development in this August forum. Thank you very much. Thank you, sir. So any questions, you can email me also. This is my email address. You have my email address, so you can email me also. Or if you have some time, I can answer 1-2 questions.
Any question? So, yeah, but I think his talk is over. There is no question. Thank you very much for your presentation.
Yeah.
Okay, now we start this session.
You may log out. So we can change them.
I'm not able to hear you, sir. Maybe you can email the questions. I'll answer to you.
Yeah. Okay, thank you very much.
Thank you, sir. Thank you very much. Yeah.
Well, now we start this new session. We have 5 talks here, and I request all the speakers to stop after 25 minutes so that we can take some 5-minute questions answer. And I personally would like to the organizer, particularly Professor Satyajit Hajra, for giving me this opportunity to share this session. Our first talk is by Dr. Vishwajit Karmukar.
That's no answer. He shared his screen. Please unshare your screen. Hello. He has to answer. Dr. Bhushan, are you, have you stopped sharing?
Yes, sir. Yeah.
You have, please unshare. Okay, I try to make up some time. Okay. So it is a nice venue for discussing condensed matter physics activity, condensed matter physics research activity at SIMP in this audience where all the CIs and their students are participating in this international meeting. And also it is good for the students to have exposure to all the research activities all over the HBNI umbrella. Okay. So this over the years in the condensed matter physics division, we have acquired many experimental facilities like growth system. There is a mirror furnace. Mirror furnace for growing oxide single crystals. There are other sample making facilities like this is a 2 meter solution, and there are other facilities like so this 2-zone furnace where one can grow topological materials.
Computer.
Yeah.
Otherwise, you are not coming if you're online.
Okay. Okay.
Use this camera.
Okay. Okay.
You just look at that right.
Okay. Basically, so this is the growth system we are use. This is one example, and then we have device fabrication facility. We use mask aligner, all those things for semiconductor device processing, and also we use thermal evaporation system and mask aligner. There are wire bonder. A lot. These are the facilities in the division, and also there are pulse laser deposition, so growing thin film epitaxial system I'm going to explain, and there are characterization system like X-ray, and we have measurement system like magnetic measurement system SQUID, and there is a magneto-transmute system which is PPMS, and and there is a low temperature measurement system in millikelvin temperature dilution refrigerator. So, and on top of that, there are other low temperature facilities, and we can actually, with this, we can actually carry out various research activity in the division. In the material science aspect, we work on magnetocaloric system, magnetoresistive system, and intermetallic compounds. In the nanomaterials in core cell structure, low dimensional system, we work in quantum material, we work on topological material, wild semi-metal. And in quantum transport, we extensively work on quantum Hall system, and also we study this correlation phenomena, strongly correlation phenomena, theoretically by our colleagues, and where we look into many delocalization, half metallicity, superconductivity, etc. So in this talk, I am going to overview some of the activity here. So first is the zero or negative thermal expansion of materials. This zero thermal expansion material is very important. There are huge applications. So the few examples where in SINP that has been achieved. For example, this is a GD-PD boron system. It is a cubic system where at the center this boron is there, and if you shift this thing by half lattice and you make a change of this boron or carbon, if you dope with more carbon, then you actually create asymmetry in the, let's say, in the Z direction or X direction or Y direction, and that causes kind of a negative thermal expansion coefficient. But if you actually dope with 50-50 boron and carbon, then your lattice becomes symmetric and you don't see this negative thermal expansion coefficient. Always it is positive. So this is one example. There are another example of this zero thermal expansion system. So this is a hexagonal system made of hafnium iron Fe17. Fe17 system. So it is a hexagonal system where there are two sides where iron sits, which are basically weakly bound, and where this iron can be replaced with chromium. And if we actually at zero chromium level, we see it is a negative thermal expansion coefficient. As we increase the chromium doping, it's tend to go upward, and at x is equal to 1, then it's become zero thermal expansion coefficient over a wide range of. So this plot is T by Tc. So this is normalized. One is here where there is a T by Tc. But the point is over 13 Kelvin to 330 Kelvin, we see there is a no expansion of no thermal expansion of this kind of material. So another example, this is again a cubic system where rare earth platinum and boron actually sits at the center. Since platinum as a big atom, so this thing is in the middle, it actually distorts. The boron actually shifted, and which actually this boron actually basically okay, this boron actually vibrates in this direction, and that way this platinum they actually move in the vertical direction. As a result, so basically it has a unidirectional negative expansion coefficient. So in the other direction, so basically in this direction it has a negative thermal expansion coefficient, but in the other direction it shows always a positive thermal expansion coefficients. So this is one of the activity. Then the other activity is that so this is again a intermetallic system where basically in absence of long range magnetic ordering, magnetic entropy change is observed, which is the large magnetocaloric effect is seen. And to confirm this, the experiment is carried out, this neutron diffraction experiment is carried out at 60 Kelvin and 1.5 Kelvin. So if we subtract these two data, there are no magnetic black peak in the neutron diffraction experiment. So that confirms that there is no long range order in the magnetic ordering, but still we see that there is a magnetization, and this we say that this is because of short range magnetic correlation. This is the first time experimentally verified, which is theoretically predicted long back, and this work has been published in this paper. In another sample, so there is a bidirectional frequency-dependent susceptibility has seen in the AC susceptibility measurement. So in this sample, so this AC susceptibility, this the peak evaluation, it is like a glassy phase, and at lower temperature, as we increase, so this is a temperature axis, as we lower the temperature, so there is a magnetic ordering, and you have a completely temperature different temperature dependence. So that has been observed and reported. So now there is another work which is the Griffith phase. So basically, there's a long has been predicted by Griffith. So if you have a paramagnetic system, and in that there is a short range magnetic correlation, so it can show some magnetization and without long range correlation. So this is again an intermetallic. This is again an intermetallic sample where with lowering temperature, we see that this is H by M. So that means M is high here and it deviates from this curve. So as we actually increase the magnetic field, so basically it goes into the paramagnetic states. So this is the first time this Griffith phase actually observed in the intermetallic system. So now we are going to present the interaction-driven magnetism in rare earth, cobalt, and silicon system. So in this system, we see there is a HC quartz field actually increases. So this is a magnetic; it becomes magnetic, and then as you so which is normal. But as you further lower the temperature, this magnetization goes away. It becomes antiferromagnetic. So this has been studied by this mu-SR spectroscopy experiment, where mu-SR spectroscopy experiment, where at low temperature, so basically at high temperature there are cobalt-cobalt interaction, but at low temperature this rare earth and cobalt interaction dominates, so it become dominate over the cobalt-cobalt interaction, and it become antiferromagnetic. So this is the explanation we got, and that has been published in this paper. Now we are going to represent some work on a single crystal of oxide material that has been grown by optical float zone furnace. So at low temperature under magnetic field, it shows magnetization, but as we decrease the temperature, its resistivity increases. And in fact, at low temperature, it is very highly resistive. And with increasing magnetic field, this resistance jumps down and it becomes conductive. So to study the physics, this MFM experiment is carried out, where we don't see any frequency shift in the tapping mode of the MFM experiment, but with increasing magnetic field, their magnetic structure is visible. Okay, this magnetic correlation also from this MH curve, this is evident that there are finite magnetization, and this is the magnetic entropy change, where this is the magnetocaloric effect, and from that one can draw a phase diagram where ferromagnetic, antiferromagnetic, ferromagnetic. This is paramagnetic, antiferromagnetic, and paramagnetic phases. How actually they change the phases. All those things has been described. This work is published in this paper, and these are the publication of the students Deepak, under supervision of Professor Indranil Das. So this is another system. This is LSMO, but where strontium actually replaced with calcium. So again, this is in general, LSMO is a half metallic system, but when you actually dope with calcium, so there is a existence of Griffith phase. Okay, and So there again we see that under zero magnetic field there is a deviation from the 1 by susceptibility curve. As you increase the magnetic field, so it become paramagnetic, and in the so there is a collapse of magnetization AC. There is a scaling collapse, and from the scaling collapse one can actually determine the critical exponent of this Griffith phase and phase change, and the phase diagram is presented here, which is published in PRB. So now this is an interesting system where LSMO, which is a half metal and magnetic half metal, and barium titanate is a ferromagnetic material, and there is a stacking is made of that, and where this barium titanate has a different phases that has been reported and reported. So there are some problems. So basically with temperature, one can see there is a change of entropy due to change of entropy in the ferroelectric loop trace, and ferroelectric loop trace, like we see entropy change for magnetocaloric effect. This is electrocaloric effect, and in this system, by changing voltage, actually one can actually tune this change of entropy by voltage. So all this work is ongoing, and there are basically this stacking. One can see study the correlation and proximity effect in this bilayer system. Magnetization and ferroelectricity both coexist in this system. Now this is an interesting system. LSMO is known for half metallicity, and if we grow a thin film on silicon, then it will have a spintronic applications. But the problem is, if you grow on silicon at high temperature, so there is a silicide formation. That become resistive at room temperature. So to improve this thing, so there is a two-step process is introduced. First, you grow at low temperature some LSMO with PLD, and then you grow rest of the thickness by high temperature. And you see this is AFM image, and you see this is the kind of a metallic resistivity of the thin film. And from squid measurement we can see there is a nice magnetization curve, and this magnetoresistance also support this quality of the sample, and that work has been published in this paper. And this is the TEM data is taken in our institute, and we shows very nice epitaxial layer in the system. So this is some way good going that for this spintronic applications at SIMP. So now we are going to quantum transport in quantum Hall system. So basically on top of the liquid, if there is, we perturb in two places, there are standing wave formations. So we know this is kind of an interference, but same thing, electrons is a particle, but in quantum limit, so these behave as a wave, and in quantum Hall boundary, people have seen these quantum oscillations, quantum interference effect. So this is our motivation to study, and there are linear quantum optic approach. One can actually do quantum logic gates out of this kind of system or this kind of architecture, I would say, and one can actually have a quantum electron approach to make quantum logic gates. So we, in this direction, we have done some progress. So we have shown that at nu is equal to 1, we know the electron actually carries the current, and it has a conductance E square over H. So E square over H. So the thing is that, so that means from H1 source to D1, there will be only one edge mode is going. So only one edge mode should connect H1 to D1. But experimentally, we have demonstrated that there are actually 3 edge mode with fractional charge E by 3, and its conductance of this edge mode is E square by 1/3 E square by H. There are 3 modes. So that means there is no more electron. So electron electron become quasi-particles. So even after the discovery of 150-year discovery of electrons, now we see that under magnetic field it behaves completely different, and there is a new venue for research even with the electron optics with their electron quasi-particles. And in this work also we have demonstrated that how we can do quantized partition. For example, from S2 there are two modes by putting the gate. So basically we can make transmission of these two edge modes which reaching to detector D2. But if we deplete this thing and make the filling fraction less, then we can actually deflect and connect this thing to D2, that we can connect the outer channel to D1. So that way all permutation combination, whatever channel we want to excite and what we want to read out, everything we can control. And that work has been published in this paper. So in this thing also we have demonstrated that this edge modes has a long equilibration length. So that means for quantum information processing, the first requirement is that it should not interact with other things. So in this system, this since equilibration length, we measure of the order of millimeter. So now the thing is that if we make a device something like nanometer length, so basically it will have a very less dephasing, less decoherence. So this is a nice venue for to accommodate many quantum logic gates, and in this direction we want to work in future. So now in the same quantum Hall system, we actually, since equilibration length is high, we have to know all the thing how this edge mode behaves. So this is an example. If we go at filling fraction nu is equal to 2, there are two edge mode. Okay, this is a red one, which is the outer mode. The blue one is the inner mode. When we have a filling fraction 2, that means electron in red channel, which is, let's say, upspin, and blue channel, the electron is downspin. So they propagate. So if they propagate, their spin is opposite. So then they don't talk. But still there is a nuclear demagnetization, all those things, they talk. So that's why there is a higher equilibration rate for nu is equal to 2. But the thing is that if we change this filling fraction, go to, let's say, other filling fraction like 4 by 3. 4 by 3 is like 1 plus 1/3. So 1 is electronic state, 1/3 is fractional state. So it's a quasi-particle, it is not electron. Then automatically if you take a overlap integral, this overlap integral is suppressed. So that means we see there is a suppression of a scattering rate, and we see enhancement of equilibration. So this is the conclusion that dissimilar quasi-particle actually induces suppression of relaxation rate, that has been published in this paper. Now we talk about our activity in graphene heterostructure sensor. So this is a very simple. So now a lot of fundamental study is going on with graphene using a very small dimension graphene devices with Scotch tape. But here we talk about CBD grown monolayer transport on silicon dioxide. This is, you see, this device length is something like millimeter. So basically these are industry friendly process. You don't have to use EBA, electron beam lithography system. So what we actually, the architecture is the monolayer graphene, then there is a dielectric, then there is a functional material. So if there is a chemical absorption in the functional material, there is a change of surface potential modulation. And this surface modulation actually part of this system. There is a voltage drop across the dielectric. At the same time, it doped the graphene and it changed the Fermi energy. So basically our master equation of the device is surface potential modulation is the change of Fermi energy in graphene and the change of potential drop across the dielectric. So we made a device with palladium, Al2O3 and graphene for hydrogen gas sensing. So why we are taking this sensor? If we actually, this graphene has a lot of free pi bonds. So if we directly deposit palladium on that, so actually it it binds and it introduces a lot of scattering. So basic graphene quality actually degraded. So we have this dielectric layer, and it's proved to be, it protects the graphene transport properties. And you know, hydrogen is very important for our future generation fuel. So, so this is a simple comparison. Simple comparison. So this is our graphene heterostructure sensor, and this is the sensitivity, how it actually, with increasing hydrogen gas sensor in air, how it increasing. And this is a MQ8, this is a SN2 oxide sensor, but without heating, because we want a mass producible, reliable, without heating, room temperature operation, this kind of devices. So you see, it actually, this our graphene heterostructure sensor is better than MQ8. Now, if we consider if palladium actually deposited on graphene directly, we see the 2% mobility with 2% gas, we see a sensitivity of 8 or 8 at 3%, and where at 3% sensitivity, we have sensitivity higher. So basically, we are studying this thing and how to improve. So that way, since we don't have to heat the thing, it is mass producible, it could be a reliable next generation sensor. And also in this thing, we can actually use various functional material which can selectively actually absorb the chemical precursor. That can be in the same way, it can work as a sensor. So this is the physics part we are actually developing. So now we come to the theoretical activity. So okay. So this is a this is a system of let's say two-band system, or let's say bilayer graphene, or stacking of graphene and HBN. So here, so we have considered a Hubbard model, and there is a this when the interaction energy U and the interaction energy U and the gap is comparable, then there is a particle hole symmetry breaking either by doping or next neighbor hopping, which actually causes different phases of metals from different phases, from pure metal to there are different ferri, ferro, and half metals, all those things. So that has been reported in these papers. So now, again, in this system, when the interaction energy and the gap in the system is much greater than your hopping, and hopping, and your T, which is the hopping rate, and T is the kinetic energy, which basically is a measure of the frustration in the system. We see then U by delta is more than 1 and sufficient frustration. This correlation, there is a there is a correlation, and this gives to superconductor in this regime, and that has been published in these papers. Now, there is a dichalcogenic system, just DIAC2 kind of thing. So this is a charge density wave insulators. And in this system, if you can actually put disorder like copper intercalation, so basically using this attractive Hubbard model, one can show there is a coexistence of charge density wave and the superconductivity. So that has been reported in this paper. Now there is a many body localizations. So basically, when you talk about localization, we know Anderson localization, so there is no interaction. So if we actually turn on the interaction. So the theory understanding is that in presence of interaction, as long as it is your chemical potential remains in the chemical potential is pinned in the localized states, so it remains in the localized states. And in other work, in presence of long-range interaction, this many-body localization remains. But if there is a long-range hopping, it delocalizes the system. So these are the kind of studies are going on, and the last thing is that in the many-body localized states, this long-range random interaction, okay, it actually changes from a ergodic phase to non-ergodic extended phase, which is poor metallic. I would say it has a slow dynamics, and that has been published in this paper. And this in the single particle green function method, this low range dynamic. So anyway, so this thing Arthi can explain better. Okay. And in this many-body localized system, so basically there is the occupancy of particle and non-particle. So in this thing, if one can study the quantum dynamics, then people see there are there are slow dynamics and memory effect in this system, and that has been published in this paper. And in this talk, we have contributor Professor Indoli Das, Professor Chandan Mujumdar, Professor Arti God, and myself. And thank you for your kind attention.
Very nice presentation. Maybe some quick questions. Yeah. Is
ice.
any other question?
What is that one? Huh?
No, speaking microphone. Yes, to let us thank speaker for the lesson. Now I request Dr. Nirmal Mukhopadhyay.
Jonathan. Okay. So apart from thanking the organizers, I should also thank my division members for giving me the opportunity to represent surface physics and material science division in this forum. And what I was trying to put the things that what is our focus as a whole in science of this division. So that is what I was stuck that point, if we want to talk about the research of areas of SPMS division, then what should we say? So then I coined a term that physics in low dimension. So that is the term probably I feel that fits very well in to explain our divisional activities. But this looks like a slogan, but I will explain that how we are contributing in this area. And then definitely it is a big area, but we are a subset of that area and how we are contributing in that direction. So what we do that for purpose? So we grow materials having different structures, like nanostructures, two-dimensional structures, thin films, and nanoparticles, and all these things, and arrange them in different organization and study their structure. So this is a growth of those materials is a big activities in our division. And then we characterize those materials, like we can do with a structural characterization, microscopy, spectroscopy, and there are other imaging and other things which we do regularly to characterize those materials so that we know what materials we are working with and how we can tune the materials to have a better property. So that purpose we do property measurements, and we have some instruments which is for measuring the transport, optical or magnetic properties of those materials, and we do it regularly in our division. And also we have two beam lines. One is in Indore and another is in DST sponsored program in Japan, where we developed a beam line which is being used for those materials, not only for the SPMS division, but also for the other Indian users or Indian scientists and universities. So then we can say, okay, picture somewhere. So the aim of the division is to grow materials in confined geometry, characterize those materials, understand the basic properties, and in some cases, what for its application as energy materials. So that is the basically brief of our activities in SPMS division. So these are the faculty members of our division. So, and you can see all the names and with the email address. So if you feel to contact anybody, you can. And this is the web page that we have. So first, the growth facilities. So we have different growth facilities. So I divided it into two components. And one is for soft materials, like we can deposit in using polymer spin coat. Mostly the polymers and long chain molecules we deposit there. And then we have a very good facility of Langmuir-Blodgett film depositions unit. And then, and we are quite expert in depositing this Langmuir-Blodgett film. And then we have a organic MB unit where you can deposit some organic semiconductors, or make the device with there, because there is a inorganic part. So you can combine these two and make a device using this unit. Then we have hard materials, we have molecular beam epitaxy unit, we have sputtering unit, then EV evaporation unit, and then also nanocluster deposition unit. So these are mainly used by different faculties for their research for the hard materials. And as a characterization instruments, we are quite expert in structural characterization using X-ray scattering techniques. So for that purpose, we have two X-ray facilities in lab-based facilities. One is we call versatile X-ray diffraction instrument. Another is a high resolution X-ray reflectivity. So HRXRD and VXRD we call, and both are working very well. This one is quite old, but still it is working.
and this one is quite new. New means 5-6 years. So these are the two X-ray facilities that we routinely used in our laboratory. And then we have two beamlines that I said before, that we have a GIXS beamline at Indus 2 RRCAT, and we have an Indian beamline at Photon Factory KEK Japan, where we can do all the structural characteristics. Then for microscopy, we have a 300 kV scanning transmission electron microscopy. And then we have a SPM cum triboscope or AFM we can use. And then we have a booster angle microscopy attached with the LV deposition facility. So we can see the monolayer using the booster angle microscopy and do a lot of optical studies. And there is a background, there is a big TM sample preparation facility that you can see that all students are there. And Vishwarup Satpathy is an expert in that direction. Then for spectroscopy, we have ARPS unit, XPS unit, XPS UPS unit, and Raman spectrometer. And also there are SIMS and UVs, because I have not put everything. I am just trying to minimize the slides so that I finish it in time. And then we have this surface plasmon enhanced photonics using cathodoluminescence. And recently installed low energy electron microscopy facility, which is a first of its kind in India. And it was installed by Professor Krishna Menon. Then we have some property measurement facilities, which is a variable temperature electro-optical property measurement unit. And then we have a probe unit, where you can measure some dielectric property of the materials which you have grown in other units of the growth facilities. So next, this is the most important part, that what are the research highlights in this SPMS division? So I cannot cover all because this is my limitation, and also there is no time. So I have chosen some part, and I am presenting as a work of some faculties. So if you have any specific questions, maybe I cannot answer, the faculties can answer to that. So one thing is that Professor Tapas Chini and Vishwarup Satpathy is doing is a plasmonic behavior of nanoparticles. So what they do, they develop some nanoparticles which have different morphology. And that morphology contains something like nanoflower or nanocube. And the way they develop that, they have some kind of a angular end. And that is actually enhancing the plasmonic behavior. And that is one research area they are working on. And then on top of it, you can, they are also involved in core cell nanostructure for application of surface enhanced Raman scattering and interaction of energetic ions with solids or nanoparticles. Then this is the work from Professor Tapas Chini. So where I just told that they have developed this nanoflower thing, and then they studied with a cathode luminescence. So cathode luminescence is basically you focused electron beam on top of your material, and then there will be luminescence enhancement where there is some kind of this kind of angles, sharp angles are there. So that's what they studied, and they found that there is that those tips are actually talking each other, and when they talk each other, there is a split, and when they don't have this kind of talking of these two tips, then electron fields, then they have a single field. So this is a simplest basically explanation that you have started developing this talking between two tips, and there is a split in the luminescence spectra. And this is a continuation. This is a nano cube where they have started with. And then you can see that the plasmonic, they have simulated some the plasmonic functions. And then they have shown that there's the enhancement of plasmonic behavior at the T age of this tip. And this is done with a concave nanocube, which is this one, gold particle on silicon substrate, and they have demonstrated some features which is explained here. So we have a big facility which is a transmission electron microscopy, and this is one of the best instrument in India that Professor working on. And these are the various features of that TM. Next, I move on to another topic, that is photovoltaic materials, where the materials are grown in SINP lab, and then you can study the structure, and you can study the electrical properties, optical properties, and thermal properties, and try to correlate between structure and property, and then tune the structure to have a better property. So that was the aim for this kind of study. So, and you can, here you can see that gadolinium arsenide gas, basically Al gas or gas buffer layer, and then you have a set of these materials, Al gas materials, a superlative structure. You can see the same picture. And by doing this kind of thing, Professor Bhunia measured the reflectivity. So this reflectivity and this refraction, I guess it was measured in Indore, right? Yeah. So Indore beamline. So that actually tells you that how good is our beamline for having some kind of structures. So this is a multi-layer reflectivity from that sample. And then we also have this rocking curve, which is at the diffraction peak. And that of this multi-layer structure that was measured in Indore beamline, SINP beamline. And then what he has done, he measured the photoluminescence as a function of temperature. And what he has found that the band gap is actually decreasing as a function of temperature. So that's the work I am presenting here, and there are several publications from this work. So that are also he has done this carrier transport and recombination dynamics of indium arsenide, gallium arsenide, submodular quantum dot near. So this has an application as a photo detector. So he has developed those quantum dots and then was trying to extract the responsivity as a detector. So that he is showing that as a function of energy, how these detectors are sensitive, and how as a function of voltage, so how this response of this detector is changing. And of course, the structures are we are doing this thing in laboratory and synchrotron experiments. And then we are measuring those properties in our lab to have a better correlation. So this is another work by Professor Krishna Menon, which is basically explain the area of his field. So what he has shown that there is you can think of three different areas where is the crystal structure and morphology, and there is the electronic structure and the magnetism. So, and there is obviously overlap. And so he is working on these three aspects of a material. And for that purpose, I will show that he has taken different materials, but for this kind of material, he used lead and lean. So basically the structure and morphology, he is using lead and lean facilities. And for electronic structure, he is using ARPS and XPS facility, and also some synchrotron radiation-based absorption spectroscopy or photoelectron spectroscopy, magnetism, the XMCD or XMLD kind of measurements he is routinely performed and expert on that. So First, he has a very beautiful lab on angle resolved photoelectron spectroscopy. And this is used to study the surface electronic bond structure of crystalline materials and also the elemental characterization of material, then the structure using lead and the integrated facility so that you do not have contamination. So basically you can grow your sample there and then do the study. And these are different materials that he is working on to explore those kind of properties and those kind of structure. And then this is the new facility that he has developed, that lean facility. So it's a microscopy, backscattered low electrons, and you can also attach beam facility, but probably it is not there yet. And then you have a spatial resolution of 5 nanometers. So you can image your surface with a spatial resolution of 5 nanometers. And it has the fast imaging ability. So you can tune the surface and at the same time you can measure it. So that's a very good facility I recently developed. And these are the different materials he is working on to understand the subject. So this is another area. I don't know why this thing is not going. So research on high K based thin film devices. So here it is a high K materials. So hafnium oxide, zirconium oxide, and vanadium oxide, niobium oxide, cerium oxide. Kind of all these materials we are depositing in our laboratories. And then we are fabricating metal oxide semiconductor devices using these oxides and also measuring the transport property of those materials. So these are some examples of the data that I told you that we have a nanocluster deposition facility. And here it was on oxide films, those nanoclusters were deposited. And as you can see that the loops open up as you deposit different type of nanoclusters, different size of nanoclusters and different. So you can see this, though in no nanocluster, there is no open up of loop, and also this switching properties is changing. So next is another material that I have started working on. It's a 2D perovskite material, and it has a very vast application. And we are developing, we have prepared this molecule, PBBR4, this perovskite material, and we have done the XRD on this flex. So this comes as a flex because this is a 2D perovskite material. So you can see this thing. But when you do this film as a flex only, then it is showing a splitting in the PL speak. But if you basically solute this thing and then deposit as a thin films, then you don't see this splitting. So we are working on this new area we have started. And more data are coming up. So maybe next meeting we can show more on this subject. So next topic is the soft matter, because I have to now covered the area of soft matter, hard matters. Now I want to move to the area of soft matter, where basically Professor Suthit Hajra and myself is working mainly. And then we have organic semiconductors, where I have shown that we can grow and investigate the structure of in thin films of this organic semiconductor. And accordingly, we can tune the molecules to have a better orientation, so that our orientation and ordering to have a better electron structure. So that's our aim. So so for that purpose, we need to have a structural information, and accordingly, we have to tune the sub molecules to have a better electron structure. So major challenges in this program are tuning the structure, that is the molecular orientation. So sometimes these are symmetric molecules, but sometimes these are kind of rod molecules, and I'll explain some data. And there is also that metal part of the semiconductor. We are depositing it on silicon or some metal substrate, and then the ordering near that surface area. So we have to tune this alignment through molecular orientation, and that is our aim. and the film electrode, film metal interface. So all these interface we have to study properly to understand the area, understand this transport behavior, charge transport behavior. So a combination of techniques like AFM, X-ray reflectivity, or small angle, or some other spectroscopic technique. So these are actually useful tool which is available in our division. So and which we are working on. So this is an example of that work where this is the UPS spectra of the samples deposited on the substrate. And then what they are trying to, because these are not symmetric molecules. So these are kind of rod molecules, and they are trying to deposit the, measure the as-casted sample and then thermal annealing after the effect of that thermal annealing to have a better ordering. And what the temperature will be to have a better ordering temperature. So this kind of studies they have done with a beautiful analysis scheme and shown that the density gradient, how these density gradients are changing as a function of handling temperature and also as a function of layer thickness. So this is another example of pi conjugated polymers, so P3HT, and then these molecules were deposited just as it is, basically in the solution aging method. And then we have predicted this kind of structure. But if you do then some post-deposition treatment, then we can have a better ordering, and then that better ordering gives you some better electronic properties. And also we have done here that it was mixed with stearic acid. Stearic acid is a fatty acid, so we and then we can spread it on water surface, and then we can deposit those molecules, and we have a better order structure on this in this way of growth of this molecule. So this is a substrate organic interfacial electronic structure. So I don't want to go much details in that because I don't have time. So this is another molecule that I am working on, that is a CuPC that we are depositing using e-beam evaporation technique. And then you can see that these are kind of a columnar structure over a thin film and forming, it's like a rod-like growth, and then it is forming the film. So you can see that this is the diffraction peak is coming if you have a GIXRD. We can produce beautiful layer structure, and you can see the diffractivity profile and the corresponding fitting. So basically the gap is between these two molecules, and this is the higher electron density region. So you can beautifully model this kind of structure, and you can fit the reflectivity. So we can exactly talk about how the molecules are oriented in this film. And our aim is to produce some organic fate or organic spin bulb structure using this. Yeah, okay. 2 more minutes. So, okay, so I will quickly go over. Now, this is another area that I am working on quite a long time. So this is a organic, this is proteins or some lipid molecules, so interaction of proteins, liquids. So what we do, we spread those molecules and add those proteins or exogenous molecules in this, and then do reflectivity, GID, and all these things to understand the structure. So this is one example. So DPPC monolayer, and then we have added some spectrines. So these are different kind of spectrin. So one is a brain spectrin, another is a blood spectrin. And we have done some systematic measurements to understand how this, one case it is a little flexible, another case it is a little rigid, little rod-like structure. So how these are actually affecting the structure to so that we can talk about the cell function between brain cells and the blood cells. So these are the last few slides I want to quickly go over. because we have developed SIMP beamline at Industrial Arcade. And we are regularly, now it is users operation has started. So everybody is welcome to submit new proposals and do the experiments. So we can do diffraction experiments from powder sample, environmental condition at high temperature and low temperature. Low temperature facility is having some little problem, but we are working on it. And also we can do very good reflectivity and diffuse scattering at different conditions that I have shown you just a few slides back, one example. And this is the SIMP beamline components that we have, beryllium window, DCM, monochromator, and all. And finally, the goniometer, where we mount the sample. So this is the schematic view of that image of the beamline. So we start with a pretty big beam, as you can see, 88. You can see it's a visible. It's a basically normal camera. So we start with something beam like a centimeter or so, and then we end up having a beam which is 2 millimeter by 1 millimeter. So we have a very good focusing instrument which focuses this big beam into a spot, and that enhance the intensity quite a bit. So that is the beauty of our beamline. And then we have a Indian beamline, which is a funded program from DST. And these are the facilities that we are available in this beamline. All of these are working. And these are the pictures of different facilities so that we have all and working properly.
Quantum dot of indium arsenide.
Yeah. No, this for online.
So that you are showing a shift into that is a towards the gallium arsenide. So I would be more interested to know that what happens to the indium arsenide response instead of the gallium arsenide.
These are some monolayer quantum dots. These are not Starsky Kasparov quantum dots. So what the results are to show as a function of monolayer coverage. So as you go towards less coverage, so less quantum dots, so it shifts towards gravity. No, yes. Yeah, it's Indian Ocean quantum. Indian Ocean quantum dot. That's not right. Yeah.
You're talking about this one, right?
Yeah, but then it is actually gallium arsenide. Yeah, I think gallium arsenide is around 1.4 somewhere. Yeah. But then if you see this red one, which is shifted most towards the lower energy, means it has higher fractional coverage. So the dots are more. And if you see the right side, it is 0.4 monolayer coverage. So this is also higher energy. Right.
Yes.
Oh, sorry.
So we talked about the PPPR for best having perovskite. Comment on the stability of this perovskite.
Yeah. Okay. These are stability means with time.
Yeah.
No, it is quite stable. Quite stable. I will say more than a month. Okay. So we are working on. We are thinking of solar applications, but we have not yet in that stage yet. So we have just done, we have got beautiful structural information. So we have done in last week, I have done synchrotron experiments. So I don't know. I have to do that measurement. So I have done only the structure at this point. Yeah.
But it has got very good optical properties also.
Yeah. It has very good optical properties, which I have not shown. So room temperature, and also it changes color with respect to how you are actually thin film, powder, and this thing. So these all three have different colors. It is 3.02.
Yeah.
3.02 is the highest peak. Yeah.
And
Yeah, thank you.
Now I request Dr. B.U. Rajashekar. One thing, I have to leave in between when I have another meeting. I request Professor Indranil Das to continue.
Well, it's so into. You have your Mac, right?
Yes.
That is
the.
okay. It is
okay.
okay.
Best thing is on Mac transfer is the PDF.
Yeah.
Okay. Yeah.
Yeah, taking a private.
Otherwise, the PPT is in there.
Yeah, no. And it's CMB, SNB, UB. It is already there, no? Yeah. This one, no? First of all, let me thank Professor Hazra to give an opportunity for giving an opportunity for a talk presenting some work here, and also thank Professor Milan Senya for not starting my time yet. Your time has started. Okay. So I am presenting on behalf of Institute of Physics. This here. Institute of Physics is a small institute, probably lesser than a division of BRC or even comparable to a division of Saha Institute. So we have basically 4 major groups in Institute of Physics. One is condensed matter theory group. There are about 5-6 faculty members there. So they work mostly on mesoscopic systems, superconductivity, topological systems, strongly correlated systems, and some of them are in statistical mechanics and soft matter, including including biophysics. And then we have an experimental condensed matter group, which also comprises of about 6 faculty members. The accelerator, ion accelerator based research, then sensors, nano bio interaction, nano functional materials, thin film heterostructures, 3D, 5D quantum materials, tailoring of superconductivity, 2D heterostructures, van der Waals systems for optoelectronics, resistive RAM, etc. And then there is the conventional band structure of strongly correlated systems and topological insulators. We have also theoretical high energy physics, which most people, they work on standard model, Newton physics, cosmoparticle physics, quark gluon plasma, string theory, quantum information, and so on. And then a small group of 1 faculty member of experimental high energy group. And they are part
of the mega science projects related to CERN and so on, and INO, Indian Neutrino Observatory, CMS experiments and ALICE experiments and so on. And then there's theoretical nuclear physics group, which is focusing on structural properties of finite nuclei, nuclear equation of states, and so on. Coming to the experimental facilities, this is the biggest facility of Institute of Physics, about 25 years old, 30 years old, or more than 30 years old, I would say. And this facility is working. So it's a 3 million volt particle accelerator. So we have two ion sources, multi-cathode SNIC source for metallic ions and so on, and alpha TROS for the gaseous ions, helium. And we have this is the particle accelerator, 3 MB pelletron accelerator. There are 6 beam lights. One is for RBS, Rutherford backscattering experiments. The other day, someone was mentioning this is one of the only facility in India currently working on Rutherford backscattering. Then we have an implantation beamline, and which is also very, very popular and used very much. Then there is surface science beamline and micro beamline. And at 0 degree, you have the nuclear physics beamline, which was also used by SANP for a long time. And that is mostly now used for proton-induced X-ray emission experiments. Except 2 beamlines, AMS beamline and micro beamline, all of the beamlines are working. And there are lots of works, which are more than 700 papers came out with more than 50, 60 PhDs came out. During 1990s and 2000, there were a huge lot of activities related to that. It has come down a little bit, but still it is going on. So that's what the status of this. So ion beam, we have, apart from the 3 million volt particle accelerator, we have a 40 keV negative ion implanter also, which is also working, which is also used very lots of users we have from all over the country. And then there's a focused ion beam, 30 keV focused ion beam. And mostly the work which is being done is on ion beam mixing and implantation and so on. Then there is a ripples, nanodots, E-beam lithography, and 3D nanostructures. For the characterization, we use, most of the people, they use Rutherford backscattering and elastic recoil detection analysis. Ion channeling was one of the experiments which we were doing. We were real experts at that time, ion channeling experiments. Then proton-induced X-ray emission. There's a new accelerator with electron cyclotron resonance based ion source, which is not functional fully, but it is coming up. So this is the pelletron accelerator picture of that, and then the beam hall with the 6 beam lines. You can see it's an old picture, but this the beamline hall. There are many other facilities which has come up. And then we have other ion beam facilities. It's a focused ion beam facility we have. Then the one which I told you about, 40 keV negative ion implanter, that is the low energy negative ion implanter facility. And then the ECR ion source is also shown here. And then there are low energy ion beam induced surface nanostructuring unit. So we have a very highly used high resolution TEM. There are lots of uses for that. And then the microscopy facility, we have SPM, scanning probe microscopy, and focused ion beam FESEM we have. Then AFM also we have. Then thin film growth facilities, we have lots of them these days. One PLD is right connected to the accelerator surface beam line. And then the DCRF magneton sputtering. Then we have the variable temperature scanning tunneling microscopy with MBE related to that. And that's also working. And then there is one more PLD there. And then UHV E-beam evaporation facilities also. We have that. Then high resolution X-ray diffractometer we have. Magnetic property measurement, that is SQUID based VSM we have. Then PPMS, physical property measurement systems also, that's another system we have. And then there are some other facilities like X-ray photoelectron spectroscopy is there, Raman spectroscopy, confocal Raman spectroscopy is there. Then there is angle solid ultraviolet photoelectron spectroscopy, which is basically for angle integrated also. We can use that. So now I am coming to the work of people. So those were the facilities. Now various groups means one faculty with students. Okay, so this is Shikha Verma's group, means Shikha Verma plus students. So Professor Shikha Verma works on mostly sensors for detection of arsenic, of course important for this region, Eastern, and mercury, then the glucose sensor, photocatalysis and photoabsorption, resistive random access memory devices, nanobio interactions, which she is probably one of the experts in doing that. That is the DNA absorption, and DNA as a sensor for toxic elements like mercury and so on. So some of the results are also shown here. Arsenic detection using 3-APPA, that's an organic molecule, aminopropylene, some acid. Okay. And then we some of the publications. The publications are given here if somebody wants to refer to that. Resistive random access memory devices, then visible photo catalysis. Then we have DNA as a sensor for mercury. This also is very good. And then arsenic pollution in Delta water, Bengal Delta water, which was done in collaboration with Kalyani University and Grenoble and so on. Then glucose sensor. These are some of the results which. And then we have Professor Tabobrada Som. Tabobrada Som works mostly on ion beam mediated defect engineering and so on. So there are most of the works are about cold cathode electron emission with ultra low turned on field from gold nanoparticles and gold self-organized gold nanofacets. And there are lots of activities, especially from this group, and for anti-reflecting surfaces and so on, and with the faceted surfaces and the nanoparticle organization in those facets and so on. And growth facilities, you can see some of them: gallium arsenide, indium phosphate, silicon, and germanium. And he also uses the high resolution X-ray diffractometer, and we have the PLD system. And then we have some of the results from ion beam facilities from the same group. So it's a low energy ion patterning facility, integrated ion patterning facility, and so on. Some of the works are having which were really appreciated. Great things like patterns and so on. That ECR-based ion beam facility, which is coming up, is also there. Then we have works from Professor Devaganda Samal's group. So mostly this work is on designing of quantum materials, and that is complex oxide thin films and heterostructures. Correlated topological magnetic materials, spin orbit coupled 3D, 5D quantum matter, heterostructures, and so on. And then low dimensional magnetism in layered hybrid organic, inorganic materials. One thing which I had noticed, which will be very interesting, was this tailoring of superconductivity with artificially engineered heterostructures. So some of the works were really good. And this is the PLD system with read and so on, which is connected to the ion beam laboratory beamline, surface science beamline. This is the growth facility which mostly he uses for growth of complex oxide thin films and heterostructures. And some of the publications are here from that group. And see that. And then we have Professor Satyaprakash Sahu. He works mostly on low dimensional systems, van der Waals systems, and so on. So 2D materials and heterostructures for optoelectronic applications, and resistive random access memory and neuromorphic computing. Some of the one paper which was recently came as the cover page of physical chemistry, Journal of Physical Chemistry, was that top-gated MOS2 WS2 heterostructure that was highly cited. And then some of the facilities which he has, most of these are grown using photolithography in a clean room. Then we have other facilities, especially you can see that some of the MOS2 work has been done, the corner which you have. So resistive switching, there are some results from that group. So this is about graphene oxide, barium iron oxide, random access memory. So this multi-level switching can be achieved by combining graphene oxide with this hybrid device configuration is useful for high-density data storage applications. So some of these works, and then so the publications also have been given. And then coming to some of the activities which I have been involved. So we are working mostly on the topological insulators using, it's about studying the electronic structure using photoelectrons. So especially band mapping. This is some of the recent works on topological insulators. The canonical topological insulator is the Vi2AC3. And as we can see that you have the Vi2AC3 at the gamma point, we have the spectra coming, RPS spectra coming. And the bulk valence band is here, bulk conduction band is here. There's a gap between the two, but the surface state bands, that is the topological bands, they have the linearly dispersing bands are there, that is gapless. And if you check, this is of course done in the lab itself, and if you check the thing, take the cross section and look from the top, what you have is the Dirac cone. This is the Dirac point, of course, because these are the Dirac fermions leaving on the linear band. And it's a circular one, and the Dirac point you have, it will be like a dot. So, and this itself change of photon energy, and then itself will tell you that this is coming from surface states. And one can see that if it is taking at the nature of these bands, studied using various photon energies and then the various polarizations and so on. If it is, there is this picture goes somewhere else. So there is the Fermi surface of another compound that is bismuth, antimony, SBT, and this particular, again, these are topological insulators. Because of the crystal structure, what we have is the Fermi surface, which is like a flake-like Fermi surface, which otherwise should have been circular in normal case. And then we have some of the other works is about, so the topological insulators mainly are characterized by the Z2 time invariant Z2. Can either be 0 or 1, and if it is 0, it's a bulk insulator. There's nothing interesting in that. It is trivial. And if Z2 invariant is 1, it is topologically non-trivial. That's a topological insulator with you have non-degenerate spin states and gapless states. They are further classified. If it is between 0 and 1, it can be a strong topological insulator or a weak topological insulator. And BISC is something which is, the other one which I showed was BI2SE3. BISC is something which even calculations of our collaborators and so on, we have been finding it to be a good candidate to be a weak topological insulator. Understanding weak topological insulator is also equally important, like understanding the whole. It's a weak topological insulator. We have the Fermi surface again. It's a circular Fermi. This is a Fermi surface which is mapped. Then the circular intensity pattern, which shows that the warping parameter is lambda is 0. And we have, this is the spin polarization of the weak topological insulator. But from the picture, you can see that this in S polarization means the photoemission is done using S polarized light. And this is P polarized light. So there's an intensity difference between this arm and this arm of the topological states. Whereas in P, if you use P, this is stronger and that is weaker. So the difference between the two intensity of the two in two polarizations, this asymmetry of the spectral weight reveals the important information about the spin orbital spin texture of the surface state bands. One certainly it's spin non-degenerate. So in one arm you have the electron with spin up, and in the other arm it is electrons with spin down. And that varies as we change the polarization or as we vary the energy. You will see that there's a change in the. So this is with the energy one can see that it's coming. This is one means their intensity is equal. Intensity of minus k and intensity of positive k should be equal in the MTC profile. But as you see, as you increase the energy, you will see that the intensity changes from one arm to the other arm. And this is something which is very important in the case. Yeah, since he has gone, I can take 10 more minutes. Okay. Okay. So that I don't know. I just finished. Yeah. So that's what it is. Yeah. It depends on the interaction of the polarized light and the spin of the electron, because the two arms are spin non-degenerate. Light is also polarized.
Maybe I can just.
Yeah.
Yes,
Not very difficult question, Indrani.
If you have one room temperature measure, you get explain.
Okay. Yeah, actually, some of the measurements were done at Electra. Okay, especially with the spin polarized, the S and P polarization. The other ones, which are beautiful Dirac cones and so on, they were done in the lab only. But in the lab, what we have seen is most of the topological properties, they don't change with temperature. So we have not tried this thing in the synchrotron also. Most of them, they show the same. Temperature doesn't have much of any role. I can also do that. Yeah. Even Krishna can do it. Oh, okay, below 100K. Yeah. Not in my lab. No, for fresh surface of a single crystal. Yeah, certainly. Yeah. So there's no growth facility, but if it is single crystal, I can make a fresh surface by either the post technique or by this tape, Scotch tape technique or anything. You can, because we don't use, there is an argon iron gun to sputter, clean it, but we don't appreciate that anyway. So cleaver is not there. There's no crystal cleaver because that also is a mechanical thing, doesn't work very well. The best technique I have seen is put a post, some torsil glue with a post, and then kick the post, and this will be cleaned. Okay. Yeah, the vacuum is very good. And as you go down in temperature, of course, the rate of adsorption will be more. So it will get contaminated more. But the one thing I can say, unlike superconductors or strongly correlated other systems, topological insulators are not that prone to the surface contamination. So it's pretty okay. But of course, our measurements in the lab, we are finishing within the RPS measurement will be finished in about an hour or so after cleaving. And in synchrotron, it will be only half an hour. And vacuum is low minus, good minus 11 kind of thing.
There is no questions.
And you have put. Yeah, extensively.
Good afternoon. So at the outset, I'll thank organizer for giving me this opportunity to present some work which has been done at our center at IGCAR. We have a strong group of condensed matter physicists at material science group. I would like to present some of the work which is being periodically done here. And I have, during this presentation, we have seen that most of the work in condensed matter physics, whatever is done, is being done throughout the country. SINP, IOP, Bhubaneswar, BRC. So most of the things will be common when we go in condensed matter physics but one thing is there, the aspects of the research at different centers are different. So I'll give the flavor of the work which is being done in one of my division. It is not working. Huh? You know, these are all members of my group, my division, who are working in this area. I'll quickly go to the, sorry. What are the important activities which has been pursued at in my division? These are the proper, one by one, just I will narrate it. And after that, I'll focus on particular activities and I'll give you the flavor of the work which has been performed. So, as I have already told, our main theme is to carry out the research in condensed media at extreme conditions, maybe very high pressure, very high magnetic field, very low temperature, and even very high temperature as well. So the systems which we have been studying are superconductors, strongly correlated heavy fermion systems, then topological insulators and topological systems, and then intermetallic systems, ferroelectric materials, multiferrites, and many intermetallic systems. In this talk, I'll try to present some of the work, just to give the flavor, how we can tailor the ground state properties when we bring two long range order together and try to marry these two together and looking for the offspring which is going to come out from these things. Many times what we'll see, this long range order will interact among themselves and try to bring out some novel properties which otherwise is not possible in a given material naturally occurring. So this is a lab-made materials which can be tailored according to the need. So this is the property which I will just show you. In this pre-ground state, I will just try to see that how they are evolving. One is superconductor, other is topological insulator, and other is a CMR material in which there are various kind of the magnetic ground states which are existing. So this I'll just narrate it. But other activities which are going is our magnetocaloric effect. Already many of speakers have told. I do not want to give all the details about those things, but we have chosen new materials, but particularly rare earth selenide, which has not been explored much. And we have found that one of the material like rubidium selenide has given very high AMC values. Now many work is going on at double perovskites to see that how magnetocaloric behaviors in these systems are evolving. Other activities of our division is to study the glasses. These are another systems and a lot of activities are going on in these systems. Basically, some of these borate glasses, they are also used for our other activities. In this, we'll have many facilities to probe lattice Raman spectra as well as Brunel spectroscopy on these material and try to find out their properties. Many explosives also we have studied, but there is a strong activity to carry out or synthesize novel systems by subjecting the material at very high pressure and high temperature and trying to find out with the phase. So
that also includes study of the phase transitions at structural level as well as electronic. We have synthesized several such materials of F electron tunneling intermetallic systems under high pressure and high temperature conditions. We have also studied many uranium intermetallic because uranium is our workhouse because we are at the Kalpakkam where all the three types of the reactors are existing. So uranium is workhorse for DAE. We have to study their properties in details. So that activity is also going on. Another is a soft condensed matter. We are also having a full programs in which a lot of studies are going in these areas. We have photonic hydrogel magnetic system that is used for extraction of the uranium in aqueous solution. Then we have fabrication of functionalized opal and inverse opal photonic crystal to develop photonic hydrogel to monitor and extract heavy metal ions. And we have developed one technique called holography optical tweezers, by applying which we can pick up the single molecule and study its properties. We have detailed program on pump probe spectroscopy and quantum computation and entanglement problems. So just I will now go through the topic which I have chosen to present here. Here I'll just give the glimpses of some of the activities which has been pursued and going on. Here I'm going to put into two parts. In first part, I have chosen high temperature superconductors, which has got coupled with a magnetic material, which is emanating from the manganites. Mostly these manganites, which we have chosen for these studies, are three types of. One is NSMO, then PCMO and PSMO. First materials, some of them are having a very different kind of, one is a ferromagnetic and there are various types of the antiferromagnetic. These interaction of this antiferromagnetic material with the superconductivity is very important because they have a varieties of the ground state, and we have to see that how these ground states are evolving and interacting when they come in a direct contact with the other long range ground state. So next part will be on the topological insulator, which will, for that we have chosen yes type of superconductors like BCS superconductor and try to see how their properties are getting modified. Now just everybody knows how proximity works. Here two materials have been brought in a very close intimate contact. Then what will happen? They will start sharing their properties with each other. So for example, you have a normal and superconductor. The moment you put them these two together, then what will happen is from the normal state, the superconductor will, the Cooper pair will try to penetrate inside the normal material and try to make the interface also superconducting. Similarly, the free electron will try to go in these things up to the small length, coherence length across the interface. And this will give rise to various kind of the ground state because it can also make the whole normal state to superconducting state. There are various types of the interaction which has been done. But I'll go to the next one, which is more interesting is when you put instead of normal, you put the magnetic material and see that how ground state properties are changing. There are a variety of phenomena which can happen in these things. As you have seen, the superconducting order parameter can go to the ferromagnetic layer, and ferromagnetic layer will start strongly interacting, not like the normal one. Normal one will not be that much violent attacker on these Cooper pairs, but ferromagnetic is antagonistic to the superconducting order. So their attack will be much more stronger. Like many such circumstances have been seen where system, even a yes wave pairing is getting changed to P wave pairing like situation has been occurred. They are getting modified by the ferromagnetic layer, and many such a system will come where superconductor and magnetic system both will coexist together, and those systems will be employed for many spin trucks and other device making. I'll not go into further details. These are the several consequences which can occur. I do not want to spend much time on this one, which can happen when you are marrying these two ground state and trying to look
what type of the new phenomenon or exotic phenomena is appearing. What is happening? It has gone out. Got closed.
One.
Already saved or not?
Yeah, it is. You're sharing. Share.
So better I'll use the mouse. So now I'll come to the what will happen instead of ferromagnetic if you have topological insulator. So there are varieties of the phenomena which is expected to occur, like I have already, when we start discussing the result, I'll just see. Here also it has been seen that even a BCS superconductor, this Cooper pair when penetrated inside the topological insulator, they are getting modified. There will be admixture of sometimes S and P types of the superconducting wave. And this kind of many exotic phenomena has been reported. And also this superconductor can change the topological insulator into topological superconductors. And those topological superconductors are becoming a host of Majorana state, which can be employed in supercomputing and other phenomena of spintronics. I will not go into the details. Our aim is just to have a basic understanding of these phenomena. Now, first part, I'll just start. This is with magnetite. Magnetite has various types of the magnetic ground state. One is very ferromagnetic, that is not very much interesting. But if you see the antiferromagnetic ground, there are several types of A to G. You can see that there are several arrangements. I will just concentrate only A, B, and C, these systems, and try to see that how this magnetic ground state is affecting the superconducting ground state. Just I'll see the A type means this AB layer will be ferromagnetically coupled, but C layer will be antiferromagnetically. Similarly, all these variation has been shown. Just I'll come to the one of the systems which we have chosen. This is YBCO systems with and heterostructure is made YBCO and neodymium strontium and manganese oxide. In this is a type of antiferromagnetic material. NSMO is a type of antiferromagnetic material, which has it's a TN at 265. And another one we have the canted type of antiferromagnetic materials, which is has its Neal temperature 270, and canting in ferromagnetism is taking place in 50. So two ground state it is there. One is antiferromagnetic, and further lower it goes to ferromagnetic. So we'll see that how these systems are modifying our property. You can see that the spin is arranged here in ferromagnetic. AB plane is like a ferromagnetic, but along the C they are antiferromagnetics. Here it is just ulta. So you know why we are choosing YBCO, and both are the perovskite material and they are oxide. So making these heterostructures is much simplified rather than choosing some intermetallic systems. These are the phase diagram of NSMO. I have chosen this concentration. This is for A-type antiferromagnetic ground state, and this is the C-type antiferromagnetic ground state. This material has been chosen. Now I'll see the two effects, proximity-driven two effects. One is the static, and other is a dynamic effect. I'll just show first the static effect. These are the layer which has been prepared in a different geometry. This is the normal geometry. Then this is spin injection geometry, and this is the tri-layer where spin can be injected. So this I'll just summarize the result here. You can see that we have first, second, the A type of antiferromagnetic systems and its interaction with the YBCO, I am going to present here. In this scenario, what is happening is due to presence of various thickness of NSMO layer we have chosen from 40 nanometers, it has gone to 200 nanometer, and YBCO thickness is fixed at 80 nanometer. What we have found, this is the final result. The final result, you can see that there is no change in the Néel temperature of NSMO, but TC has drastically changed. This has been dropped at a very low value at low thickness, and higher thickness it is just low, coming very close to the YBCO. YBCO is around 90. It is coming around very close to that one. But this is what is not expected. This is unexpected result, because with the thickness increase, we are expecting that would have interacted much strongly and TC would have decreased with increasing the thickness. But it is happening just opposite. TC has decreased rather than increase. TC has increased rather than decreased with increasing the thickness, which is unexpected. But why it is happening? That reason you can see when we do the magnetization measurement. If as the thickness is increasing, you can see that this magnetization values are increasing. Thickness is decreasing, magnetization is increasing. Means this there is, as such, in A type interferomagnetic, we don't expect any magnetization value to occur. But what is happening is because of the lattice mismatch of NSMO with the substrate, there is a strain enhancement. This strain enhancement, what it has done, one side of the plane, it has just tried to put any strain. Because of this strain, magnetic moment has developed in AB plane, because AB plane is ferromagnetically aligned in A-type interferomagnetic. That started giving the ferromagnetic contribution, and because of that, there is a drastic decrease in the TC when thickness is decreased. Now we did the dynamic effect. What we have done, we pass high current, keep on passing the current, so that some of the spin, because we know that in these CMR material, magnetite material, are highly spin polarized materials. They are called half metallic half. So because of the large degree of spin polarization, if you pass high current, some of the spin polarized electron can go inside the superconductors, and they have more deleterious effect on superconductivity rather than just normal injection of the normal exchange field. So you can see that in YBCO, when there is a single layer, there is very little change in the superconductivity when you pass the current up to this much value, current density we have passed. But the moment we have started in NSMO, we have seen that decrease with the current. If you see, it is 10 to the power minus 5. But once you do in bilayer, it is 10 to the power minus 2. Means 3 order of magnitude suppression is there in the TC when spin polarized electrons are injected inside the superconductors. Now I'll come to the second topics, which has been on C type of antiferromagnetism. In C type of antiferromagnetism, you can see that canting is taking place at some temperature around 30 Kelvin. And here a very nice phenomena has been seen. There is a reentrant superconductivity has been seen when it has been married with YBCO. You can see that there is a transition, first transition, and then again superconductivity vanishes when this canting is on, this ferromagnetism. Then superconductivity get killed. Then there will be competition between magnetic order and superconductivity. We know that superconductivity order becomes very much strengthened when you go lower and lower temperature. At that time, superconducting order wins over the magnetic order, and superconductivity is restored again. Then next, we have then the thickness dependent. How with the thickness, this superconductivity is changing. We have seen that this process get almost relaxed when you go to 200 nanometer of NSMO layer. I do not want to go much details of this one. Just to summarize whatever work has been done, this A type of antiferromagnetism, decrease of the TC will be from 88 to 82 Kelvin you have seen because of strain enhancement. And if you go a thickness more than 200, 160, then strain is getting relaxed. So there is not much decrease. But in the case of you compare with the C antiferromagnetism, C type of antiferromagnetism has decreased from 88 to 73. So C in type of antiferromagnetism more deleterious effect it has compared to the A type. Now I'll go to another system. This is, we have chosen the BISCO and then PCMO. This is another, this is a ferromagnetic ground state and then superconducting ground state. Here, this is the BISCO. BISCO occurs in the three different phases, and they are 2201, 2212, and 2231. This is the formula. N is the copper layer number. So they have different TCs, 20, 80, and 110. Maximum TC has been seen in the BISCO. Now I'll just. So you can see that we have prepared the superconductor thin films, and in thin films, we can see that at STO, LAO, and MGO, the maximum TC has been observed on the STO, and which has less width of the transition. And this we have chosen for the proximity effect. This system has been chosen for proximity effect with the PCMO and PSMO. And here we have shown all the properties we have tabulated, which has been achieved after doing the magnetoresistant measurement on these systems. And this report has been published in this journal. So now I will introduce the PCMO, which we have chosen to make the heterostructure with these systems. They are PCMO. You can see that this is the composition which we have chosen, 0.5. It has a charge order insulating phase at 250 Kelvin, and then at one C type of antiferromagnetic arrangement is there at 170. C type antiferromagnetic arrangement has been shown in this figure. What will happen? And second one, PSMO, this is a ferromagnetic things. This composition we have chosen, which has a ferromagnetic transition. TC is around 300 Kelvin. Now we'll see that what happens when this is, we have chosen these two material itself and try to find out the proximity effect. One is a charge order material and other one is a ferromagnetic material. In this you can see, I have tabulated the result here. They are of different thicknesses. We have found even at the room temperature, their CMR effect, considerably good amount of CMR effect has been seen even at the room temperature 31. The material which is thinner one, which has given the larger CMR value compared to which was a thicker one. Now I'll come to the proximity effect between the manganites and PCMO. One of the result I'll just show. These are the structure which has been used for doing the measurement. And we have done detailed magnetotransport and magnetization and magnetic susceptibility measurement. I'm just showing one of them. So what has been observed is, just 5 minutes. No? 5 minutes, I'll try to conclude. So in this, you can see that this material has shown that superconducting transition is getting suppressed when they are coming in the contact of PCMO. At the same time, there is a reduction in anisotropy. Now I'll go to the part 2, topological insulator, where we have chosen the niobium, molybdenum nitride, and this is coupled with bismuth selenide. You know, topological insulator, most of the time it has many introduction has been made. Topological insulators are a quantum, new quantum states where there coexist bulk band gap as well along with the surface state. These surface states are protected by the time reversal symmetry. So they are quantum mechanically protected. Therefore, both exist simultaneously. Bulk is a insulator, but the surface is a metallic. These are the two things which are inseparable in true topological. It can be, if it is already all the properties of the insulator has already been discussed. I do not want to give more details. Just want to say that this is spin polarized. More important is this the state. Whatever is the gap states are there, they are they are called the surface state, and these states are protected by the spin time reversal spin symmetry. You can see that there is a pair, electron is existing in spin pairs, and just like similar pairing is there in the superconductor, which you can see there will be these are called, instead of Cooper pair, they are called Kramer pairs. So now you'll see that how these Kramer pairs and Cooper pairs will interact when they are brought together. And these are the various features. These are the system which we have chosen, business selenium. I'll not go into detail. I'll come to the result. You can see that what happens here when this is the measurement has been done at the superconductor side. It shows the superconductivity occurring. And you see that topological insulator. The moment it comes close to the TC, it shows upturn, just close to it. Just its physical property has got changed. Generally, it should have shown, would have gone like this. But because of interaction with the Cooper pair and this kind of these two dissimilar ground state, there is a change in the nature of their transport properties. Now, I'll just skip these things. I'll show the various things. This is niobium nitride with niobium nitride. This is a pristine one, and then this is getting married with BSS, like the molybdenum nitride and niobium nitride. Final result I'll just show in this one. Here you can see that because of this niobium nitride, and this is their niobium nitride and niobium nitride molybdenum nitride, and then this is heterostructure, and first one will be this is your single layer, then heterostructure, single layer, heterostructure. You can see that there is a change in the TC accordingly. TC get depressed when they come in the contact of the topological insulator. This work has been reported already. Now, more clearly, you can see here, just one example I have chosen. You can see that this is the niobium nitride single layer. The TC is 7.7. The moment it comes to the BSS, there is a huge drop. It goes by 4 Kelvin. Recently, this work has been Superconducting Science and Technology. They invited me to do this work within 6 months and report in the focus of superconductivity, and this result has been recently published there. Just I'll summarize these results. We have given just a flavor of how ground state property of two interacting long range orders can be modified when they interact strongly, and new exotic ground state can be formed. With this, these are my collaborator who has contributed in this one. I'll just stop here. Thank you very much for your attention. Gayatri. Everything has been done. Now, this PLD says we have. This is a pulse laser deposition has been used for oxide one, and for this metallic sample we used sputtering system, DC sputtering and magnetron sputtering systems. No, mic is required. You have to get connected. Neil temperature effect, I have not shown all the results. In one of the results, it has modified, and because of some small controversy, we have not reported that result. But still, we are working on that system. So I have not presented because I have not published that result.
You are doing the proximity effect and a lot of excess of uranium. A lot of uranium based heavy superconductor, and which is UF superconductivity.
UG.
Superconductivity is mediated by magnetic fluctuations.
Uranium, germanium is there.
So on those materials, my interest is studying this proximity effect. I hope it will be derived than non-mediated superconductivity and this the S wave. Now that's the key.
It's a very good suggestion. It's very good suggestion. I'll definitely take it up. Very good suggestion. Thank you.
Supercurrent, when it penetrates the ferromagnetic layer, what is the penetration length?
It is up to some nanometer length, not more than 10 minutes.
What is the use of making, say, 80 nanometer, 100 nanometer? So doing that, if you make a multi-layer and make it more interfaces, and you can get what.
Actually, what happened? There has been a report. There is an unconventional nature of the proximity. What happened in some material? It has been seen. It is not only getting limited with coherence length. Suppose like in topological insulator, what they are telling, though your coherence length be limited to a few hundred of angstrom or something. But what will happen? They are spin polarized state already in topological state. They themselves start carrying this information to the longer distance. So that's why we made a longer, large number. Ultimately, we have found that has not helped us. We have again made it to 3 nanometer and 5 nanometer. There we have seen proximity effect. So we are in impression that whether we are able to carry it for longer one. But there we have seen the decrease in the TC, not because of proximity, but because of some other reason. That reason was some when if it takes, the grain connectivity, another problem has given those things. So ultimately we have to make a smaller one only.
Thank you again.
Thank you very much for your attention. Give whatever I have.
একটা মোবাইলে দেখলে
আনমিউট করতে ওই তো ওটা দেখা যাচ্ছে তো আনমিউট করা যাচ্ছে
মিউট হয়ে গেছে
Dr. Govindraj, can you hear us?
Just unmute your microphone.
Can you please unmute your microphone?
তোমার আনমিউট করা রয়েছে
তো এই হয়ে আছে না
এই তো ঠিক আছে হয়েছে
Can you hear us?
Can you start now? No, but we cannot hear. বলে যাচ্ছে he is unmuted but he is not already unmuted. Everybody জায়গায় অরিন্দম দেখো তো ওখানে
বলছি
everybody
দিচ্ছি না। প্রেজেন্টে তো আছে। Dr. Govindaraj, can you hear us? We cannot hear you. Dr. Govindaraj, we cannot listen to you. No, now again mute. He's muted. He should unmute.
Hello, sir. Yeah. Are you able to hear me, sir? Now? Hello.
Share your screen.
Now we can hear you. Please try to share your screen.
You are able to hear me now?
Yeah.
We can see you now. We can see you now. You share your slides. But suddenly stop.
Again unmute. Unmute হয়ে গেছে না?
কথা বলছি এমনি কথা বলছো না কথা বলছি তো এখান থেকে এই যে এখানে আর ওখানে হ্যাঁ
But he should unmute here, no?
Unmute.
He's unmuted. He's muted actually. You see?
Voice earlier. Okay, 1 minute. I will try. I will try. இங்க unmute வரணும். Unmute பண்ணியாச்சுப்பா. Sir, is it okay now?
Yeah.
Unmute பண்ணியாச்சு. Yeah, you are able to hear me?
Yes. Yeah.
Okay. Thank you. Okay. Yeah, let me check. Okay.
Okay, we start. Try to finish it.
Good evening to all of you. I will be talking on the insights of defect studies in some novel materials. Okay, the scope of the talk is defect studies. I will the talk is divided into 2 parts. First part I will be covering mainly on some reactors, defect studies, some reactors, and the second part will be on the insights of defect studies in novel oxides. Okay. And we have the major facilities like, for example, accelerators, 1.7 MeV accelerator and 400 kV accelerator. These two are used for dual ion beam mode. Ion implantations using dual ion beam mode of implantations. So we implant heavy ions and also light ions together for simulating the conditions of defects as produced in reactors due to fast neutrons. Okay, so then these are studied by microscopy, high resolution RBS, channeling, and so on. Okay, the accelerators are the forming the main part of the tools which produce defects, and we also have a very strong section working on computation and modeling of defects and associated properties, working on wide varieties of problems. And we have another section called defect study section, using mainly nuclear techniques for addressing defects in materials. We are studying open volume defects, positive annihilates with electrons, and 2 element kV annihilated photons are produced, and this is mainly used for producing for getting the information about the defects. Okay, and we look at the positons are obtained by means of beta decay, and the time elapsed between the emission of the gamma ray associated with the emission of positron due to beta decay, that is 1.28 MeV gamma photon, and the moment the positron enters inside and annihilates with electrons, 2 element kV gamma photons are produced. and the time elapsed between these two, the detection of these two gamma rays is called the positron lifetime. And the positron annihilating with electrons should emit two photons which are at 180 degree, and the energies of each of the gamma rays should be 511 plus or minus delta E, and there will be a there will be a Doppler shift due to the momentum of the electrons with which the positrons annihilate, at which is at rest. Okay, so therefore, if you look at the delta E or the angular correlation, that is whatever the deviation between 180 plus or minus delta theta, if you measure delta theta or delta E, that is called as angular correlation spectroscopy or Doppler bonding spectroscopy respectively. And these are also used for studying defects. And shown in the schematic is briefly, like for example, that this is the Doppler broadening of the 511 kV annihilated photons, and we look at the broadening, and which implies the Doppler shift of the photons, and by means of looking at the contribution from the core and the wing, okay, the peak corresponds to the annihilation of positrons with the valence electrons, that refers to the annihilation of positrons with valence electrons, that annihilates that is referring to the peak, and the core annihilation, the annihilation of positrons with core electrons is due to the contributed by the wing portion. Okay, by means of looking at for example, if I create a vacancy, then there will be a core electrons will also be removed along with the ions. So therefore only valence electron, there will be a enhancement in the concentration of valence electrons. So positron annihilating with valence electrons will be much more. So therefore there will be a peak enhancement in the peak at the cost of the wing portion. So this is called as the S parameter. So I will be referring to that in the course of my talk. And then there is also a depth resolved Doppler bonding spectroscopy. Here the positron beam is taken, and this is taken out of after moderating the fast positrons, and only a very small fraction of positrons is accelerated, and then made to annihilate at different depth in the sample, and we get the depth resolved Doppler broadening. Or we are also involved presently in setting up a depth resolved positron lifetime spectrometer, where we will be using the pulsed positron beam with RF electronics. And we also have hyperfine techniques for studying defects. We use time differential pentatriangular correlation, and also the Mossberg spectroscopy for studying defects in a detailed manner. So these are all the most of the main techniques that we use in our lab for studying defects. And we quickly go through the two stages of the talk. Like first phase, we will be just quickly covering the defects in reactor materials, and the second phase will be on the defects in novel oxides and so on. So the first study is on the TDPAC and positron lifetime studies in helium implanted zirconium hafnium. Here we look at the nucleation growth of helium bubbles in zirconium hafnium. Interestingly, this study, the 40 MeV alpha particles were implanted to 100 APPM dose at VCC Calcutta only. So therefore, I have just taken this first study, and the TDPAC shows that there is an offset in the zero offset in the time differential spectrum. So which implies the vacancy loops, that is talking for loop of defects that are present in the HCP matrix. So giving a local structure of FCC. So therefore, there is a zero offset that you observe in the first spectrum, and this refers to the striking fault loops. As hafnium is of same size as that of zirconium, so there may not be a very strong binding of defects and so on. But on the other hand, the positron lifetime spectroscopy results, if you look at, there is the positron lifetime the lifetime spectra is resolved into two lifetime components, and with the lifetime tau 1 and tau 2, and the intensity of the defect component is I2. I1 plus I2 makes 100%. So that tau 1, like for example, till 600 degree Kelvin, there is a this tau 1 remains constant. That is understood to be due to helium vacancy complexes, and it remains quite stable. And the tau 2 is understood to be due to positron annihilating with vacancy cluster, and it's close to 500 picoseconds. It remains constant till the annealing temperature of 500 Kelvin, beyond which the He vacancy complexes dissociate, and the helium goes and decorates the vacancy cluster, and this marks the onset of the nucleation. And beyond 700 Kelvin, there's a growth of helium helium that are trapped at vacancy clusters that grows into voids. That grows into helium bubble. Okay, so this marks the helium bubble growth. So this interesting nucleation growth of helium bubbles are investigated by Positron electron spectroscopy. And recently there have been many defect studies that are carried out in RAFM steel, reduced activation ferritic martensitic steels, and here the depth resolved Doppler broadening studies have been done using Positron beam. And here you see that this spectrum refers to the lifetime, S parameter corresponding to the defect-free sample. And the moment you take the irradiated sample with helium, there is an enhancement in the S parameter. And if you keep annealing, if you subject the sample to isochronal annealing studies at different temperature, there is a decrease. There is a decrease in the S parameter, and it gets restored to the defect-free site. So shown is the variation of the S parameter as a function of temperature. For example, the samples which are subjected to high dose, you see that beyond 600 Kelvin there is an enhancement in the S parameter, and in the low dose case, this happens only beyond certain very high temperature. This is what this has been published in. There again, we look at the effect of hydrogen also on the growth of helium vacancy cluster. This is also very interesting. This refers to the S parameter corresponding to the as a function of energy, which marks the depth of the annihilation of the positron and this marks the positron beam energy. So therefore, the positron beam energy is enhanced to different energy, so that positrons are made to annihilate at different depth, and S parameter is measured. And shown is the black dotted thing refers to the unirradiated sample, which is just decreasing as a function of depth. And in the case of sample subjected to hydrogen, and this is the variation, and in the case of helium, the S parameter is very high, and it also decreases as a function of depth. So then, this is also shown as a function of annealing temperature. What happens is also shown here. So such kind of interesting studies as a function of recovery of defects is also done. So in the last case, we discussed the high temperature ion subjected to irradiation. So here self irradiation is also done, and in the case 1 without pre-injected helium, and the case 2 refers to the Fe irradiation with pre-injected helium. Show the S parameter variation as a function of positron beam energy shows a remarkable variation. Like for example, this shows the unirradiated sample, and for helium implanted sample it is very high, and the defect is shown to recover as a function of annealing temperature, that's shown here. And in the case of helium implanted sample, you see that there is a helium bubble growth. So therefore, there is, after decreasing to at 673 Kelvin, there is again an upshoot due to the bubble growth. So this is also an interesting result that we have obtained using the positron beam based Doppler broadening spectroscopy. And also we use high resolution RBS for studying, like for example, the iron oxygen vacancy interstitial loop and so on. So this also high resolution RBS is also latched with the 1.7 MeV accelerator, and extensive measurements have been done on chromium clustering, and other interesting studies have been done on the chromium and oxygen 18 implanted iron and oxygen implanted Fe chromium, where there is a interstitial loop and so on. So now we quickly go to the Mossbar results on the Eurofer. Again, it is similar to your RAFM steel kind of thing. So here in that Eurofer 97, we see that so when we subjected to different annealing temperature, beyond certain temperature, 1273 Kelvin or so, there is a M23C6 phase formation, which is marked by the appearance of singlet in the spectrum. So here we look at the variation of the mean hyperfed field as a function of temperature. Once that singlet phase is formed, the mean hyperfed field decreases. So this is again marks that recrystallization, grain growth, and other transformation can be studied by means of this Mossbar spectroscopy. And again, we have taken another system called the nickel 50, cobalt 15, Fe35 alloy, which is proposed as a magnetic switch in fast reactor. So this is here we take this system, and then we have carried out the Mossbar spectroscopy measurements at different temperature. You see that the hyperfed field decreases with the increasing temperature, and around 895 Kelvin there is a Curie ferromagnetic Curie transition from ferromagnetic to paramagnetic transition, marking the appearance of the singlet, total singlet. And we again go back to the room temperature measurement, where we see that again we have got the singlet, and here there is no other impurity phase marking any non-magnetic phase and so on. Therefore, this implies that the phase stability of this alloy, and this is a magnetization result that is shown here. And again, we have taken this system independently and then subjected to annealing at 750 Kelvin for 5,000 hours to just simulate the rugged condition that exists in the reactor. And we see that almost, see this technique, the result of this technique shows that, because it's very powerful to study, like for example, if there is any other phase gets formed, and if any low hyperfin field component gets formed also, it will be able to deduce, since no other such defect components or any singlet phase is formed. So this Mosber spectroscopy results established that this is a this is a well-known alloy that can be used for this purpose, this magnetic switch. It gets qualified to be used as a magnetic switch in fast reactor. Okay, then interaction energies of defects in BCCFE, that computation results, and these results are also published in physical review materials recently. So he has taken, the colleague has taken, he has observed, he has reduced the point defect formation energy, vacancy solute formation energy, binding energy, computed in FE matrix with different solutes. And this is again, they have also, the computation group is also involved in atomistic models of glasses and so on. So now we are again going to the second phase of the talk, like for example, defect studies in novel, that is materials. Okay, here we have also addressed the phenomenon of negative thermal expansion in zirconium tungstate. And here our results, like for example, we have done, we have carried out time differential pentabangular correlation studies and at different temperature, and we found out interestingly that there is a distortion of Z06 octahedra for the first time. And because this is a well-known negative thermal expansion material, and as a function of increasing temperature, there has to be a contraction. Isotropically, there has to be a contraction. But for the first time, we have deduced by means of the TTPSC studies that we interestingly deduced the Z06 distortion. So what is the interesting result that is shown here? And these two, MQ2 and all the other higher frequency components, are due to the defects, and the revolution is shown here, as can be seen in the slide. This is what is the interesting thing. And not only that, we have also, like for example, we have used the simple expression of the quadruple frequency varying as the 1 by r cube. That is, with that we could also deduce that we try to deduce the dl by l, that is increase in the expansion, increase in the lattice parameter divided by the original lattice parameter, and as a function of temperature, and we find that there is a negative slope, and then which gives a value of the 10 to the power minus 5 Kelvin inverse. So which is referring to the coefficient of thermal expansion, which is negative, and the value is also somewhat closely matching with the literature result. Okay, then we have also applied time differential pentabangular correlation for studying the interesting colossal magnetic resistance, that is local structural and magnetic field variation in colossal magnetic resistance oxides like lanthanum, strontium, manganese oxide. Okay, so here we are deducing two distinct hyperfine components. So the one important thing is that if and only if hafnium substitute the manganese side, the super transfer hyperfine field will be very high, and we will in turn observe very high magnetic field, magnetic normal precession frequency, which is the case that we observed here in this system, very high normal precession frequency, which implies that hafnium substitutes manganese side. And not only that, we have obtained a very interesting linear correlation between the normal precession frequency and the quadruple frequency. Like for example, as I was telling you earlier, two distinct hyperfine components have been deduced, and like for example, the normal precession frequency corresponding to site 1, that is a fraction of hafnium atoms substituting manganese side. So there is the critical exponent based on the variation of the normal frequency as a function of temperature. We deduce the critical critical exponent, which is close to the 0.13 or so. And in the case of side 2, which refers to after substituting the ferromagnetic side, the variation omega L2 varies as a function of temperature as shown here, and with this we can deduce the critical exponent based on this expression, which is deduced to be 0.38, so which is close to the ferromagnetic, and which this value is also lying very close to the Heisenberg three-dimensional ferromagnetic system. Okay, so then now from here we have got the interesting linear correlation between the normal precession frequency and the quadrupole frequency, which directly implies that it establishes a very strong spin orbital coupling. So this provides an experimental elucidation, which this experiment is a very short range probe technique, and which is very powerful enough to deduce this kind of strong information. That is, like, for example, there is a very strong spin orbital coupling as established by means of TDPSS technique. So similar case is obtained in the case of LCMO, and here you see that the slope is much higher, and which is also because in this case the alternate distortion will be much more significantly higher as compared to that of LSMO. Now we move on to the defect study in CO2FeAl. CO2FeAl is a full Husserl alloy, and with a spin polarization coefficient of this is a half metallic system having spin polarization, but unfortunately it exhibits a spin polarization coefficient close to only 0.5 or so. It is theoretically it is expected to be 100% as it's a half metallic system, but the question is why. So why the value is so low? So we try to address this study by means of Mossbar spectroscopy, and we have also taken this system as prepared. Then we have also doped deliberately lesser percentage of aluminum, and then the magnetization results show that see in the case of as a reference system, this like for example the magnetization value is slightly higher than that of as dictated by the Slater-Pauling rule, and in the case of partially doped, that is a 0.95 doped aluminum CO2FeAl, we see that there is a slight decrease in the magnetization, which also establishes that there is a disordering. And with the Mossbar spectroscopy, we found that there is close to some 30% of A2 type of disordering that is present here in the system based on the hyperfine fields that are deduced. Okay, in the case of defect-free situation, we get hyperfine field to be very high and so on. So then with respect to defect and with respect to aluminum rich zones, ion atoms associated with aluminum rich zones, we get a singlet and so on. So this is very interesting, and the interesting result is that so here we in this system we deduce about 35% of the probe atoms are associated with A2 type of disordering. So that is present in the system, therefore leading to very low value of much lower value of the spin polarization coefficient. And here also we interestingly see a variation of linear variation of hyperfine field with isomer shift, which implies that the linear correlation between the valence electron contribution and the effective magnetization in this Husserl compound, which is directly illustrated by this result, because the Husserl compound are expected to show this, okay, because these obey the Slater-Pauling rule. And we move on to BaFeO3 multiferroic, which is at multiferroic at room temperature, and this is antiferromagnetic and ferroelectric. Okay, the bulk BaFeO3 may not be so interesting because it's antiferromagnetic and but ferroelectric, but the interesting thing is that magnetoelectric coupling is significantly very low. Okay, that is the point. And in the case of nano BaFeO3, what happens is that there is a large reduction of the FeO-Fe
Can you
bond
finish
length.
it in 5 minutes?
Hello, sir.
We are running quite late. Can you finish it?
Yes,
in
sir.
5
I'm
minutes?
just I'm quickly completing. Yeah. So in the
Okay.
case of nano BaFeO3, so there is an interesting magnetization, that is it exhibits weakly ferromagnetic component, unlike your bulk BaFeO3, which exhibits antiferromagnetic thing. And there is an interesting magnetoelectric coupling that we observe in the case of nano BaFeO3. That is what is shown here. So here we apply the magnetic field also and see that like for example the 723 Kelvin annealed sample, we interestingly see that like for example this shown here is the variation of polarization as a function of electric field, And here, with and without the application of magnetic field, shown are the results corresponding to sample annealed at 723 Kelvin. Here you see that there is a significant variation in the polarization graph as a function of the application of the field. While if you anneal the sample to slightly higher temperature where there is a grain growth and the defects also get, you don't see that result. Like for example, there is a we move on to the last result. Like for example, there is a strong trapping of the cubic iron oxide nanoparticles in zeolite that is established by means of this Mossbauer result. And here are shown are the XRD patterns corresponding to Fe3O4, and you show that the particle size is very, very low, of the order of 4 nanometer and so on. So here the Mossbauer results, we quickly go through that, and then we anneal the sample. Like for example, this one shown on the left panel refers to the Fe3O4, which is not introduced in the zeolite matrix. On the right hand side, this is dispersed in zeolite matrix, and it is very bound, strongly bound. Like for example, you see that after annealing at 623 Kelvin, you started seeing that there is a interaction between the magnetic Fe3O4 particle and that coescents. Therefore, there is an onset of the growth of the 6-line pattern corresponding to the onset of the ferromagnetic ordering. Otherwise, it is remaining superparamagnetic particle. So in the case of 823, in the case of zeolite bound particle, you see that it is still remaining as a doublet. That is, the paramagnetic signature is retained. That means the particles are very strongly trapped in zeolite matrix. So this Mossbauer result has clearly shown that there is a very strong trapping of Fe3O4 nanoparticles in zeolite matrix, and shown are the results that the fraction varying with the temperature. In the case of zeolite trapped Fe3O4, it remains stable, quite stable up to 750 Kelvin, and beyond which only there is a decrease in the trapped fraction, then leading to the fraction experiencing magnetic interaction. So on the other hand, you see in the other case where is right from the beginning there is a decrease. So this interesting results show that there is a significant trapping of the thing. And I would like to thank all this is the end of the talk. I would like to thank all the DDSD colleagues and embassy, my student Dr. Hirojit, Dr. Alaka, and recently Parvati and Ravi are doing. All of the former MPS, DDS members, Dr. Gopi, BV, and CSS, Sundar, Amarendra, up to Ravi. Satyajit Azra, I would like to thank Professor Satyajit Azra, HBNI organizer Dr. Nayak, Dr. P. Vasudev Rao, Dr. Chandrasekhar, Dr. Raju, Director Ajika for encouragement, Brit RSD Dhruva for our collaborations. Thank you very much.
Now, it is open for questions. Anyone?
Thanks for a nice talk. In quite a few places, I find.
So that's it.
Can you please?
Hello, I'm not able to hear you.
Hello.
Could you yeah. Hello? Yeah.
Can you hear me? Hello.
Sir?
Hello.
Are you audible?
Yeah. Correct. Now I'm audible. Yeah, please. Tell me, yeah. Yes, sir.
In quite a few Mossbauer spectra, I find that normally, the spectra is generally 1:2:3. 3:2:1 if you
No, sir, you are partly only audible, and or you can put it in the chat box, I will tell you. So that's it.
Okay, sir. Maybe you will be audible to me.
Yes, sir. Now you are audible. I would like to see.
So, is it possible, suppose if you have a highly collimated positron beam, can you do this 3D mapping of your defect?
Yes, sir. With positron beam, you are talking about pulse positron or Doppler bonding studies? Doppler bonding studies also you have done. Depth result Doppler bonding studies using positron beam.
No, you have done it. What I'm telling it, is it possible to do this mapping of defects? Suppose if you get some reactor material or fuel pipes, you like to see that how the defects are distributed. what is the space resolution and how whether it is possible to do it?
Exactly. Yeah, yes, it's possible, sir. Now, right now, we are only doing Doppler bonding studies where only S parameter can be deduced. For any defect quantification, like for example, to identification of defects at all, we need to go for pulse positron beam. But here in the you asked a very good question. It is very much possible. We will get as a function of depth, we will get information about the defects and so on. That is possible.
So
But
what is the depth
mapping
resolution?
wise, sir, mapping wise, spatial mapping wise, we need high intense positron beam. That is, you need something like positron microscope and so on. That is with Kraulhaus in Germany. Those people, they have that facility. Positron microscope is there.
Okay, so if that is no more questions, okay, we can thank.
Yes, sir. Thank you very much. Thank you.
Maybe you can log out.
Yeah, so we'll go for a tea or something.
So we can
Yeah.
let him announce. Go for quick
So-
tea, 15 minutes.
So you can probably stop sharing your
There's
screen.
a poster, there's an online poster from 6 o'clock.
You can stop sharing your screen.
Okay.
Okay. So already the post. So yeah. So we will assemble, Chandan. We will assemble here again at 6.
Within 10, no. Give 10 minutes or 15 minutes. 40, only 10 minutes.
No, not for tea actually. I am saying after tea, or some of them have already tea, they can go directly to the upstairs to have a look in the posters. So we'll come here again at 6 for the online presentation.
Make it at 6:30.
It will be too late.
That's it, that we have to do is for now.
Yeah, so you can go right now. There is no means already there is something.
10 minutes, and with tea, you cannot go there because inside the return is not allowed.
Yeah, so yes. So after 6, we will join again. So for the time being, we are trying to cover the posters. So let's see. If possible, we try to cover some of them.
student कौन है? He's upstairs. I called them, but no one wants to come. No, they're feeling better. No, not that. But now the point was that now the kids are not trying to push, but pull everybody close to their poster. So because we are late, pretty late. It was over just at 10 minus 22 minus 5:40 like something. So no, they are there. 2 minutes.
না ও বোধহয় শেয়ার করছে। হ্যাঁ ঠিক আছে, আপনি এখান থেকে বলে দেন কটা বাজে। 6টা।
Sir, am I audible?
হ্যাঁ 6টায়।
Yes, just hold on a few minutes.
Okay, sir. Okay. I'm waiting.
Yeah, just wait for 5 more minutes, okay?
Okay, sir. Okay.
If you can manage once. No, 7. I put it in 7 minutes. And maybe one or two. We can start. Exactly. That's very clear. Hello. Hello, Dr. Kumar. Can you hear me?
Hello. Yes, sir. Actually, it is slides are freezing. I am sharing again, sir.
No problem. But remember one thing,
that you
Okay,
should
sir.
try to complete it by 7 minutes. I
Okay,
will,
sir.
remind you after 5 minutes so that you will have 2 minutes more time. And then
Okay,
if there is a question answer,
Okay, sir.
it will
Okay.
take 1 or 2 more minutes. Okay.
Okay,
So
sir. Okay.
your time is say 7 minutes, and I will give you an reminder at 5 minutes. Okay.
Okay, okay, sir.
Please try to maintain the time.
Okay,
Because
sir.
afterwards there's a lot of other people.
Okay, sir.
Please.
So it's actually freezing. Okay.
No,
So
no problem.
so should I start now, sir?
Yeah, please.
Okay, so I would like to thank the organizer for providing me an opportunity to present my work here. So title of my work, the talk is the collective magnetoplasmal excitation of an effectively magnetized strongly coupled system in a disordered solid phase. So my name is Prince Kumar. I'm my supervisor, Dr. Devendra Sharma. I'm from Institute of Plasma Research, Gandhinagar. So first, we briefly look at the collective excitation analysis in various state of matter. This is a theoretical analysis. So collective excitation spectra in the periodic lattice where the localization dominates. So the energy landscape has a deep minima where the particles are localized and they oscillate about their mean positions, and the phonons are the primary excitations in such system, and which can be governed by the harmonic approximation. On the other side, on the other extreme, in the gaseous phase where the free motion dominates, no local minima exists for the energy landscape, and the particle can freely move. So collective excitation spectra in such system can be governed by the random phase approximations. But the important thing is that in the intermediate state where the localization and the free motion intervene, you would require a more sophisticated theoretical analysis to cover this both localization and free motion. And quasi-crystalline approximation provides a good description to such systems. So the assumption of this theory is that the particles are trapped in a local structure which can be diffused for over time, and the oscillation period time of the particles is much higher than the diffusion time scale of the background structure. So that background can be represented by the pair correlation function. So the oscillatory frequency can be decided by the local potential as well as the structural effects. So QLC quasi-crystalline approximation is applicable from amorphous solids to astrophysical objects, and in the context of plasma physics, it can be known as a quasi-localized charge approximation theory. So the purpose of this present talk is to analyze the effect of strong magnetic field, because strong magnetic field can significantly alter the collective excitation spectra equilibrium and transport property of such liquid or quasi-crystalline state of such systems. And so the purpose of this talk is to analyze the effect of strong magnetic field on the collective excitation spectra in such system by using a dusty plasma as a model system within the QLC quasi-localized charge approximation framework. So before analyze these effects, we first look at what is dusty plasma is exactly. So dusty plasma is consists of usual plasma species like electron, ion, and neutrals with the heavy charge particles, which are from nanometer to the micro particles. They acquire a very high charge, so which allow them to organize in various state of the matter like solid, liquid, and gaseous state. These two parameters, this is referring to the coupling parameter, another is screening parameter. These two parameters define the state of the system. So this is a phase diagram, and it has also been observed experimentally. This is the experimentally observed picture. The dusty plasma can be well organized like in a crystalline state, and if we increase the temperature, it can transform to the another phase like liquid and gaseous. So it can exist in various state of matter by just tuning the parameter like temperature. And these systems also responds to the external perturbation, and various collective excitations have been observed experimentally like linear waves, shock waves, and solitones has also been observed. And so the question is that can we magnetize dust particle, this heavy charge particle, can we magnetize in a laboratory based experiment? So the question is that it is quite quite challenging task to magnetize such heavy particles, because this beta parameter, which is defined as the ratio between the cyclotron frequency to the characteristic frequency, it has an inverse relation with the mass. So generally dust has a in the range of kilometer, like 10 to the power 12 kilometer kg mass. So in order to make this beta parameter greater than 1, you would require a very tremendous amount of magnetic field of the order of 10 to the power 4 Tesla. So it is quite challenging or very difficult to assess such magnetic field in laboratory based experiments. But fortunately, we have an alternating approach which have been proposed in a recent experiment, where they have put dust cloud into a rotation and take measurement in their rotating frame. What they have observed that in the rotating frame, Coriolis force mimics the effect of Lorentz force in their rotating frame, and this beta parameter, which is now this cyclotron frequency, is now replaced by 2 omega, this is the rotation frequency, and they have managed to produce effect of 10 to the 4 Tesla magnetic field even with a small rotation of 10 hertz frequency. So it is a very remarkable thing. So we consider this rotating dusty plasma, strongly coupled rotating dusty plasma within the QLC charge QLC approach. So here's the schematic of the system. So here's the patch. The dust is now rotating with some finite frequency. This is a simulation patch. And this is the equilibrium flow, and the background electron and ion has their own dynamics, because their dynamics is very fast, so they would not respond to the rotations. They have their own dynamics, so they just seal the dust particles. So dust can be interact by a Yukawa potential. So we now perturb this equilibrium, and we drive the dielectric response tensor from under the QLC assumptions, and from there we have obtained this longitudinal and a transfer dispersion relation, which has a function of DL matrix, DL and DT matrix, which are the central quantity in the QLC framework, which contain all the
2 more minutes, please.
Okay, so which contain all the essential correlation effects. And so now we are concerning about the long wavelength dispersion relation of the dusty plasma. So we have taken approximation to the GR function. So we are considering here the step function, which has a reasonable approximation if we are concerning in the long wavelength limit of the dispersion relation. So by this assumption, we can analytically derive the dispersion relation, longitudinal and transfer dispersion relation of the system, and we have a drive and plotted the dispersion relation with different rotation frequency, where beta is defined the rotation 2 omega divided by dust frequency. So this blue color curve is corresponding to the longitudinal component of the dispersion relation, which is recovered from the QLC theory, and this is red curve is correspond. Sorry, this is for the weakly coupled limit, and this red curve corresponds to the strongly coupled limit of the theory. And what we have observed a close correspondence between the strong coupling limit and the weak coupling limit of the theory, and this corresponding increase significantly if we increase the beta parameter rotation frequency. So can we verify this quantitatively? Because what is the meaning of this correspondence? It is meaning that if you rotate the system faster, this rotation tends to leads to the system in the weakly coupled states. So what have been observed experimentally, that by the rotation frequency, this coupling parameter reduce. If you increase the rotation, this coupling parameter reduce. What we have already observed from our theoretical model. So the next question is that, can we verify our predicted result quantitatively with the experimental dispersion relation? So we need to focus our attention to the weakly coupled limit of the theory, where there is no correlation exists. So in a recent experiment, they have observed a dispersion relation in rotating frame, strongly coupled dust cloud, which is rotating with finite frequency. They have observed the dispersion relation with different beta values. So now for the weakly coupled limit where there is no correlation at all. So fluid model can easily describe the collective excitation in the rotating systems. So these are usual fluid equations. These are momentum equation, continuity equation, and by usual perturbative method, we can observe this, we can recover this dispersion relation. Now we have with the same
Dr. Kumar, just can you kindly
I'm finishing just 1 minute, sir. Okay, so in the so we have observed this, we have recovered this dispersion relation with the in the weakly coupled limit, and what we have observed, a close correspondence, again a close correspondence with the experimentally observed dispersion relation. We have considered same set of parameter here, and this corresponding increase means increase significantly, means it let's is at the beta is equal to 0.7. At the higher beta value, there is a saturation in the frequency around T3 omega, which is exactly matching with the experimental obtained dispersion relations. So it's again confirm our theoretical predictions that the rotation tends to reduce the coupling amongst the dust particles, and the dispersion relation is matching with the weakly coupled systems. So here is the concluding remarks. So what we have observed, a finite jump of the frequency at the 2 omega, which is the corresponding to the cyclone frequency in the magnetized system. So it is indeed a magnetoplasmos mode, which is actually recovering in the rotating frame. The agreement with the experimental observation is improved significantly for the cases with higher rotation frequency. So it means that, and rotation tends to reduce the coupling amongst the constituent particles. So it means that if you rotate the system faster, there is a centrifugal force acting on the particles which lead the particle away from the center. So there is a reduction in the interatomic spacing. Consequently, the coupling parameters also reduce. And while we have focused on the collective excitation spectra, several other plasma property, including the diffusion and viscosity, are affected by a strong magnetic field and are now accessible experimentally. So thank you very much for listening. So if you have any question, I am ready to answer.
Thank you.
Okay.
If there is, I can just only one question. If anybody else, yeah, please. Okay. Just please, better.
Hello. Yeah. Can you hear me? Hear me?
Hello.
Hello.
Yes, sir.
There is a question.
Okay, sir.
The question is, how do you experimentally ensure that the dust is rotating?
Okay, so answering means as you can see, here the schematic of the system of rotating dust cloud. So what they have observed, this is the experimental setup. Can you see this diagram? Okay, so in the experimentally, what they have put a rotational electrode, and that rotation electrode dump their energy to the neutrals, and neutrals drive the dust cloud with some finite frequency, and they take the measurement by moving the probe with the same frequency as the dust cloud is rotating. And
that is the question. That is the question, that how you are how you are ensuring the dust is rotating. So that is the question.
So dust is actually because dust is a very massive species, because electrons and ions are a very light species. So ensure means the effect have been recovered experimentally. They have observed these effects, these rotational effects, and from theoretically as well as experimentally. So I'm hello.
Yeah. Okay. Yeah. Okay, Dr. Kumar. Thank you.
Okay.
Kindly stop the sharing, please. I will go to the next person.
Okay.
Next is Dr. Sukriti Hansa from IPR. Will be speaking on role of temperature-induced surface diffusion in the pattern formation. Our people in Yeah, Dr. Sukriti Hansa. Nothing is audible. Nothing is audible. Can you unmute Dr. Hansa?
Hello, am I audible now?
Yeah. So look, you have just try to maintain the time. It is just 7 minutes. I will remind you after 5 minutes and kindly try to maintain the time. Okay. In
Okay.
7 minutes, you have to complete. Please.
Okay, my slides are visible.
Yeah, please. Please
Okay.
start.
So myself, Sukriti Hans, I'm from Institute for Plasma Research. I'm working under Dr. Mukesh Ranjan. So today I'll be talking about role of temperature-induced surface diffusion in the pattern formation. So till now we know that this nano pattern formation, that is to pattern materials on nanometer scale, have wide variety of applications, and people are trying to produce in a fast, reproducible and a well-controlled way to pattern material surfaces so that it can be used in a lot of applications. So on to the left, we can see that we have this ion beam system. We have ion source onto the left, and there is a sample manipulator where we can rotate the sample. And the lower image shows that the sample holder where we can place the sample. And this is this beam. We can see that there is a beam which interacts with the material, and whatever the modification happens after ion interacts with the material is reported, is characterized using an atomic force microscopy. So on to the right, you can see images of SEM or AFM, where people have tried with different materials and at different ion beam parameters. So till now, people tried to get a lot of materials, like they tried on silicon, they tried on gold, they tried on different semiconductor, metal, insulator with different ions, different species, different ion beam parameters. And the goal was only to achieve as better highly ordered ripple pattern, dot pattern, so that they can be highly accessible from application point of view. So so for that, we should know where we can use, like for plasmonics, ripple pattern can be used for plasmonics. So if we have a bare sample, we won't get any peaks, but if we have an ordered chain of patterns on which AG or AU deposited, we get a good peak, and we can also use to sense the material. For magnetic also, we can try to make material from paramagnetic to ferromagnetic. Also, we can align DNA materials on these ripple patterns. Even on glass, we can use these materials to pattern so that we can enhance the Raman's peak. So within these pattern formation, there is always a problem of these triangular feature formation. So nobody has looked for these triangular feature formation till now. So my topic of interest is how these features appear, and with different ion beam parameters, how they fade, how their dynamics changes. So what are triangular features? So if you look that onto the left side, this is the AFM topography of a silicon material which is being irradiated using argon ions. So we get ripples, along with them we get this triangular feature which superimposes them. So these triangular features appear in the two varieties. One is elevation and the other is depression. So elevation is like the ripples which are elevated above the surface, and depressions with the ripples which are elevated below the surface, which are depressed below the surface. So line profile, we can see that this 2D, in the 2D triangular features looks like this. So I tried to look for the dynamics with different ion beam parameters. So first parameter I chose was ion energy. So when I started with 200 eV ion energy, there was no triangular feature. Even the pattern formation was very shallow. So with an increase in energy, the triangular feature started appearing with a base angle. And when I started to increase energy further, the elongation was along the ion beam projection, which was like along the x-axis. And at higher energy, again, the triangular feature starts to vanish. So with this, we get to know that they're highly dependent on ion beam parameters. So I tried to look for another parameter, which is ion incidence angle. So within this window, I tried to get these parameters where triangular features appear. So at 60-degree angle of incidence, the features were very shallow again. But with increased ion incidence angle, the triangular feature base angle increases as well as their lateral length, which is this one. So they also increases. So we get a window where we find these parameters where triangular features appear as well as disappear. So once we get to know the dynamics, even from their line profile, we can see that there are elevation and depression which get enhanced with increase in ion incidence angle. At particularly 67, we get highly good order ripple patterns, but obviously triangular features are still imposing on them. So there was a theory which tried to explain the phenomena, which said that triangular features or these ripple patterns appear because of two phenomena. One is when one process roughens the surface, that is basically eroding the surface, taking out the material, and other is smoothing. That the material which is eroded out, they try to smooth, they try to diffuse. On to the left, you can see there is erosion, whereas on to the right, there is diffusion. So this was a theory established in 1988. But at that time, they were only able to...
please.
Okay, so a lot of theories came and they tried to enhance the theoretical background. So use this model we tried later, and we also get the topography in simulation we got in experimental. So we got to know the parameters which are responsible for the formation. So in a simulation, we got to know that dependence is important for incidence angle. And we were very well able to establish the experimental and simulation comparison. And this from here, you can also see how they are well matched. So now where comes the temperature? So we tried to know if we can evade or we can manage these triangles. So we increase the substrate temperature from when we started at 100 degree, the temperature, the features as it is like once we get for room temperature. But with increase in temperature at 200, we get very low base angle of triangular feature, and hence we can get very good ripples which can be used for application. But at higher temperature, these triangular feature again vanishes and corrugates these features which are not good for application. So using this, we also try to get the line profiles from there. Also we can see there is elevation and depression, but at higher temperature, these have actually vanished. So also in simulation, we tried to vary this diffusion parameter and we got the same result what we get in experimental and exactly the same line profiles. So we get to know that if we increase the temperature and if we this irradiate the sample for a longer time, we can get patterns which can be very useful for application, and which were actually trying to somehow deviate the SERS or plasmonics application. We can get good patterns, and this was a summary that we have studied on silicon. And if we can possibly, there is a possibility to exploit dispersion so that we can produce ripples, which is a very good topic of experimental investigation, and hence our applications can also be improved. Thank you very much. If you have any question answers, you can ask.
Thanks, Dr. Harsha, just to maintaining the time exactly. So if there is some questions, it will be.
Yeah, so have you checked your pattern by rotating your substrate? Because in all
Yes,
the
sir,
AFM image I can see, so you have presented it like that, or you have make the AFM like that?
No, I tried to rotate the sample. So this you can see at this at different ion incidence
Can I have
angles.
any image? You have a scan direction in means
Image of?
other scan directions. You have any image? Because triangle is always an artifact
This
of
is my
AFM.
sample.
No? So have you checked that?
No, sir, it is not an effect of AFM. There is a well
No, that is well established.
established theory for the same.
But
And
have you
using
checked
that
it?
only,
Have you
yes, sir,
checked?
I tried to check on different angles also. So this triangular feature appear only in a particular window.
So can you show me some of the image other than these scan directions?
Other images hasn't. See, you can see if you
Okay.
change
So
the energy, these triangular features won't appear.
Okay, Dr. Hans. Thank you. Can you kindly Unshare the screen, please.
Yeah, sure.
Stop the sharing. So next is Dr. Rakesh Dora. Okay, might have completed. I do not know. I do not know because there are though not yet completed. Okay. So next is Mr. Rakesh Dora. His talk is title is Nature of the Anomalous 4/13 Fractional Quantum Hall Effect in Graphene. Mr. Rakesh Dora, please.
Okay.
Mr. Rakesh Dora.
Yes, I am presenting.
So please try to complete your talk by 7 minutes. Please try to maintain time, and I will give you a reminder after 5 minutes so that you will have 2 minutes to rush on if you need. Okay. So please start. I'm trying to maintain the time. There is no other way. Look, otherwise all these people will beat me up because they are dinner. If it would have been the morning, I would not have mind.
Can you share? Okay, I can't share my screen actually. So it requires co-host or presenter makes you the presenter.
Okay, then what we can do, we can go to the next, and if he can by that time make the presentations, then we will call him again in the next slide. So Mr. Dora, is it okay with you? So you try to adjust, solve your internal computer problem. We will go to the next presenter, and by that time we will call you again after maybe 10-15 minutes. Okay. After this topic.
From your side, I mean, host.
My side, our side. So far, it was working with everybody else, actually.
Okay, I will.
Oh,
I can't share screen because it says
last speaker was Sukriti Hans. So yeah, Miss Hans, are you there? Can you kindly unshare? She has unshared.
Okay, now I can share my screen. Okay, is my screen visible?
Yeah. Okay. So, Mr. Dora. Yeah, but now but in a quick glance, I could see you have quite a lot of slide by 7 minutes. I don't know whether you can really complete it or not, but please remember, I will remind you in 5 minutes and I will stop you after 7 minutes. Okay. So please choose your slides accordingly.
Okay.
Kindly start.
Okay. Hi everyone. So I will talk about the nature of the anomalous 4/3 fractional quantum Hall effect in graphene. So okay, so let's start from what is quantum Hall effect. In general, electrons under subjected to a perpendicular magnetic field exhibit some certain peculiar kind of phenomena. So when in this system, when one measures the Hall resistance, which is the ratio of the perpendicular voltage divided by the total current passing through the system is quantized at certain region of magnetic field. And it develops a plateau, and on that plateau the Hall resistance is quantized at certain integer values in units of h over e square, and that phenomenon is called integer quantum Hall effect. And whenever this Hall resistance is quantized at some fractional values, it is called fractional quantum Hall effect. And another feature is that whenever there is a plateau forms, there is a dip in the longitudinal resistance. So it turns out the integer quantum Hall effect is easy to understand. It is a simply non-interacting electron picture, but fractional quantum Hall effect requires interacting electron picture. You want to include the electron-electron interaction. So when we include the electron-electron interaction, if more than 3 particles or beyond 3 particles, the Hamiltonian is hard to solve exactly. So the traditional way is to guess a wave function. In this regard, the Laughlin proposed a trial wave function at the fractions of the type 1 over 2n plus 1. For every odd fraction, he proposed a trial wave function, and it turns out that this fraction captures well, it has good overlap with the numerical obtained ground state of the Coulomb interaction, and it has non-trivial property that the excitation above this ground state has fractional charge. It's like an electron has split into 3 pieces. Now, Laughlin wave function cannot explain the fractional quantum Hall effect observed at different fractions. So there is another theory called composite fermion theory, and it explains fractions of the type n over 2np plus or minus 1. So here n and p are integers. So in this theory, an electron under perpendicular under magnetic field B captures certain amount of magnetic flux to form an emergent particle called composite fermion and experience a less effective magnetic field. And this fractional effect quantum Hall of electrons can be understood in terms of integer quantum Hall effect of these composite fermions. And there are other kind of fractions which lies beyond this composite fermion, like 4 by 13, 5 over 17. This kind of fractions are there, and in this talk I will consider one of such fractions 4 by 13, which the Kumar and his collaborator found strong evidence of fractional quantum Hall effect at this fraction. So we propose a trial wave function following a method called pattern construction. In this pattern construction, one divides an electron into some fictitious number of particles and forms the integer quantum Hall state of these patterns under the same magnetic field B that the electron experienced, and then finally fuse them to get back the physical electrons. And this procedure yields a wave function of electrons and in terms of the integer quantum Hall state of patterns, non-interacting patterns. And so there are various conditions that under the like the number of patterns must be odd, and we can determine the charge of these patterns. Okay, so following this pattern construction, we propose a state called 4 bar 2 1 cube for the fractional quantum Hall effect at nu equal to 4 by 13. So in this procedure, we divide an electron into 5 patterns. So one pattern has charge e over 13, and second pattern has charge minus 2e over 13, and other 3 patterns have charge minus 4e over 13. And finally, we form an integer quantum Hall state of these patterns. So this procedure leads on wave function of electrons, a highly correlated wave function of electrons in terms of these non-interacting patterns. Now our task is to test this trial wave function with the exact Coulomb ground state. So one obtains, so we simply choose a basis and diagonalize the Coulomb interaction in a basis and obtain the ground state energy, and then compare the ground state, compare the expectation value of our interaction with respect to our proposed trial state. So we find that our proposed trial state is just 0.0075 units of energy is higher than the exact Coulomb ground state. So even if there is a little difference, we expect our proposed state captures the universal properties of the fractional quantum Hall phase at 4 by 13. By universal properties, I mean what is the charge of the excitation, what is the statistic, and there are certain topological quantities that our theory captures. And
Dora, 5 minutes are over, 2 more minutes.
Yes. So another property is that whenever we are in fractional quantum Hall phase, at the boundary of the system, there will be some gapless edge modes. And following field theory construction, we propose an edge structure of the 4 by 13 state. So in our theory, we find that, so at the edge of the sample, there will be 5 counter propagating modes. 2 of them will propagate one direction and 3 of them will propagate along an other direction. And with this, we calculate the chiral central charge which is the difference between number of upstreaming mode and number of downstreaming mode, which is -1. And then we propose an experimental measurable prediction that if our state is correct, then in experiment it could be measured that at 4/13 fractional quantum Hall state, the smallest charge of excitation will be -e/13, and we can compute the thermal Hall conductance since we know the chiral central charge. So when by assuming that all edge modes are in equilibrium with each other, then thermal Hall conductance will simply -1 times some unit, some constant times temperature, provided the temperature is less than gap. So this is our experimental measurable predictions, and with this I conclude that we have provided a microscopic and effective field description of the fractional quantum Hall state at 4/13 filling fraction, and also we have predicted some experimentally observable quantities that would validate our proposed pattern state. With this finishes my talk, and thank you for your attention.
Thank you, Mr. Dora, maintaining the time. Is there any question? So, any questions from any higher audience? No. Yeah, okay, Mr. Dora. Thank you. So, can you kindly stop the sharing, please?
Okay.
Next talk is by Mr. Soumya Shur from MedScience. The title is Novel Criticality in Quantum Compass Models in 2 Dimensions. Okay, in our places, did they have to share? Okay, Rakesh Dora is put it and share. Now Mr. Soumya Shur. Mr. Shur. Mr. Soumya Shur. I think so, but they are. Rakesh, is stop shared or not? Stop shared. Soumya, can you share your unmute, please?
Hello. Yeah, I am trying to share. So
yeah.
So can you help me? So basically, I don't see the how to share the full screen. So do you know how to? Hello.
First, we have to share the screen. We cannot see
Yeah,
anything.
So I am trying to share, but I cannot share. Like it's saying that I cannot
Is
share
it
the content.
our problem?
I see. So that button is not working. The share button is not working somehow.
Just see.
Now I can see. So yeah, now I can see this. Yeah. It's okay. So I have shared. So can you see my screen?
We can. Yeah, once came and then suddenly something vanished again.
So can you see?
No, we cannot see anything. We can see you, but not your screen.
Hello. Hello. Hello.
Can you? Yeah. Have you opened the PowerPoint window?
Yeah. So, but I shared the screen. So I don't know. So in this,
they have allowed. Okay. So it's from outside.
Can you can you tell me how to share the full screen? So I am using iPad. So do you know someone know how
then
to?
we can make it full screen.
The bottom you will find it.
No. Sometimes it's saying that I cannot share the content. Yeah, but I can. So it is sometimes it's showing that I cannot share.
I think there is one of your friend just now gave the talk. Yeah, now something came. Now white, pure white.
Okay. So can you see now the screen? So basically, I never use this WebEx platform. So can you tell me, someone tell me how to? So basically, how to share the full screen of iPad?
এই তো
That's the problem I am
অরিন্দমকে একটু ডেকে আনো তো। না না না, মানে কথাটা শুনতে পাচ্ছেন, শুনতে পাচ্ছি। ওকে, সো অরিন্দম, তুমি একটু হেল্প করতে পারবে? ফোনে কথা বলছে।
So just I am trying myself. So let's see.
So don't blame me if I cannot complete it by 7. As an organizer.
So now can you see?
Great. Yeah, finally. So now you are
So
here.
actually, sorry for that. So I don't know why it was happening in iPad. I never
remember one thing,
presented in iPad. So
7 minutes. I will remind you
Okay,
after
okay.
5 minutes, okay? Please try
Okay,
to
thank
complete
you.
it by 7 minutes. Start now.
Okay. Okay, so at first I want to thank the organizers, and without delaying anything, so in this talk I am going to present some our work on the quantum compass model, which was done by me with my PhD supervisor, Professor Mukulis Lad and Professor Isar Hassan. And next, so at first I will start from a general motivation. So basically, the quantum physics of matter is can be classified into two categories. One is called Landau-like order, which are generally classified by the symmetries of the Hamiltonian and generally contain local observables, local order parameters. So you have one phase which doesn't have any order, or order, and other one is has some order which breaks some symmetry of the Hamiltonian. So generally, these kind of states have continuously some in cases of continuously symmetry breaking, there are gapless Goldstone mode. The famous example is like ferromagnet paramagnet transition and superfluid Bose transition, Bose gas transition. And on the other hand, we have quantum order. In this case, the classification is not based on the symmetries of the Hamiltonian. So there is no so-called quote unquote local order parameters. So in this case, the property of the system is classified by the topology of the ground state degeneracy and fractional excitation, etc. So just now, the previous speaker spoke about fractional quantum Hall state. So that is one kind of quantum ordered state. And in addition, there are spin liquids and different gauge theories. So the necessary ingredients for quantum order is competing interactions or frustration. Second is lower dimensionality of the system or low quantum number. And the third is the existence of a new kind of lower dimensional gauge like symmetries. So in this talk, I am going to, as I said, I go to tell about this kind of quantum spin compass models, which has like this kind of anisotropic interaction where the different spin components act couple along different bonds in a different manner. So this kind of model historically was introduced in the context of description of the degenerate orbitals degrees of freedom in transition metal oxide by Kugel Chomsky in 1970s. In recent years, this after the discovery of Kitae's honeycomb model in 2016, which is exactly solvable model and has exotic properties like fractional excitations, Z2 topological order. And also simultaneously there are proposals which came from different people which says that this kind of compass like anisotropic interaction can in principle can be generated in systems which have a strong spin orbit coupling, and if they and also this kind of interactions can be generated in nowadays by Josephson junction implementation, which are this quantum information people nowadays there are a lot of application in this direction. So then I will go to our model and our formalism. So in this talk, I am going to focus on the compass model on a square lattice. So as you can see from the Hamiltonian, the Pauli spin x components acts on along the x direction, and the z components acts along couple along the z direction, and we have anisotropic coupling along x and z direction. So in this kind of model has a lower dimensional symmetry, P and Q, and which has certain commutation relations, which gives rise to certain restrictions on the properties of the various correlation functions. In addition, we have a dimensionality reduction in this kind of system, which has lower dimensional symmetries, which tells that if you have some local operator, the expectation value of the local operator in the full system, higher dimensional system, is constrained by the expectation value of the lower dimensional system where the this kind of symmetries acts. As a consequence of that, the local magnetic order at any finite temperature is 0 for this kind of compass model. So there are possibility of Ising nematic order at finite temperature. So all these constraints put a very strong restrictions on the kind of analytical theory if one wants to construct that put this kind of symmetries puts a lot of restrictions on that. So there are varieties of numerical approaches that has been used for this model, like quantum Monte Carlo, variational tensor renormalizations, but all these has some limited success in terms of describing. Some describe the finite temperature properties very well, some describe the zero temperature properties to some extent well, but there is no reconciliation of this result. So and also the nature of the elementary excitations and their role, what are their properties in different phases, or correlation function, spin correlation function, that is not known. That is not in our work we try to construct a semi-analytical theory based on the exact solution. So if you have a two-leg ladder system, as you can see from the figure of the full square lattice two-leg ladder, if you
Mr.
consider a
Sood,
two-leg.
you have just 2 more minutes, please.
Okay. So as I said, we try to construct a mean field theory based on the this two-leg ladder exact solution of the two-leg ladder compass model. We try to implement a Kramers-Vernier duality, and we try to implement. Then we applied some mean field theory. We decouple the mean field, the Hamiltonian, in such a way that this preserves all the lower dimensional symmetries which I mentioned earlier. We then we solve this cell consistency equation, and then we find that the ground state has a first order phase, shows a first order phase transition, and there is a good convergence of the ground state energy for 4 and 8 leg ladder case. In addition, we also find some duality in the phase diagram in terms of the various order parameters delta x and delta z. In addition, then we also studied the finite temperature continuous phase transitions, which shows that this nematic order at Jx is equal to Jz goes like a, some T minus Tc to the power half, and also the susceptibility diverges at that temperature. So then I give a summary of the phase diagram which we find. So we have a phase where the spins are mostly ordered along the chains, and we have another phase called ZZ order, which in which the spins are aligned along the columns, and there is a first order transition between them, which is shown by the border of that is shown by the red line. And there is a zero temperature phase transition between a spontaneously symmetry broken phase to the disordered phase, and in at finite temperature there is a second order transition which ends at the critical endpoint of the first order transition. So then also we studied the elementary excitations of our.
Nearly over. Can you kindly complete it, please?
Okay, so then I just because initially let me summarize the key points. So we constructed a mean field theory which preserves all the symmetries of the Hamiltonian. Then this mean field theory, as we find that properly describe the most part of the phase diagram in both zero and finite temperature. And we find the spin correlation length in most part of the phase diagram is has a finite correlation length and only at t is equals to tc it has a power law behavior, but still the spatial correlation length is finite. And the excitations are dispersive domain walls that has some important consequence in the context of spin orbitals models. Thank you. Sorry for.
Yeah. Okay, thank you, Mr. Shur. So is there any question from the audience? Okay, if there is no questions, thank you again, Mr. Shur.
Okay.
Can you kindly
you.
stop the sharing, please? Next talk is by Mr. Pushpendra Gupta from Niger. The title of the talk is Simultaneous Observation of Anti-Dumping and High Spin Pumping Voltage in Manganite/Heavy Metal Bilayer System. So, Mr. Pushpendra Gupta. Mr. Gupta, you are here? Please unmute.
Okay.
Yeah, okay. Now make it full screen. By the way, you have exactly 7 minutes. I will remind you after 5 minutes. Okay. Try to complete it by 7 minutes, please.
So I'm audible,
Please
sir?
start. Yeah, please start. So I will remind you after 5 minutes and you have to complete by 7 minutes. Okay.
Okay, sir.
Please,
So
please.
good evening, everyone. I am Pushpendra Gupta from Niger. I am working under Dr. Shivankar Vedanta. So first I would like to thank to the organizer for giving me opportunity to present my work here. So, okay. So as all of us know that the electron has two basic property. One is the charge, another is the spin. So in normal electronics, we are dealing with the charge of the electron, but in spintronic, we are dealing a charge as well as the spin of the electron. So spin has two states, up state and down states. So why we are moving toward the main question is why we are moving toward the spin current or spintronic. So because of the following reasons. So let's consider you have electrons and you want to move them from one place to another place. Then the time consuming in moving electron one place to another place and the power consumed will be large in comparison to flipping one state of electron to down up state to down state. So in that way, spin current have advantage that it can consume low power and the dynamic will be faster. The another important aspect is non-volatility. So these devices are will be non-volatility in nature. So how we are dealing with the spins? So let's consider you have a ferromagnet and you apply external magnetic field. Then the spins of the ferromagnet will start processing and they will try to align in direction of external magnetic field. So this is the very famous Landau-Lipschitz-Gilbert equation. The first term is the precession term and the second term is the damping term. So here alpha is the Gilbert damping constant and that decide how fast the spin will align in direction of external magnetic field. So the type of study like spin pumping and inverse spin Hall effect, we are dealing with the bilayer system where one layer will be the ferromagnet and another layer will be the non-magnetic layer which have very high spin orbit coupling. So in that type of system, Gilbert damping constant can have several contributions like intrinsic, proximity effect. Let's say you have cobalt platinum system, then platinum will get some induced magnetization that can also lead to the enhancement in the damping. And the most important factor is the spin pumping. I will discuss this part later. So basically, I want to tell here, in case usually it has observed that if you have spin pumping in your system, your Gilbert damping constant enhances. But for application point of view, low damping material is desirable. So what is the spin pumping? So spin pumping is a basically phenomena where spin angular momentum of a ferromagnetic layer is getting transferred from ferromagnetic layer to non-magnetic layer. So basically we are injecting spin current from ferromagnet to non-magnet. So as I'm going to discuss about the spin Hall effect and the inverse spin Hall effect, let me give a brief introduction to this. Let's consider you have a high spin orbit coupling material, let's say platinum or some other metal. Then you flow charge current into this. Then your one type of spin will get accumulated in one side, another type of spin will get accumulated another side because of high spin orbit coupling of this material, and the atom of this heavy metal will work as a scattering center. So now you have spin current from this side to this side, but you can detect it only qualitatively. Quantitatively, you cannot detect it because your voltage will be zero. So to overcome this issue, we need to convert this spin current to charge current. So the process by which we are converting spin current to charge current is known as the inverse spin Hall effect. So the process for this is the same because this is also happening because
Mr. Gupta, can you kindly bring the mouth close to the microphone?
I'm audible now, sir.
Please bring your mouth close to the microphone.
Now I am audible.
Huh?
Hello? Now I am audible, sir.
Mr. Gupta, can you hear us?
Yes, sir, I can hear you. Can you hear me? Hello, sir.
Yeah, continue, please.
Okay, sir.
A little louder, please.
Okay, sir. Okay, sir.
And you have 3 minutes, okay?
Okay, sir. So the conversion efficiency.
I give extra.
So efficiency of conversion is known as the spin Hall angle that is given by JS by JC. So as I told that we need a bilayer system, ferromagnetic and non-magnetic layers. So people always prefer ferromagnetic side, a low damping material like permalloy, cobalt, iron, boron, yttrium, iron, garnet, etc. And from heavy metal side, people prefer high spin orbit coupling material like heavy metal, antiferromagnets, topological insulator, etc. We have chosen LSMO as a ferromagnet because of its high spin polarization, and its Curie temperature is also high, more than room temperature, so we can use it for the application point of view. As we are going to study the LSMO property, so we have chosen platinum as a standard heavy metal which have very high spin orbit coupling. So the samples which we have prepared is listed in the table. We have used oxide-based molecular beam epitaxy, and we have monitored the film growth by using lead and read. As you can see, this dark spot from the lead images and the streak pattern from the read images tells that our films are very high quality. We have also confirmed this by cross-sectional TM, and you can see from HRTM that LSMO has grown layer by layer. So this is our main setup where we have performed Gilbert damping constant measurement and the spin pumping measurements. So I have zoomed this part. So we put our sample in flip chip manners, means upside down. And when we give the when we apply the external magnetic field, then the spill will start precessing, and the precession frequency is known as the Larmor precession. When we give the RF current, then if the frequency of Larmor precession is matching with the this RF frequency, then resonance will happen and the absorption will be very large. And you can see this black color curve. This is FMR absorption spectra. From fitting of this, we can obtain the value of resonance, H resonance, and from FWHN, we can get the value of line width. And simultaneously, we have measured the voltage, and when we got the FMR absorption, same time we have obtained the peak in the measured voltage. So this is voltage due to maybe because of spin pumping. We have performed to get the Gilbert damping constant value. We have performed frequency dependent FMR measurements. So from frequency 3 to 16 gigahertz, and separately fitted for each frequency to get the H resonance value and the line width value, which are fitted as you can see from the figures. And the Gilbert damping constant which we have obtained is listed in the table. So very interestingly, that Gilbert damping constant for single layer is 0.01, but for the bilayer case, this significantly reduces. So it's very important that usually it happens then when you have spin pumping, then Gilbert damping constant increases. But in our case, we have obtained the decrease in the Gilbert damping constant. So we were puzzled. So then further we have systematically studied, and we found that the reason behind that may be anti-damping like torque. I will not be explaining here because of short time. If someone wants, we can discuss it later. Further, we have performed the inverse spin Hall effect measurement. This blue color curve, you can see that. We have fitted this by using this equation, which has two components. One is symmetric and another is asymmetric. So further to rectify other component like spin pump, anomalous Hall effect and isotropy magnetoresistance, we have performed angle dependent inverse spin Hall effect from 0 to 360 degree, which is fitted by using and separated symmetric and symmetric part and plotted with the angle. So then further we have fitted the symmetric part by using this equation and asymmetric part by this equation. And the several component has been separated out, and you can see the listed, the values are listed in the table. So it's very clear that we have very high spin pumping voltage in our system, nearly 20.5 microvolts. And so in one hand, we have very high spin pumping voltage, and in another hand, we have decrease in the Gilbert damping constant. Usually these are the contradictory parameter, and but we have observed simultaneously. So this makes this system very important and useful for the application point of view.
Yeah,
And
can you kindly
Yes,
complete it soon?
Sure, sure. So further we have calculated spin Hall angle, and these values are closely matching with the reported values. So here is the summary. We have observed anti-damping in our LSMO Platinum series, and we have observed very high spin pumping voltage. So these two parameter, simultaneous observation of these two parameter make this system very interesting and useful for the application point of view. So there are several open questions. So theoretical understanding of anti-damping is still pending. So FMR response is also very crucial for this LSMO things. So I would like to acknowledge my supervisor, Dr. Shubhankar Vedanta, and my other lab members who has helped me in this whole things. So thank you all for your kind attentions.
Yeah, thank you, Mr. Gupta. So is any questions from the audience? Any questions? Okay. Since there is no more questions here, so Mr. Gupta, can you kindly stop the sharing?
Yes, sir, I have stopped.
Thank you. So the next speaker is Mr. Deepak Garg from BRC. The title is missing here. I don't know the title of the talk. So Mr. Deepak Garg, you are around?
Yes, sir. Hello. Yes.
Yeah.
Hello. Am I audible?
Yeah. Can you kindly share the screen, please?
Shared.
So the point is you have to complete your talk by 7 minutes. I will remind you after 5 minutes. Okay. Please try to maintain the time.
Okay. So shall I start?
Please start.
Good evening, everyone. I'm Deepak, a PhD student working with Professor S.M. Yusuf, BRC. Today, I will be speaking on understanding of correlations between negative magnetization and exchange bias phenomena in rare earth chromates. So this is the outline of my presentation. First, I will speak about negative magnetization and exchange bias phenomena, and I will discuss about these two systems, and finally I will conclude. So first is negative magnetization phenomena. So in this phenomena, basically, this DC magnetization of the compound changes its sign from positive to negative across a certain temperature, which is called compensation temperature. So basically this phenomenon where magnetization changes its polarity. So this phenomenon is called negative magnetization phenomena. Next is exchange bias. Exchange bias basically is a measure of the asymmetry in the hysteresis loop. For example, here this loop is symmetrical, like HC2 and HC1 both are equal. So there is no exchange bias. The exchange bias is 0. But in some cases, if your MH loop shifts towards the left side of magnetic field axis or either toward the right side of magnetic field axis, so it will be then negative exchange bias and positive exchange bias. Basically, depending upon the shift, it will be negative, or it could be positive. So what are the main requirements to observe negative magnetization and exchange bias phenomena? So first requirement is that compound should have 2 or more magnetic sublatiles, for example, Si and Sj. A second is coupling is required, and third is the anisotropy energy in between the anisotropy energy. So because in the absence of anisotropy energy, this antiferromagnetically coupled sublatiles could rotate in the direction of the magnetic field, and then there will be no NM phenomenon. So today I will discuss. So here R is La1 minus X PRX and second is YbCrO3. So I will discuss about these two compounds which belongs to RCrO3 family. So first is La1 minus X PRX CrO3. So this is the DC magnetization data of these compounds. So here for intermediate compositions for X equal to 0.25, 0.5 and 0.75, this negative magnetization phenomena is observed because this magnetization becomes negative below a compensation temperature, whereas for X equal to 0 and X equal to 1, magnetization remains positive below the magnetic ordering temperature. And this is the exchange bias. So we measure this, we did this measurement at 5 Kelvin, and this is the exchange bias as estimated from corrosivity values as I discussed earlier. For intermediate compositions like 25, 50 and 75, this positive exchange bias is observed. And while for X equal to 1, this negative exchange bias is observed, whereas for X equal to 0, no exchange bias, because for X equal to 0, compound basically compound has only one magnetic sublattice. So as I discussed, if compound has one sublattice, then there will be no. So here you can see that for intermediate compositions, positive exchange bias is observed, whereas if you see magnetization data as negative. So this indicates the correlation between negative polarity of magnetization and positive polarity of exchange bias. So it indicates the correlation. Similar kind of correlation we found for the other member of this series, which is YbCrO3. And so here below compensation, that magnetization, whereas exchange bias was positive. And similarly above compensation, magnetization was positive and exchange bias was negative. So this again indicates the correlation between negative magnetization and exchange bias, as well as we observed this polarity reversal of exchange bias across the T compensation also. So to get the microscopic understanding as well as mesoscopic understanding, we used neutron-based techniques which are available at Dhruva reactor BRC. So first is the neutron diffraction. So this is a refined neutron diffraction data at two temperatures. One at 1.5 Kelvin and what is other is 120, which is basically magnetic ordering temperature. So below magnetic ordering temperature, intensity of 011 and 101 peak.
Yeah, you have 2 more minutes, please.
This peak corresponds to magnetic ordering of the CR, basically antiferromagnetic ordering of CR, while the other peak, which is 002 peak, which corresponds to ferromagnetic component of the YB. But as I said, two ferromagnetic components are required to observe the negative magnetization phenomenon. So, but neutron diffraction is giving antiferromagnetic component of CR, and there will be no ferromagnetic component. So to see whether there is ferromagnetic component corresponding to CR or not, we employed the neutron depolarization. The beauty of this experiment is that in this experiment we use polarized neutrons. Unlike to unpolarized neutrons. Diffraction experiment. Second beauty is that this experiment sees the domain magnetization. If domain has some magnetization, then it will you depolarize, otherwise it will not. So this is the neutron depolarization data as a function of temperature. So here below magnetic ordering temperature, neutron beam started to depolarize and full recovery is observed at the T compensation. So it means below magnetic ordering temperature, there is some net domain magnetization sets in the compound, and at compensation there is no domain magnetization. It means net magnetization of the domain. The net DC magnetization at the T compensation. It indicates that there are two ferromagnetic cancel each other. So to explain NM phenomenon, we use according to which net magnetization is given by MCR plus MYB, and which MYB is given by this term. So here MCR is the ferromagnetic component of CR as earlier. H is the applied field, HI is the internal field, theta is the Curie-Weiss constant. So good agreement is observed between the experimental and calculated. From this fitting, we found HI is negative and it is greater than H. So it means MYB is dominating over MCR across the compensation, which is giving the negative magnetization in the compound. Next,
yeah, Mr. Gork, can you kindly complete it soon?
Just this last slide, sir.
Yeah.
So next is the exchange-wise reversal. In this compound, we found the polarity reversal of exchange-wise also. So this is strongly intertwined to the negative magnetic. When we go from first quadrant to third quadrant, system is going from the favorable to unfavorable state, unfavorable magnetization state. So that's why more energy is required to go from first quadrant to third quadrant, which makes Hc1 higher than Hc2 and which is giving the exchange bias negative. Similar explanation holds for the positive exchange bias. So this indicates that negative magnetization is correlated with the positive exchange bias, and whereas positive magnetization state is correlated with the this negative exchange bias. So this is the inferences. The present work infers the study of NM and DB in radioactive weights. Second, correlation is established between the two phenomena in these compounds, and the understanding has been achieved by using DC magnetization, neutron depolarization, and neutron diffraction techniques. Thank you.
No, thank you, Mr. Garg. Is there any question? Any question? Okay, if there is no other questions, thanks, Mr. Garg, once again. Can you kindly stop the sharing, please?
Yes.
The next talk is by Ms. Vidha Bhashin, and her title is Investigation on Thin Film Electrode Based Lithium Ion Battery. So, Ms. Bhashin, there will be total, your talk will be limited to 7 minutes, and I will remind you after 5 minutes. Okay? Is it okay
Yes,
with
sir.
you?
Yes,
Yeah,
sir,
please
yes.
try to maintain the time. Yeah,
Sure.
kindly
Shall
start.
I start, sir?
Yeah,
Shall I
yes,
start?
we can see your slide and you are perfectly audible.
From Atomic Molecular Physics Division, BARC. Battery. The motivation behind nowadays to mitigate the effects of global warming that is caused by burning of fossil fuels for energy production. Shade behind. As you can see from the figure in the left, the lithium so as the name suggests, lithium-ion battery is all about the movement of lithium charge and discharge. What happens is during charging, the lithium ions move from positive electrode to the negative. The ions also move from positive electrode to the negative electrode. They both then combine to form lithium, and lithium gets deposited in the negative electrode. And the vice versa happens when the battery discharges. There is a separator also in between provided to allow lithium ions to flow while it prohibits structure, and the current collectors are provided to receive the electron power nowadays, from laptops and computers and cell phones to hybrids and electric cars. Lithium-ion batteries has immensely grown because of its many advantages, like it has higher energy density, low self-discharge, low maintenance, and many more other benefits. Normal battery electrodes, they are made by slurry-based approaches. That is, they are mixed. That is, the paste of synthesized electrode powders are mixed with conductive carbon paste and PVDF binders. So this basically a possible solution for us that we can switch to thin film based lithium ion batteries, as the thickness of thin film batteries is very small. It decreases the charge diffusion length, and other PVDF binders are not added in this thin film electrode preparation. So thin are then pure and relatively impurity free. From this compact configuration and increases the energy loading in the cells. Next, we have chosen TiO2 as our anode. But you can see from the figure in the right that metal oxides our anode material because it is abundant, cheap, and safe. It is environment at higher voltages, which is 1.7 volts. It has excellent structural stability with high theoretical specific capacity. RF magnetron sputtering technique. For 4 hours, we have done 4 hours substrate temperature of 450 degrees Celsius. The films were then annealed at 600 degrees Celsius in air for 1 hour. Next, you can see we have done the structural characterization using GXRD, and from that graph, you can see the green one, the black one, and the blue one will give us the amorphous anode TiO2. We have pieces of TiO2 and made coin cell type lithium-ion batteries out of that, and done checked the electrochemical behavior out of for all the 3 cells. So we have made coin cells where working electrode was the counter electrode was lithium metal, separator used was F6. The first electrochemical characterization we have done was GCD, which is galvanostatic charge discharge at constant current rate of 0.127 milliamps per centimeter square, and for 3 cycles. So for the first cycle, we are giving 0.75 volts and 0.35 volts. Next, in the 5 volts and 1 volts. The change in plateau is due to the SEI layer formation, which is charge, and the weak potential at 1.5 insertion into TiO2. However, the potential at 1 volt substrate that we have used for the deposition. We have verified this using GXRD. So as you can see from the figure in the right, Fe2O3 peak at 35 degree is prominent at bare SS substrate GXRD also, and the anatase TiO2 we have deposited on SS substrate. Also, in the GXRD sample extracted after 100 cycles of battery operation is giving elemental peak of Fe. So from this layer present on the top of the SS substrate is participating actively in the electrochemical process of the battery. 0.1 millivolts per second for 5 cycles, and you can see in the first cathodic scan we are getting 2 peaks at 0.7 volts and 0.3 volts. 0.7 volt peak is due to the insertion of lithium into Fe2, while 0.3 volts signifies the SE layer formation, as I told earlier. In the canodic scan, we are getting a 1.6 volt peak corresponding to the oxidation of Fe2, Fe2 plus to Fe3 plus. In the subsequent cycles, there are no notable changes observed, and we can infer that the anatase TiO2 electrode is showing highly kinetically reversible approach. This is a Nyquist plot that I have plotted for amorphous anatase and rutile TiO2, and I've circuit model. From that, the fitting parameters that I've got are solution resistance, charge transfer resistance, Warburg coefficient, and diffusion coefficient. So from the table, you can see that we are getting the lowest charge transfer resistance for rutile. TiO2 we are getting, so it indicates the excellent electronic and ionic conductivity that has led us to a better charge discharge performance of rutile TiO2 with a better storage capacity. I will, as you can see from this figure. So this is a GCD. We have a constant current 0.127 milliamps per centimeter square for continuous 1000 cycles in voltage range of 0.01 to 3 volts. Out of these 3, you can see that rutile TiO2 marked the highest capacity of 1.217 milliamp hour per centimeter square per micrometer after 1000 cycles. Next, I have done
Ms. Vasin, I think you have 2 more minutes, okay?
Next, I have done rate capability test also, and you can see from the figure that electrodes have restored their capacities when the current value of 0.032 milliamps per centimeter square, which confirms that they are tolerant to even high current charge and discharge. Next, this is the comparison of our results with the best results so far reported in the literature, and from the table, this is apparent that were the best among us the so far reported in the literature for this system. Morphological characterization using also, it has increased the interaction between the electrode and the electrolyte which happens due to lithiation and delithiation. Are that we have got very high capacity in our lithium-ion battery devices. This is due to that the TiO2, which is having high stability but low theoretical capacity, combines when with the Fe2O3, which is having low stability. Because of the synergistic effect of both of capacity, we are getting a battery which is giving us high theoretical capacity with high stability.
Ms. Bhasin, you will take longer time?
Sorry, sir.
How much time you will take? Longer time?
So one minute.
Yeah, please.
Yeah. So to investigate the structural changes in the root. So I have chosen various voltage points during each charge and discharge cycles to do the exacts. The region, the voltage points have the region A and B is the before constant voltage. Constant voltage plateau region where the structural phase change happens, and then region D is after that. So this is the Zane spectra that I have charging and discharging at each of the voltage points. As you can see during discharging that there is a shift of Ti TiO2 and the oxidation state of Ti atoms is reduced from Ti4 plus to Ti3 plus. Like, as you can see from discharging until at point 3. This is also verified using GXRD, and you can see that till 0.38 volt, I am getting the rutile phase peak, but from 0.2 volt, the peak has gone and anatase peak has started coming up, which has retained it during also we have done the exacts of each of the obtained at different voltage points. This is the exact Fourier transform exact spectra of rutile TiO2 electrode. As you can see, as the first shell of TiO2 is contributed by TiO shells of TiO2, for the rutile phase it's coming at 1.25 angstroms, but for anatase it is coming at 1.44. Likewise, second peak is contributed by Ti shells, and for the rutile it is coming from at 2.42 and 3 angstrom, while for the anatase it is coming at 2.6 angstrom. So as you can see, and TiO2 with a single peak contribution rather than we can infer from this that exact study results that there is a phase change from rutile TiO2 to anatase TiO2 when rutile TiO2 lattice was thin film anode. This is
Ms. Bhasin, can you kindly complete it?
Yes, sir. Yes, sir. This is the fitting that I've done for Fourier exact spectra. And from that, we can infer that during discharging the first Ti coordination shell, there is a gradual increase of Ti coordination from 2 to 4 as the battery is discharged from 0.038 to 0.01 volts because the phase changes from rutile to anatase. This is also verified using Raman spectra. As we have chosen 2 points, 0.52 volt, 0.5 volts, and 0.2 volts. 0.5 is the before structural phase, and 0.2 volt is the after structural phase voltage point. So 0.5 volts is giving us 0.2 volts is giving us the 6 typical vibration modes of anatase. The conclusions we can draw is that during the first discharging cycle, we are getting a constant transition. This is verified by using GXRD and exact measurements, which shows that there is a clear signature of rutile to anatase phase transition at 0.36 volts. And then this is also verified by using Zane spectra and also the Raman spectra of the samples. Thank you.
Okay, thank you. Is there any other questions? Okay, since there is no questions, Ms. Bhasin, thank you again. Okay, kindly stop the sharing and thanks. Yeah, so I think next presentation is tomorrow, and today I think there must be some dinner.
the organizer, I do not know where he is. He was supposed to announce it at the end of the. I don't think he wants us to. उसका हो गया We cannot hear anything. Yeah, means I thought late हो गया.
So we are closing this session now. Yeah, so tomorrow again at 10 we'll join. So thank you everybody. So we can close now.